Greece, an international workshop. To programama σήμερα θα είναι στα αγγλικά. Θα συνεχίσω να μιλάω και στα αγγλικά. Okay, good morning, everyone. I'm Bonna Wescoat, the director of the American School of Classical Studies in Athens, and it's my pleasure to welcome you all here today for the conference, LiDAR and Landscapes in the Archaeology of Greece, an international workshop. It's an honor and a pleasure for the American School to be able to support this initiative, and I'm very grateful to my colleague, Professor Alex Knodell of Carleton College, for being both the initiator of the idea and the chief organizer of the workshop. I also want to thank our speakers for sharing their investigations using LiDAR. The robust response to our call clearly demonstrates the efficacy of this approach and the great value of sharing its potential and its challenges. As this is a workshop, we want it to be as inclusive as possible, and that means we have a very full program. The speakers will need to keep strictly to time so that everyone can be heard. And I now turn to Alex to introduce the workshop.
Good morning also from me. I'll be relatively brief here in the interest of jumping right in. We have an excellent program today, a wonderful lineup of 18 papers. As Bonna said, the response to our call for papers was fantastic. I think pretty much everybody that we invited personally kind of jumped at the opportunity to present their work. And then there were also many people whose work I did not know about with LiDAR in archaeology in Greece. So what we're left with is this wonderful array of 18 papers that we split up into 4 sessions. The first and the last will look at the use of LiDAR in archaeological surveys. The first group of papers will be more focused on a regional scale of analysis, with the last group focused more on sites and their immediate surroundings. The second session will get into more of the technical details of analysis and remote sensing methodologies in the field and the lab. This will include both LiDAR analysis and also comparing different modes of LiDAR analysis with other forms of remote sensing research. And then the third session will make some explicit comparisons between drone and airborne LiDAR survey. So that's the lineup we have. We aim to keep, in the first place, going on in time and keeping speakers to time. But also we hope to keep both speakers and audience members well fueled with coffee breaks and opportunity for further conversation. A further note on logistics is that because of the relatively tight schedule, we'll try to move very quickly from paper to paper. So we would suggest that people reserve their questions until the scheduled discussion periods, which will happen either in the middle of a session or at the end of a session. In sessions with 4 papers, they'll all happen at the end. In sessions with more than 4 papers, there will be 2 discussion sections, one in the middle and one at the end. In these discussion sections, we encourage questions for individual papers, but we also encourage audience members to share their own ideas and insights and knowledge about things that may not have been presented. As Bonna said, we organize this as a workshop due to the kind of collaborative nature or trying to foster a collaborative atmosphere here. But we're also very grateful to all of the kind of institutions, projects, individuals who are making this happen. Especially, I would say, to the American School staff, Konstantinos and Christos and Miguel in back, who are running everything here, and we couldn't be doing this without them. So I think with that, we should dive right into the first paper. The first paper will look at LiDAR-based research in the Phokian Kephissos Valley, and it'll be presented, it's by Katja Sporn and Will Kennedy of the German Institute here in Athens, and it will be presented by Katja. So, welcome.
Good morning to everybody. Thank you very much for the organization. I will start right away. In 2018, an interdisciplinary joint German-Greek cooperation project was launched in the central Kephissos Valley in ancient Phocis under the direction of Dr. Petros Konouklas from the Ephorate of Theotida and Evrytania and myself. The aim was to reconstruct the settlement development and respective sanctuaries, necropolis, and infrastructure throughout antiquity within its natural environmental context. In addition to specific historical events, for example, destructions or resettlements, particularly the question of how natural and/or human-induced phenomena, for example, possible changes in the river course and waterways, effects of floods and earthquakes, affected the use of the fertile fields on both sides of the Kephissos River and the relocation of settlements, is of great importance. The chronological range of the project spans from the Bronze Age to late antiquity, but mainly focuses on the periods from the foundation of the Greek city-states to late antiquity. An approximately 145 square kilometers large area across the central Kephissos River is examined, which paradigmatically includes both sides of the river and the plain, as well as the slopes of Mount Parnassos in the south and Kallidromo in the north. You see the map here. Major sites include Elatia in the northeast, in the northwest, Aia Marina and Tithorea, in the southeast, Aia Marina, Anemomelos, and Tithorea, and in the northwest, the sites of Paleophiva and Modi. This is a collaborative, interdisciplinary project involving prehistoric and classical archaeology, ancient history, landscape and building archaeology, the geosciences, historical and physical geography, as well as climatology and speleology. Archival sources, such as historical aerial images, plans, and other material from previous research are consulted, and important new data has been specifically acquired for the purposes of the project. Such is the case of the multispectral satellite imagery taken in 2020 by Worldview 3, covering an area of around 735 square kilometers, which was analyzed by our colleague Simon Hoffmann, who could provide preliminary results mapping nearly 2,500 anomalies, which will be further processed and correlated with the results of our LiDAR data, the main theme of our workshop today. Since the satellite images cover a far larger area than the LiDAR, which is limited to our study region, sites around Kalapodi in the Assos Valley, where the Institute conducts research for more than 50 years now, can now also be further investigated by analyzing various multispectral satellite images, for example, the Acropolis of Hyampolis, as shown here on the right. To date, the region has been studied primarily from a historical perspective, with a particular interest in the numerous fortifications, some of which are still in excellent condition. Most recently, Petros Konouklas and Eric Laufer were able to document ancient Tithorea in a preceding project between 2016 and 2019, with a particular focus on the Hellenistic fortification walls of the site, one of the best preserved examples in all Greece. However, in terms of landscape and geoarchaeological aspects, the Phokian Kephissos Valley remained comparatively under-researched. Our colleague, Stefan Biernack, therefore conducted, back in 2018 as his master thesis, a GIS analysis in preparation for our current project, in which he analyzed all archaeological data within the study area mentioned in relevant literature in terms of overall settlement development patterns. Such GIS-based analyses include, for example, cost surface analysis, a possible reconstruction of the route network, you see these images here, or visibility analysis from selected fortification sites. In 2018, the Fritz Thyssen Foundation generously funded an airborne LiDAR survey in order to clarify the natural conditions and to provide a data set for identifying ancient sites. The entire study area was recorded by Geosystems Hellas in 2 days using a small manned aircraft, which came, I think, from Belgium back then, at an altitude of around 1,000 meters, equipped with a specialized camera and a laser scanner, both with integrated GPS INS equipment. This provided the project with both a digital elevation model produced from the LiDAR data and over 1,600 high-resolution aerial photographs of the study area. The aerial photographs were merged into a georeferenced ortho image with a resolution of 8 centimeters per pixel, and the LiDAR scans generated a point cloud that was further processed and analyzed. After filtering out erroneous or unusable data, the 500 to 500 meters LAS files each contained around 2.5 to 15 million points, which is 10 to 60 points per square meter, or 1 point per 13 to 32 centimeters. Balancing file size, manageability, uniformity, and information content, it was decided to set the grid size of the derived GeoTIFF files to 25 to 25 centimeters, which corresponds to about 2 to 16 filtered points per grid cell. While basic classifications were conducted by Geosystems Hellas, additional classifications relevant for further processing, such as vegetation, ground, and buildings, were defined. However, as the broad terrain variation not always allowed an automatic classification, 2 models were created from each LAS point file. An unfiltered elevation raster, including vegetation and noise, the digital surface model, and a filtered elevation raster without vegetation and noise, but with recorded built structures and natural features, the digital elevation model. The most valuable derivative of this dataset is the simple local relief model, in which the natural elevation gradient, which is hills and valleys from the DEM, is removed, thereby highlighting smaller elevation changes that most likely signify features of potential archaeological or environmental interest. Based on the first detailed analysis of the LiDAR data, conducted again by Stefan Biernat, a total of around 2,700 anomalies were mapped, exemplified here with the site of Archaeology. These anomalies serve as a crucial base data set for the exploration and future endeavors of the Kephissos Valley project. In order to further highlight the advantages of LiDAR-based research in the Kephissos Valley, but also to showcase the particular potential in following a multidisciplinary approach and applying other remote sensing as well as field archaeology in addition to LiDAR, the following shall briefly present some results. First, from ancient Elatia, which, next to Delphi, was the largest polis in ancient Phokis and a particular focus of the project. On this slide, we see a detail of a LiDAR model of Elatia, and here, a 3D visualization of the LiDAR-based DEM and ortho image as modeled by Simon Hoffmann. Fieldwork in Elatia began already in 2018, which included geophysical prospections conducted by our partners EMS4, Rethymnon, an intensive architectural survey, as well as test trenches excavated by the University of Munich and us. This slide shows the overall results of these collaborative efforts, from which we can now, for the first time, largely determine the course of the city wall and thus the approximate size of ancient Elatia, of this city, which was almost 100 hectares large, and we can also see the outline of the insula in the lower city. Chronological issues could also be clarified. Particularly the Acropolis, which is here, demonstrates why different methods must be applied. Prior to our investigations, a fortification wall and a small fort was already known. The fortification wall is this wall, and it's with a cyclopic style, let's say. So these were known. They were also visible in the orthophoto, which we generated in 2018. The fortification and the castro was mapped by our architectural survey in the field. You see it here in blue. But the LiDAR, particularly the SLRM, not only revealed the outer fortification, but a second line of fortification in the inside, and also clearly marked here in black, the older trenches conducted here. Geomagnetics and particularly GeoRadar could not offer additional information concerning the two wall courses. However, the GeoRadar results on the left, in comparison with the LiDAR-based SLRM on the right, nicely underlines the added value and advantages in applying different methods and evaluating their combined results. Because in the LiDAR you saw the two lines of wall, whereas only in the GeoRadar we could detect the settlement which was on the Acropolis. Case study 2. A similar situation can be found at the extra-urban sanctuary of Athena Chronaea, lying some 3.5 kilometers northwest of Elatia on a high plateau in the Kallidromo mountain ranges. In Hellenistic times, the sanctuary served as the archive of the Phokian koinon, as its seat was then in Elatia. The sanctuary is currently studied within the framework of a PhD project in building archaeology by Elea Königsecker. Thus far, only the classical temple was known through the excavations by Pierre Paris in the 1890s, and Jean-Pierre Michaud mapped a large fortification wall in the 1960s. The LiDAR images, however, clearly show that the interior was extensively built with structures of yet unknown date. Case study 3, Aia Marina. Opposite of Elatia, along the northeastern slopes of the Parnassos, is Aia Marina, a site which was first only known for its castro. See some photos here. And since our recent publication of this older Gose Schober plan, which we had detected in our archives, which comes from the 1920s, and we published it only in 2017. Since then, we know that there was also a circuit wall of the lower town. After an architectural survey, we were able to trace the course of this lower fortification wall, which enclosed an urban area of about 10 hectares. Although partly visible on the surface, the LiDAR data revealed numerous additional anomalies in the town center, indicating irregular street grid and house structures. On this basis, a large P-shaped structure with 11 internal room units could be documented for the first time. In 2022, test trenches have revealed that at least parts of the structure date back to the 3rd century BC, with a reuse in the Byzantine period. Case study 4, coming to the end. We turn to the western part of the study area with a particular focus on the site of Paleotheva. A British aerial photograph from 1945 clearly shows three sides of the square fortification structure, which is around 350 meters long, with partially preserved towers and central gateways. While the site is described in modern archaeological literature, it has only been mapped very schematically. The LiDAR now clearly shows that many structures are still preserved underneath the modern vegetation. Although only loose stones and rubble indicate that the now largely destroyed fortification in the field, in 2019, geophysical test prospections could at least suggest that the fortification wall and some internal structures were not completely ploughed away, but are still partly preserved under the surface. Following the preparatory work of Simon Hoffmann, traces of a possible bridge across the Kephissos River in line with the presumed northern gate of Paleothever were investigated in 2021. This hypothesis may be corroborated as exclusively at this point, large ashlar blocks were found in the dry riverbed on the right side, which could well have once belonged to a bridge. Case study 5, and finally, we do not wish to withhold an exceptional find in the Kephissos Valley. For years, capitals and column drums of a Doric temple were known in the modern village of Modi, which typologically fall in line with the known capital types from other classical temples in the region, such as Kalapodi, Elatia, or at Athena Kranaia. Our colleague Petros Konopoulos was able to get to know the original find spot of these architectural members, which you see here, which was scattered with roof tiles of the classical period and other finds. The geophysical prospections, radar and geomagnetics then most clearly revealed the outlines of a peristyle temple measuring about 45 to 19 meters, thus directly comparable to the classical North Temple of Kalapodi and much larger than the Temple of Athena Kranaia at Elatia, smaller than the later Temple of Delphi, of course. While this discovery raises many important questions as concerning the identification of the cult, the polis affiliation, the chronology, and so on, what is remarkable for the theme of today's workshop is that the LiDAR revealed no structural elements whatsoever. This becomes particularly clear when sketching in the mapped outlines of the temple on the basis of the geophysical prospections, once more highlighting the advantages of applying multiple remote sensing and field archaeological methodologies in addition to LiDAR. And with this, we hope to have raised the importance of interdisciplinary collaboration, issues of scale when considering data on a macro, meso, as well as on a micro level, and its various potential for further reaching investigations. Thank you for your attention.
Press this to turn. Can you hear me? Yeah, great. Thank you, Katja. Our next speaker is Sylvian Fachard, who's presenting a co-authored paper with Chloé Chezeaux on LiDAR-based remote sensing and ground truthing in the Eretria-Amarynthos survey project. Syl, if you'll allow me 1 minute, it occurred to me that there's a certain amount of probably assumed knowledge for most of the presenters. For example, what is LiDAR and what does it do? Maybe we should say something for people in the audience who may be less familiar with this. So I'll take 30 seconds to tell you something about that. In brief, LiDAR stands for light detection and ranging. In this way, it's an acronym that's become a word like radar, radio detection and ranging. And its main utility as a remote sensing tool is as a form of 3D laser scanning. One thing that's particular about LiDAR, at least aerial applied LiDAR, as we are mostly talking about here, is its capacity to penetrate vegetation coverage. So especially in heavily vegetated areas like forests, you can kind of peel back that layer because it's shooting millions of laser pulses, and some of them get through to the ground level. So you can peel back that vegetation layer and come up with a bare earth model or the scan of the ground surface as it exists. So that's my 30-second introduction to LiDAR for those of you who may not be part of the LiDAR cult represented here. So I'll turn it over to you.
Thank you, Alex. The Eretria-Amarynthos survey project, or should I do something for the PowerPoint? Or? Okay. So the Eretria-Amarynthos survey project was initiated in 2021 as part of a 4 years archaeological project around the sanctuary of Artemis Eretria-Amarynthos, which is, as you can see on the map, situated some 11 kilometers east of Eretria. Now, the main goal of the projects were to study the emergence of the shrine and its long-term insertion within the ancient landscape. And the project is a collaboration between the Effort of Antiquities of Evia, of Euboea, and the Swiss School of Archaeology in Greece under the co-direction of Dr. Angeliki Simosi and myself. Now, thanks to the generous funding of the Swiss government and the Swiss National Scientific Fund, the project includes a large team composed of professional archaeologists, postdocs, and doctoral students working in parallel on the excavation of the temple area and the archaeological survey at the same time, which I think allows the sharing of information, data, pottery expertise, as well as a joint study strategy and publication. So in the last 3 years, excavations focused on the Bronze Age remains on the hill of Paleoclesias and the early Iron Age horizons in the sanctuary, where spectacular discoveries were made in the so-called area of the temples. We have 2 successive hecatomb type temples built in the early 7th century and late 6th century, and a votive deposit which was found in the temple area of more than 700 objects, including vases, figurines, and weapons. Now, I'm not going to talk about those. I'm going to talk about the extramural temenos area. So the survey. So our survey is an intensive and extensive type survey that focuses on the region's archaeology, human ecology, and long-term history from the Bronze Age to the early modern period. And we also address more specific issues that are related to the sanctuary of Artemis, such as the relations between the shrine and the settlement pattern and the topography of the sacred landscape. Now, the survey study area comprises the vast coastal plain stretching between Eretria and Amarynthos, the Sarandapotamos Valley, as well as the slopes of Mount Vudohi and Sorvuni. And since 2021, we have systematically surveyed an area of 22 square kilometers, uncovering nearly 200 archaeological features from all periods and counting over 110,000 pottery sherds and tile fragments on the surface. Now, despite the challenges posed by the extensive development of modern urbanization along the coast, the survey, kind of surprisingly, has been able to map broad patterns of ceramic distribution and long-term occupation across the landscape. And for those of you who know the area, especially in the summer, you know how densely constructed it is with villas. So before the start of the project, we commissioned a LiDAR survey of a vast area stretching from Lefkandi to Mount Sorvuni to the Greek company Areophoto in Thessaloniki. The data enabled the production of DTM, DSM, aerial photos, and a digital elevation model covering an area of about 200 square kilometers with a spatial resolution of 25 centimeters. And you have all the specifics here with the deliverables. We don't have time to go into the details, and if you have some questions regarding the data, I'm very happy to say that Pericles and his team is here in the room, and they can answer all the technical issues you might have. The combined LiDAR data has played a fundamental role in the project since the very beginning, offering unmatched aerial coverage, guiding teams in the field, and leading to significant archaeological discoveries, including terrace walls, roads, towers, ruined Byzantine chapels, settlements, and even illicit excavations. Now, due to the efficiency of the workflow and method, the extensive survey teams working in a very difficult terrain were able to save a very significant amount of time, and I will focus on this in the second part of my paper. Now, this paper will briefly overview the survey LiDAR data, including the protocol and methodology, the workflow, and its main advancements and limitations. And throughout 3 seasons, implementing LiDAR-based remote sensing and ground truthing has become an integral part in examining archaeological landscapes, resulting in, I think, very significant advances. So as mentioned earlier, the data was acquired through the Thessaloniki-based Aerophoto company, and I would like really to express my gratitude to the entire staff, in particular Periklis Boutsoukis, who accompanied us in every stage of the process. Now, the LiDAR also provided the data for building a new high-definition DEM, and it also provided, of course, the orthophotos, providing us with really eyes on the ground. Now, nothing would have been possible without, of course, the Aerophoto team, but without Tom Garrison's guidance and Alex Knodell's collaboration. And Tom accompanied us through the acquisition process and provided technical guidance for LiDAR data processing on GIS. And I still remember when Alex and I were Zooming when acquiring the data, but also when we got the data in Eretria, and we spent some few days working on the data in order to calibrate it to the ground. So I would like to thank both of them. Now, the Acropolis of Eretria served as the perfect testing ground for evaluating the LiDAR data's accuracy. It contained a wealth of previously identified and mapped architectural details, as well as some key and wild olive vegetation covering these remains. And because of our knowledge of this area, before LiDAR, it was really very helpful in order to produce all the images that you will see. Now, using QGIS's relief visualization tool, we generated hillshades, slope gradients, multi-scale relief models, and sky view factor images. The images were then assembled in the same layer in ArcGIS Pro, using transparency and various imaging characteristics, again using the Eretria Acropolis for fine-tuned calibration. We then generated a comprehensive collection of DTM tiles covering the entire survey region. And the protocol has been perfected over the years, and it's now available to our students who work on the survey, and they can progressively acquire the technical knowledge to process the LiDAR data themselves. And each tile is then used for remote sensing and ground truthing using ArcGIS Pro. Now, each grid is numbered, and the detected features and anomalies are drawn, numbered, and commented on a shapefile from the screen. Subsequently, the recorded anomalies serve as a guide for survey teams in the field, especially for the extensive type survey teams that work in challenging environments characterized by mountains and steep slopes and dense vegetation. The layers then are uploaded on the cloud, and they're used by the survey teams in the field using iPads or even iPhones, as you can see here on the screen. And we use 2 apps from Esri, the Esri Explorer and the Collector apps. And this allows every team to use the processed LiDAR data in the field, and it really facilitates localization of anomalies and enables also editing in the field. So you can see here the app, you can see the different maps that we upload with all the survey data that is available for the surveyors, and then you can see the anomalies that show up on the satellite imagery on your phone. And you can just click on any of them with your finger and go and find it really easily. And when you zoom in, you can see the LiDAR data that is on the cloud here with the number of the anomalies. You can also remove the layer here with the LiDAR and have the satellite imagery. And then you have the first commentary by the remote sensing team. And then in the field, you can add your own, which is cloud-based. So you have the data right away. And this really facilitates the entire process, the chaîne opératoire, from the office to the ground. And this, it's really a huge amount of, again, of time. Okay, I will now provide some examples of our matter of functioning, how we function, chaîne opératoire, as I said, to showcase obstacles and problems, but also to provide some data criticism and highlight a few success stories. So given our area, which is really heavily urbanized, there's of course much noise and pollution, such as fences, houses and villas, roads, artificial terracing for villa construction, agricultural pipes and irrigation, illegal dumps filled with destruction debris and bulldozing. Now, at the beginning, an untrained eye gets easily confused and lost in translation. However, following a few ground truthing operations, the eyes get really trained and we progressively isolate this kind of pollution and noise by recognizing modern features, bulldozed mounds, pipes, and modern cisterns. Therefore, I think it's very important to have the same team behind the screen and in the field for maximum efficiency. Now, an essential component of the project was to study the communication network, modeling the ancient road network, including the sacred way that linked Eretria to the sanctuary of the Artemisium. Now, preliminary work was done on GIS, first by georeferencing old maps and digitizing 19th century paths and roads, and then by building least cost paths and conducting optimal region connection analysis on ArcGIS Pro. Then, the LiDAR-based remote sensing was used to detect and recognize potential road path segments, which are typically characterized by the following features: long lines, elongated terraces stretching over several fields, zigzags and slopes, and potential retaining walls supporting roadbeds. Now, a good case study is the Sacred Way, whose existence has been recorded by the American School of Classical Studies at the very end of the 19th century. And you can see here the original mapping with the Sacred Way and the modern way surrounded by graves. And you can see here Alex giving a hand, trying to find some remains from it in the sanctuary, the necropolis of Eretria. Now, we conducted, of course, close remote sensing along all these potential paths, which were followed by the different roads, but also by the Sacred Way. And then we sent the intensive type survey teams in the field. Now, the LiDAR processed images showed a small but consistent and continuous anomaly oriented east-west and stretching over 800 meters, which is a lot. And this was in the middle of an area characterized by a high density of funerary finds, as you can see here, and corresponding to Eretria's east necropolis extension. Now, we interpreted this anomaly as a road supported by retaining walls surrounded by funerary monuments, including marble sculptural elements that you can see here down in the right. So this was, I think, a good case study for locating a road, but of course, the locals knew that already, as you can see here. So I'm going to focus now on other examples which are outside the plain, and they're in the very difficult terrain on the slopes of the mountains, which are typically covered by maquis or high vegetation. And I think that I'm going to highlight a few interesting case studies. So you can see here the orthophotos. We're working in high slopes in this area, and when you do of course, the remote sensing using the very high quality imagery we have, you don't see much. But then when you plug in the LiDAR, you can see very interesting anomalies here. So we're in a schist environment here, but you can see several small anomalies, probably here wells or pits. But the most interesting was this one, which is oriented east-west. It's very high relief. And it turned out to be a late Byzantine and early Ottoman church. So that was a very interesting and unknown discovery. We have other examples here where you can see very distinguished anomalies showing up here on the hillsides. And this turned out to be around a tower which was partly covered by vegetation, and it could really be seen on orthophotos. And it's probably a tower or an old windmill, Byzantine windmill, we're not sure yet. What is really interesting, and I'll finish up with these two case studies that are related to the accumulation of anomalies in small areas. And I'm going to show the examples of two unknown settlements that we discovered thanks to LiDAR data in the survey area. So here it's an area called Aion Asomaton, and you can see here several villas. We have obviously some noise, some pollution. You can recognize some roads here in villas. but we found in a karstic environment 2 wells here, thanks to the anomalies that show up really well. Here, this area showed many different relief anomalies, and when we hit the ground, we realized they were ancient quarries that were used in antiquity and in the Byzantine period. Here we found several different anomalies that really looked different from what we have usually, and it turned out to be a small necropolis with graves that were looted and created all the anomalies that we saw. And finally, another building here, an anomaly, which looked like the previous one I showed, oriented east-west again, with very high relief densities. And here it turned out to be another late Byzantine, early Ottoman period church. Another example was here in the mountains of Mount Cervuni at an altitude of close to 500 meters. And this area was known for its Byzantine church here, that you can see here in the photo, and a well and a cistern. But all this area was never explored before. It's a very difficult terrain, limestone environment. And the LiDAR data here showed a huge concentration of different anomalies. Starting here with these anomalies here that you can see that turned out to be karstic cavities. We have several springs and sources, and we found this really interesting anomaly here, which turned out to be a large well, which was carved in the limestone. And this well is modern as it showed up, but we found some classical period pottery too, so it was probably a classical well as well. But you can see the concentration of anomalies in a given area was really interesting, and it pushed our focus in the area. And finally, we found these areas here with many anomalies. You can see this huge concentration that turned out to be illegal excavation. It was conducted, and when you look at the aerial photo, all these illegal pits were covered by vegetation. You can't really see them even when you walk a few meters away from them. So really these cases show how LiDAR was really crucial for finding these 2 settlements that I just mentioned before. It's time to conclude, to keep a time. So in our case, we conclude that LiDAR provides really a significant value-added benefits to archaeological survey, but only if it's accompanied by field survey and autopsy. It really gives us eyes on the ground. It's essential for the identification and description of many types of features. It's a huge gain of time and resources during fieldwork seasons. And it provides a comprehensive field strategy for an extensive type survey. It represents, I think, also a critical and a decisive tool in what I call Greek slope archaeology. And I think we finally have a tool for exploring the hilly and the very rough regions of survey areas in mountains and slopes, which can amount to up to 80% of the land in central Greece. And students, when they process the data and when we work and do the ground truth thing together, they often ask me, how did you do it before LiDAR? And I think that military generals might have been asked the same questions after the arrival of aviation in ground warfare. Thank you very much.
Thank you, Syl. Yeah, I think we used to call during the Mazi Archaeological project how we did it without LiDAR maquis bashing. It was very painful. Our next speaker is Bonna Wescoat, who is speaking for a large collaboration with the Samothrace LiDAR project. This also involves Dimitris Matsas, Michael Page, Christopher Witmore, Tom Garrison, and Brody Manquin. Did I get everybody there, Bonna?
You did. Thank you so much. And my sincere thanks to both Alex Knodell and Sylvian Fachard, who were so generous with their time and their knowledge and their patience when we began this project. Also to Pericles Boutsoukis, who was also equally kind, generous, and informative in having us make the best choices. So in conjunction with American Excavation Samothrace, and as part of the Samothrace Exploration Project, the Samothrace LiDAR project, conducted by the co-authors of this paper, aims to shed light on occupation and land use on the wooded and mountainous island of Samothrace in the northeastern Aegean, from just before its earliest human habitation to the the recent past and even the present. We are very much at the beginning of this project, but our preliminary results that we share today are, we think, very promising. It has long been our goal to integrate our several archaeological investigations into an overarching diachronic investigation of settlement and transition across the island of Samothrace, from the Neolithic to the recent past. And because of its renowned mystery cult, the early discovery of the famous Winged Victory, and the remains of highly innovative Hellenistic architecture, the Sanctuary of the Great Gods on the northern coast of the island has attracted the sustained attention of archaeologists since the second half of the 19th century. The adjacent ancient city has received far less attention, making it a prime target of interest for LiDAR investigation. From spolia built into the Gattelusi Towers, built in the 15th century, we know the ancient city had multiple monumental marble buildings. Thus far, the finds from the city and the sanctuary are no earlier than the 7th century BCE. Moving beyond the city and sanctuary, investigation of the islands conducted over the last 35 years, chiefly by our colleague Dimitris Matsas, have significantly expanded our understanding of the island's cultural trajectory from the late Neolithic to the recent past. Archaeological research at the Tell settlement Mikrovuni opened a deep window into the island's prehistory and connections with the Balkans, the Troad, Western Anatolia, the Aegean, and Minoan Crete. Excavations at Mikrovuni have established a cultural sequence extending from the beginning of the late Neolithic to the beginning of the late Bronze Age, with a gap in the 4th millennium. Research in the area of Rikos, Salida, and Yalomantra site proved that the occupation here started at the very end of the late Bronze Age or the very beginning of the early Iron Age. And archaeological survey aiming at locating sites of this period verified the existence of contemporary sites at elevations between 400 and 600 meters along an arc extending from the site of Kremniotissa in the southeast to Vrikos in the northwest. Thus far, however, we have not located earlier late Bronze Age surface material on Samothrace. This void, unlike Troy, Lemnos, and Imbros, also occurs on the mainland of Aegean Thrace. So a key research goal is to determine if this void is real or if we have simply not found it yet in the archaeological evidence. In addition to excavation, the intensive diachronic Samothrace archaeological survey conducted in the late 1980s through serial fields in the southwest plain of the island determined the changing character of settlement and land use over the long term. This work concentrated on the slopes under serial cultivation to the west of the Xiropotamus and Katsampas rivers in proximity to Mikrovuni and covering roughly 1/9 of the island. The survey excluded the coastal plain to the east of Xiropotamus and Kapansas rivers because that area is mostly covered by extensive forests and maquis. With few exceptions, the material collected in this survey spans from the late 6th century BCE through the 14th to 15th century CE. So actually, in response to the students, how you did it over centuries and very slowly. With the Samothrace LiDAR project, we have an excellent opportunity to integrate these several initiatives and include others into a whole island investigation of occupation and land use, again, from prehistory to the recent past. So our basic aims are to, 1, investigate this seeming void in the late Bronze Age, a period of complex and varied patterns of transformation and transition across the regions of the northern Aegean, Eastern Balkan Peninsula, and northwest Anatolia. 2, document the agricultural landscape, with which is rich in agrarian ruins, distinctive irrigation networks, and pre- and proto-industrial installations. 3, locate possible anthropogenic features currently obscured by the wooded understories across the island. And 4, gain a better understanding of the landscape generally, given its rapidly changing geomorphology. We started by creating a map identifying 18 major areas of ancient habitation outside the urban center of Kemeriotis. During the summer of 2023, we commissioned Aerophoto Company Limited of Thessaloniki to undertake a LiDAR survey of the three most important territorial zones of human activity on the island. And on the right, you see the flight plan along with the equipment and specifications. The north and northeastern coastal zone included an area of about 40 square kilometers, and the two southwestern flight plans had approximately the same total area. You'll notice that the South Mountain Range divides these two regions. Current evidence of human settlement does not really rise above 600 meters above sea level, so we surveyed the slopes to an elevation of about 700 meters above sea level. I mean, ideally, we would have loved to do the whole island, but we had to be strategic. Now, these passes have generated a large amount of LiDAR data, and for this project, the Samothrace team formed a partnership with Tom Garrison and Brody of the LiDAR and Landscapes of the Ancient Mediterranean and Americas Laboratory at the University of Texas in Austin to process the data. For the first phase of our analysis, we decided to focus on the northern coastal area of the island, which includes the area south of the sanctuary and the ancient city, as well as several abandoned settlement areas around perennial rivers along the forested northeastern region of the island. You see them circled here. Now, the advantage of starting with the sanctuary area is that we have a deep basis of documentary evidence against which we might compare the LiDAR imagery. And here you can see the aerial view and then the LiDAR imagery of this region. Clearly you can make out what really we find very dramatic on Samothrace, which are deep river torrent valleys carved by torrents and perennial streams. You can make out here the modern village, and you can also, I think, see the sanctuary. Sanctuary is here. The ancient city is here. You can make out the city wall coming along here. Gattelusi Towers are here. And then an area of investigation, which might be the area of the Sanctuary of Athena and the location of those marble buildings we were speaking at earlier. Modern village over in this area. Now, LiDAR offers a significantly crisper image of both topography and constructions than the UAV imagery we had previously been working with. And it works especially well in conjunction with the 1957 military aerial photographs, which you can see here, and they act in a complementary basis to really, I think you can make out here. This is an important part of the ancient city wall that we're working on right now with Tower A breach in the wall, and then the west gate, which we believe is now, we've identified as the gate into the sanctuary from the ancient city. But the field boundaries, which you see here, are quite also crisply indicated in the 1957 photo. So again, bringing together various forms of evidence is crucial. We also conducted a magnetometry survey in this region in 2023, and were able to tease out a number of smaller scale structures. We had been working in this area using kind of traditional methods over the past several years, and this is what we have been working with in our GNSS survey. And again, it mapped, this was done totally independent of the LiDAR, it mapped directly onto the LiDAR, which was terrific. And while we can make out the structures more easily in certain other forms of reference, the landscape features were really clearly and articulately captured by LiDAR and make for a much richer image of the area. Now, just moving across the the island. I just want to bring your attention to a few of the other places. As we said, one of our major goals of the project is to understand the agrarian landscape of the island in areas of long habitation, much of which are deserted today. Along the largely wooded northern coastal plain of the island, ruined remains of past settlement areas are concentrated along perennial rivers, and evidence of habitation, again, largely covered by canopies of oak and plane with patches of low fern. And here the LiDAR imagery dramatically enhances our ability to record land use. The imagery from the area of the Christos Monastery and the Doyani River reveals the complexity of early settlement in richly terraced lands surrounding the monastery. We can now clearly record abandoned plots surrounded by interlinked stone enclosures, extensive terracing and habitation areas. This is all, just let me say, here is the modern village of Therma. This is the region we're speaking of, and it's entirely deserted today. And although we could observe through field walking that settlements associated with the monastery, maintained a diachronic system of open stone or earthen water conduits that were integrated with the agricultural field systems, we can now really clearly map it. Similarly, imagery covering the Phonias river basin up to a height of the first cataract reveals a large settlement with numerous enclosures and other features extending along the banks of the river. Here again, see this area here, again, and here as well. And again, a network of irrigation channels directed the water towards individual field plots that were encircled by low ditches, observable from the ground, but now here really conveniently mappable through LiDAR. And finally, imagery from the sites of Ciuveliu and Castelli in the region of Apano Meria opens a window on the intricately settled agrarian landscape likely associated with the sizable fortress at Castelli. This network was also tied into modern field systems that now are largely used. Actually, this is area of use for fodder crops, pasture, or just abandoned to their own devices. Now, from this initial processing, and remember we just did this a few months ago, it's clear that LiDAR imagery offers an excellent opportunity to document habitation and land use across large areas of the difficult wooded and mountainous terrain of Samothrace. It's already become a central resource in building towards a macro view of the entire island. And therefore, we would like to thank the Richard C. McDonald Elliott Endowment for Archaeological Research from the Archaeological Institute of America, American Excavation Samothrace, Emory University, Texas Tech University, and University of Texas for supporting the Samothrace LiDAR project. Thank you. We're doing well and ahead of schedule, so it's now my pleasure to introduce the next speaker, who is the organizer of this conference, Alex Knodell, who will speak about post-fieldwork LiDAR applications in archaeological surveys, feature recognition and quantification with the Small Cycladic Islands project. And the authors of this paper are Alex Knodell, Evan Levine, Sam Weg, Michaela Fielder-Jellsey, and Dimitris Athanasoulos.
Thanks, Bonna. Morning again, and thanks everyone for being here. We're delighted to be here to tell you about our ongoing program of LiDAR analysis with the Small Cycladic Islands project, or SCIP as we call it. All right, we're in business. SCIP is a regional archaeological survey focused on the uninhabited islands of the Cyclades. It's a collaboration between the effort of Antiquities of the Cyclades, the Norwegian Institute at Athens, and Carleton College, and it's directed by Dimitris Athanasoulis, myself, and Žarko Tankasic. Since 2019, we've carried out systematic pedestrian surveys of 67 uninhabited islands across the archipelago, and we have our final field season of survey coming up this summer. In 2022 and 2023, we acquired LiDAR data over 97 currently uninhabited islands in the Cyclades, working with the Thessaloniki-based company Aerophoto, who we'll hear about and from a lot today. The goals of this work were several. First, to supplement and expand our knowledge of areas already surveyed by SCIP, 2019 to 2021, many of which were heavily obscured by vegetation cover. Second, we used LiDAR as a precursor and guide to our own pedestrian survey work in 2022 and 2023, and we'll do so again this coming summer, especially for large islands that cannot be surveyed at the same level of intensity as smaller ones. Third, we wanted to investigate islands that are well known and have been surveyed by other projects using other methods. And fourth, we wanted to cover areas where it was not going to be possible to carry out pedestrian survey work due to issues of accessibility, size, or other constraints. This paper focuses on the first goal, in order to provide a different, and in some cases more comprehensive view of archaeological landscapes that have already been subject to intensive pedestrian survey. We present the results of the post-fieldwork examination of aerially acquired LiDAR data over 39 islands surveyed during the first 3 seasons of the project. In the first place, we have a methodological aim of comparing patterns of feature recognition during pedestrian survey and LiDAR analysis. Second, we examine some interpretive issues that arise from this work, especially concerning land use, landscape modification, and chronology. We'll begin with a few words about data processing and workflow. Point cloud files were classified by Aerophoto using the basic schema shown here, and then interpolated to create digital surface models and digital terrain models, the former including all classifications, and the latter the bare earth model with vegetation removed. One issue is that sometimes archaeologically interesting features are removed along with the vegetation, and this necessitates the use of multiple visualizations, including high-resolution aerial photos. Each DTM and DSM were used to generate derivative products in the Relief Visualization Toolkit. After some initial experimentation, we developed a standard analysis protocol that involves a systematic inspection of different visualizations that highlight different types of features. Compare these 3, for example. This one, and this one. The next step is the identification and classification of features and areas of interest in line and polygon vectors, from which we can assign and then analyze qualitative and quantitative information. This example from Kytriani shows the features documented in the field on the top in blue, with the features documented via LiDAR analysis classified according to function on the bottom. We can also draw important statistical information from this data set. For example, that over 12 kilometers of terrace walls provide about 19 hectares of arable land. The total size of the island, by the way, is less than 1 square kilometer. You can see how easily these terraces are obscured in other data sets, and even on the ground. But when the vegetation is peeled back, they're readily apparent. Strongilo provides another good example. This is southwest of Antiparos. And here we documented some terracing on the ground, but failed to appreciate the full extent and potential productivity of these systems during fieldwork, including in several areas that we missed entirely. One simple metric for comparing field and LiDAR-derived data sets is the number of documented features. we find the total length of documented features to be a slightly more useful metric. On all islands surveyed in 2019 to 2021, we documented a total of 530 features in the field. Subsequent LiDAR analysis resulted in a total data set of 610 features, or 80 newly discovered ones. The difference is much more pronounced when comparing total length of these features, where about 31 kilometers of features were documented in the field, with 87 kilometers in the final combined analysis, so nearly 3 times the kind of length of walls were documented. However, we should note that not all features documented in the field are also visible in the LiDAR. Some 28% of total features were observed only in the field, but these features accounted for less than 2% of feature length. About 33% of total feature length was only visible in the LiDAR. This leads to the somewhat obvious conclusion that small features are less visible in the LiDAR than large ones. Nevertheless, though, there's substantial overlap. Where LiDAR revealed the most was in situations, mostly on larger islands, where heavy vegetation obscured the surface and large terrace systems were present. Unsurprisingly, there's a strong inverse relationship between the amount of new information gained from LiDAR analysis and average visibility documented in the field. There's also a correlation between island size and LiDAR-only features. Researchers can therefore predict the utility of LiDAR data in project areas by considering vegetation indices and overall project area size. Are there trends in the identification of certain types of features? Yes. In the first place, we see that LiDAR is good at identifying large-scale landscape features like terraces, walls, and so on. When breaking down features by category, we see that terraces, paths, and roads are highly recognizable. Types of features LiDAR is likely to miss include small, low-to-the-ground features, interior walls of buildings, and walls that can be identified visually by partly buried stone lines in person or using drone photography. But those are less apparent in LiDAR, sometimes entirely unapparent. We note that the types of features that may be missed frequently occur in the vicinity of features that are conspicuous in the LiDAR data. Therefore, they're still likely to be identified during the course of ground truthing or a site documentation phase of a project. For us, the most interesting results of the LiDAR analysis and feature classification come from quantifying these data sets. More specifically, we can aggregate length and area calculations to compare overall levels of investment in different islands for different purposes. We can also compare that to environmental data, like island size and other data collected in the course of the pedestrian survey. For example, an early hypothesis that there's a correlation between island size and scale of investment, represented by feature construction, and use, represented by overall pottery counts, is largely confirmed, although there are, of course, some deviations. We turn now to some more thematic questions concerning the agrarian landscape and life on small islands. We focus our attention here on 2 particular questions. First, determining the statistical significance of agricultural features, and second, the relationship between agricultural productivity and population carrying capacity of these now uninhabited islands. In the future, these results can be tied to known settlement patterns from nearby inhabited islands in order to determine how and to what extent anthropic activity on these small islands differ from their larger neighbors. Agricultural terraces serve to control and reshape the landscape of these islands, creating discrete zones of agricultural productivity. Focusing our attention on these areas offers the opportunity to explore questions of productivity, population, and links with broader socioeconomic processes. I jumped the gun and got to this slide early. Time for some statistics. The total area of the 39 islands surveyed by SCIP between 2019 and 2021 was 839 hectares, with an average area of 22 hectares per island. Between field walking and LiDAR analysis, we isolated a total of 88 zones of human activity: terraced fields, pastoral enclosures, structures, etc. By far, the most common functional category of these zones were terrace systems, with a total area of 87 hectares and an average area of 3.2 hectares per system. For each island, then, we can expect something like 2.6 hectares of terrace land, again, working in averages. Assuming a mixed wheat-barley crop, this would provide nutrients for an average of 2 to 3 individuals, following the general parameters developed by Foxhall and Forbes and broadly accepted in pre-modern Cycladic contexts. Let's refine these estimates by exploring the terrace systems of 2 islands in particular. Dionysia, at slightly above average size at 37 hectares, and the aforementioned Strongyllo, the largest island surveyed during these field seasons at 165 hectares, or 1.65 square kilometers. 4 areas of terraced cultivation were documented on Dionysia, covering almost 10 hectares of the island's 37-hectare area, 27%. If these terraces were all functioning simultaneously, then the island could have supported a modest population of 10. From the large enclosure in the center of the island, we can also infer that the island was home to livestock, providing additional resources. However, the island presented almost no evidence for built architecture, with only a single modern structure of about 17 square meters. Did Dionysia then ever support a permanent or even seasonal population? Or, rather, did its proximity to the nearby town of Drios on Paros, occupied from the Bronze Age, mean that it was never properly inhabited and instead a sort of satellite with additional arable land and pasturage? On Strongyllo, at least 6 large terrace systems were documented across the island, accounting for 35 hectares of arable land. We also documented 6 zones with structural remains, measuring some 750 square meters, alongside hints of architecture that are otherwise obscured. With these numbers, even if the complete terrace systems were not functioning simultaneously, we're presented with a much stronger case for a sustained population, a characteristic that is corroborated by the artifactual remains documented on the island for several periods. In addition to the interpretive contributions these data provide for discussions of land use and agricultural modification, post-fieldwork analyses encourage new questions to be asked about chronology. Consider the example of Dionysia again. In blue, we see the extent of walls identified in the field. Additional areas that were found in LiDAR are traced in yellow. These sections of pastoral enclosures are certainly related to the structure, but there's no evidence that shows whether they were contemporary or represent a later phase. We see similar examples of overlapping phases of construction on Ius Lukas, where an extensive terrace network has been identified. While many terraces were not seen on the ground, our LiDAR visualizations capture the topographic alterations they cause, allowing subsurface terraces to be extrapolated from the landscape change, from land level changes. The majority of terraces had originally been considered early modern or contemporary constructions. These newly identified features lead us to reassess the previous chronological understandings derived from the visible walls only. Here, a modern field wall runs over top multiple subterranean features, subsurface features. This wall segment, identical to other modern walls on the island, suggests that the terraces beneath predate modern cultivation. These buried terraces can be found throughout the western section of Ius Lukas. Previously considered a less cultivated and utilized part of the island, a new narrative of use now emerges. Similar to the example on Dionysia, as areas of chronologically distinct agricultural terracing become more evident, our understandings of the island's diachronic cultivation and alteration become more clear. In addition to these retrospective applications of the LiDAR data, this analysis also allows us to consider future LiDAR undertakings. Perhaps not surprisingly, there's a positive correlation between chronological recency and visibility in LiDAR data. Rates of particularly high relocation begin in the medieval period. Of the previously identified medieval, modern, and contemporary features, almost 90% were relocated quite easily in the LiDAR analysis. For older features, relocation rate drops considerably. Just over half, about 52% of the broad category of ancient features are relocated, while fewer than 42% of prehistoric features were visible. Note that this does not include features with ambiguous or multiple chronologies, such as the extensive terrace systems we've discussed. A final point on chronology concerns combining artifact collections from archaeological survey with LiDAR interpretation. Returning to the example of Kitriani, the most obvious modern features also have extensive artifact scatters from the modern period. These are the darker blue dots in the area of the Byzantine to modern church complex in the top grid. Modern material is also present amidst the terrace systems. Much earlier material is present in these systems too, however, especially from the classical Hellenistic and medieval periods. While only excavation can provide more detailed chronologies for such features, the association of surface artifacts is nevertheless suggestive of multi-period use and earlier construction than is typically assumed for such features. We can conclude that LiDAR provides significant value-added benefits to archaeological surveys, even after the fact, but that pedestrian survey remains essential for the identification and description of many types of features. At the same time, regional scale LiDAR coverage allows us to carry out new types of quantitative and qualitative geospatial analyses, especially with respect to large-scale landscape modifications and inter-island comparison. Obvious benefits aside, LiDAR is not a cure-all and does not replace other forms of remote sensing, especially at a small scale. We found it particularly useful at a sort of mesoscale or landscape scale of analysis, somewhere between identifying big sites and detailed architectural documentation. And this offers particularly data-rich opportunities for analysis. In closing, we note that all of the places we have presented in this paper are quite small. In aggregate, they offer a unique perspective on a particular type of environment across the Cycladic archipelago, a type of environment that's often considered marginal. This type of analysis, however, has not been applied to the larger inhabited islands of the Cyclades, which would offer new questions and new opportunities for comparison. Thank you.
Thanks so much, Alex. We are running beautifully ahead of schedule, which is wonderful. It means we'll have time both for discussion but also for plenty of coffee. We can open the floor for questions concerning our first four papers, and we have a microphone that will be passed amongst the audience. We have an opportunity for people online to put in their questions, and we have further microphones here if any of the original speakers would like to come up and join us here.
Yeah, why don't we just have the speakers from this first session come up so it's easy to ask questions.
Two of us are here.
Yeah.
So we need Katja and Sylvian.
And Will you should come up too.
Okay. Here, we have chairs and microphones and
questions.
Okay, I think is that Brendan? Yeah.
Thank you very much. I had a question for for Katja and your amazing presentation. Do you have Bronze Age remains sort of associated with the Elatia cemetery? And also, I guess what is the relationship of the survey zone that you showed us of classical Elatia to the Bronze Age remains?
Can you hear me? Yeah, we do have Bronze Age remains. Yes, we see in the LiDAR more clearly some remains of the necropolis, both in Elatia and in the area of Modi, where we knew that there were some Bronze Age graves excavated, but now we can see that there were even more graves in the area. The second question, I'm not sure whether I understood.
I'm sorry, it was more just my confusion of the distance and the relationship between the excavated Mycenaean cemetery of Elatia with the remains you showed us. Yeah.
With the Acropolis, okay. So the Alonaki necropolis, which you refer to, it is very close to the polis. It is in a quarry. It is related to a quarry, and there are even later graves around. Like it was, as you might well know, it was reused in late Hellenistic and Roman times, but there are even more graves starting from Hellenistic times around. So Alonaki is, if you remember the map, it is on the west of the Acropolis and of the city of Elatia.
If I can do one more question about the amazing find you showed at the end with the temple. Do you have plans to do more work around with what you're showing us is so impressive? So do you plan to ground truth it?
Yeah, sure. So the LiDAR helped us to find to induce a lot of new material. As you saw also the satellite image showed us much more. So of course we will go in depth and we will conduct further survey in the area.
Excellent. Was it really exciting to see that very large temple? Other questions in the audience? Oh, okay, excellent.
Hello, question for Alex. So I'm fascinated about the small Cycladic Islands project. I'm following you on social media. But my question is, so the whole project has been planned around LiDAR survey. Is all good old-fashioned photogrammetry, extraction for motion photogrammetry, has any space in these sort of applications? Or LiDAR is enough? We get some idea what's there. We can send the field teams there to deploy on the islands or on the feature. Is there any space for a little bit more now traditional approaches on remote sensing?
Yes, absolutely. We've been working with photogrammetry since the beginning of the project, and the nice thing about surveying very tiny islands is that they're small enough that we could, in the early days before we had the LiDAR data, the first thing we do is sort of arrive on the island, and either Evan or his partner in feature documentation, Hussein Ozturk, would fly the whole island with a drone and then create an orthophoto model for the entire island. And those are still very high resolution. And they are, and we still do this even with the LiDAR data in hand, because more over select areas, because we realize that it just picks up certain things that the LiDAR data doesn't, and also it's a higher resolution than we get with the plane-based aerial photos that we acquired with the LiDAR data as well. So yeah, that type of photogrammetry has had a place in the project since the beginning, and still does. And I'd say we do that on two different scales. One is the sort of island-wide scale, and the other is we create photogrammetric models of particular features and sites of interest. Giacomo?
Thank you. I have a question for you, actually. I'm actually now working on the quantification of the labor necessary for the construction of a terrace landscape in central Italy. And I think you have an amazing case because you have those small islands where you actually have already some estimate of demographic and so on. I was wondering if you actually have some intention to do that and for using LiDAR for labor, or I don't know. I was just curious because it's really an amazing case study, I think, to do something like that.
Yeah, absolutely. That's sort of our next step and kind of ultimate goal. We just haven't quite gotten that far yet. But, you know, we're looking forward to pulling in some ethnographic work about the construction of dry stone architecture to start, you know, quantifying what building terraces on this scale is like, and examining terraces versus field walls versus other types of systems. So right now we have this sort of rough metric of kind of total feature length, but eventually we want to get more into actual labor investment and this type of thing.
Well, if I can just comment as well on that, I think that terrace landscape is also very anthropological, interesting landscape, also not only because of the labor invested, but also in the decision behind a community that decides to build up a landscape like that, and because they probably had in mind to use that for at least a generation or so on, otherwise you won't do that as well. Well, that was it.
Yeah, I mean, the scale of it is really shocking, and that's exactly how I think about it too. Like, these are generational projects and generational investments.
Actually, I'm working in Oman, and actually there the tradition is actually creating the terrace. The family, when people get married, create the terrace, and then they wait a generation that they get the filling, and then they use that as a field system.
Oh,
for us, I think it's a very interesting ethnographic thing that they still do now. For it's as a gift, they just build the wall, and then they wait for the filling.
Very cool. Thank you. Other questions?
I think we have one online.
Oh, yes, we have a question online. Douglas Daniels asks, I was hoping each speaker could briefly mention which pieces of software they use to process the LiDAR data, proprietary or otherwise. I'll just say for my part that we're doing, well, the processing sort of happens in different stages. The initial processing was done by the company that acquired the data, Aerophoto, and they can speak more to that. And then, once the data comes to us as point clouds and DEMs for the DSM and DTM, at least for our project, we're doing most of our work in QGIS, which is open source software. I don't know if you guys want to add anything.
Same thing. You hear me? Same thing. As Alex just described, we use QGIS to produce all the different images you saw before. You can actually do it on ArcGIS Pro, but it's not as efficient, I think, and not as quick. QGIS is really great. You can produce with the same image, 10 different ones with options, and it works really well. Then we switch everything to ArcGIS Pro, but I think we have some kind of a better resolution in terms of just working with the transparency and producing neater maps. And then the other reason for doing all this work on ArcGIS Pro is that we can use it on the different apps that I showed. And that's really, I think that's a great help. Because as you can see, students are independent with their phones. They can just go and find them and comment them. And that really speeds up the entire process. So QGIS and then ArcGIS Pro in our case.
So it's the same thing for us, but we just stick with QGIS, and I was amazed by what are you doing with the ArcGIS.
Does anyone from the Aerophoto team want to just say what the software you were using on the initial end was?
Okay, so there are several software that are included from the initial process of the data. We will talk about most of them in our presentation, but let's say that the post-work after the initial, the one that you are also interested in, adding, of course, to QGIS, would be Global Mapper and TerraScan from TerraSolid for point cloud classification. It's a very important tool. And then there are some other minor tools. We even can use artificial intelligence now for some bigger project, but it's not ideal for this type of work. And some other minor software for just viewing portable free solutions like Fugro Viewer. Yeah, Wriggle is very important, but for the step before the actual deliverables, we will mention all the process of of such projects in our presentation. I don't know if you want to get a preview. Someone wants to leave, but yeah, we'll do a very thorough mention of this.
Thanks, Demis.
Can I just add something? Just very briefly on the software question, because I think it's a very important issue. I can only speak for myself, obviously, but I think this very nicely underlines the importance of collaborative research, especially when it comes to very complex processing of software. And so we have to be very aware of our expertise that we have as archaeologists, where our limits are, what we can do ourselves, what we cannot. And I think the LiDAR example is a very good example that shows that, okay, when it really comes to the detailed processing of the software, or the derivatives of that, we have to leave that to the experts. And when it comes really to the content-related processing of it, so the detection of features, whatever they may be, that has to be then the job of the archaeologist. Obviously, we have to go and ground truth that. And we had it in the project, obviously, with the satellite imagery as well, which was a huge effort, which our colleague Simon Hoffmann, with a lot of time, had to process. And I think, we have to turn the question to ourselves: what can we really achieve ourselves, and what do we have to outsource to the real software professionals? I think that's also, a question, at least that I have in my mind constantly when we're dealing with this. That's something I just wanted to add that.
Yeah, absolutely. Are there other questions? Oh, more on the online. So one question online from Zala Fashant is, do any of your institutions work collaboratively on any of these sites? I think I think some do and some don't. It depends on the kind of nature of the. I mean, we all work collaboratively in the sense that all archaeological research is somewhat collaborative. We have a very direct collaboration with the Small Cycladic Islands project between the Eretria and the Norwegian Institute and my own institution. I suppose it's different for all of us, right? Another question is, Susan Lupak says, hello everyone from down under. I'm curious because I'm about to start working with Aerophoto and Pericles on conducting LiDAR over the Perachora Peninsula. Katja said that the temple was not visualized by LiDAR. Is there some reason why that was not visible with LiDAR? Something that we can predict or at least understand?
Yeah, I'm sure, because the temple is hidden below the earth. So whatever is hidden below the earth, LiDAR is just, as you explained, Alex, it's just taking away the vegetation. So what is below the vegetation is above ground is visible through LiDAR, but nothing which is below ground.
Other questions or discussion topics from the audience? Yes.
Thank you. I'm one of the people in the audience, Alex, who really benefited from that 30-second overview of what LiDAR is, so thank you, and I'm here to learn just generally. One data point I noticed several of you mentioned, maybe all of you, is what type of aircraft was used to collect the data, and I'm wondering if that makes a difference.
I suppose the Aerophoto team will talk about this too, but do you want to say something briefly about?
Yeah, hello from me. My name's Chris Bouchougis. I'm from the team of Aerophoto, actually. There are plenty of aircrafts or UAV or UA systems or rotorcrafts that can be used with onboard LiDAR sensors. The point here is whether we have to map a wide area, a specific area, and how it can be cost efficient. Of course, the selection of aircraft has to do with the point density and whether we have to use UAV to, let's say, capture a specific object like a temple, increasing the density of the point cloud in that context, but actually raising the time that the UAV has to be aloft capturing the area. So actually, we have the sweet spot with fixed-wing aircrafts flying at approximately 3,000 to 5,000 feet AGL, giving densities more than 35 to 40 points per square meter, which can be very valuable for your research.
Thank you, Christos.
Maybe we could go to coffee break.
Sure, yeah. Go.
Why don't we, at this stage, break for a coffee and further discussion? May I just remind everyone to be back in place at about 5 after 11, so we can begin right away at 11:10. Thanks so much to all the speakers this morning.
LiDAR presentations. Thanks to all of our first speakers. We're moving on now to the second session where our first paper is by Nevis and Michael Donius of the University of Vienna, and they are talking about terrestrial and underwater use of ALS, ALB in Mediterranean landscapes. And this will be presented on Zoom, so I'll turn it over there now.
So good morning from Vienna. Thank you for the invitation and the opportunity to present our work online. We will show some results from Croatia and briefly discuss two topics. Firstly, it's about the geography and archaeology of the Croatian coast and why we actually need LiDAR survey. And secondly, we will show some results that illustrate why it is important for us to overcome the boundary between the land and the sea, and how the LiDAR survey, based in combination with other methods, allows us to analyze Croatian landscapes. The landscapes of Croatian coast are a little similar to those of Greece. They are quite diverse, as the coast is over 1,500 kilometers long. The large parts of the coast and many islands are affected by two extremes. On one hand, they are deserted landscapes, with or without vegetation, where archaeological work is nearly impossible due to the dense vegetation or advanced erosion. On the other hand, they are often overbuilt landscapes, which have been created primarily for the needs of the tourist industry since the 1960s. They also make archaeological work quite difficult. The tourist infrastructure has also a devastating effect on the research of the 500 years of Roman rule, as the architecture and maritime infrastructure are located directly on the coast. And due to the general rise in sea level, around 1.5 meters in the northern Adriatic since Roman times, Roman villas, especially large villa estates from the 1st and 2nd century, are today partly submerged. So for a long time we had to accept these circumstances and study terrestrial and underwater relicts separately. However, a combination of many different methods can quickly become complicated and very expensive. And that was one of the reasons why we carried out our first test LiDAR survey already 12 years ago, in a hope that it will work just as well as in the European continental Europe and to overcome the border between land and the sea. Over time, we have worked in several regions, but at the beginning we focused on the northern Adriatic and Cres-Lošinj archipelago. The islands are archaeologically rather unexplored, which is certainly related to the difficult working conditions due to dense vegetation. For us, however, the vegetation was the first reason for choosing the islands as a case study area, as the LiDAR had to be tested in a difficult region, and this was about the most difficult landscape we could find. Cres and Lošinj offer large areas of maquis and other secondary vegetation, as agriculture has been largely abandoned on the islands since the end of the Second World War. The other reason was the great clarity of the seawater in the region. Bathymetry requires a green scanner that can penetrate the water. The calmer the water, the clearer the water, and the calmer the water, the better the results. This means that during the data acquisition flight, there should be no rain and no wind, as on the morning of the data acquisition on March 2012. A few words about data processing. My co-author, Michael Doneus, handles the difficult task of the data processing and can also answer your questions about this topic later. LiDAR data supplied by companies, at least the data that we get from Austrian companies which fly for us in Croatia, needs to be reprocessed for archaeological purposes. Most importantly, a reclassification of the point cloud to derive terrain models better suitable for archaeology is usually advisable. Also, instead of a digital terrain model, the use of digital feature model proved to be best for our purposes. A feature model is interpolated from points representing both ground and buildings, or in our case, dry stone walls. It may even be necessary to produce varying classifications adapted to different environments, vegetation regimes, or research questions. Here's just one example showing how different filters lead to the disappearance of dry stone walls on the left side, while showing agricultural terraces in more clarity. The verification of the results above and below the water surface was often difficult, but always carried out. And perhaps it should also be mentioned that the most interesting results from recent years, such as the medieval parcelling shown here, are not classified as archaeological sites. as they do not contain architecture or finds. About the results, we use, of course, LiDAR survey data for mapping archaeological relics that were previously hidden under vegetation and seawater. Here's an example from the Colonna Bay in Istria, where submerged architecture and maritime infrastructure are preserved. Bathymetry provides good results down to a depth of 10 meters, which is quite sufficient for Roman period, and allows not only the documentation of the relics, but also the visualization of today's relief underwater. However, we use the LiDAR data much more often in the context of the landscape-based approach, documenting and interpreting all relics, including those of agriculture or military history, because the greatest strength, in our opinion, of archaeological prospection is probably its ability to reveal relics from human activity over large areas without judging them in terms of archaeological significance and thereby excluding them from further research. This also means that we always need to be prepared for surprises, which brings me to our two current projects. We have used original test area of the islands Ceres and Lausanne for a new project with a focus on the ancient town of Ossor, marked with the blue circle, as Ossor was a regional town center from the Iron Age until the 15th century. The ILS or the LiDAR is playing an important role in the current project, and the area was surveyed again in March 23, so that around 70 square kilometers are currently available for project purposes. There are 5 major themes in the project, and the LiDAR is particularly important for issues of land use outside the city wall and for the landscape context. The reconstruction of the landscape context, including relative sea level changes, the reconstruction of paleo coastlines, and underwater sedimentation processes, are essential for the understanding of a maritime city like Ossor. In a long time, they also form a basis for the understanding of strategic and military role of the town and his role in the maritime and cultural long-range trade networks. A combination of LiDAR, terrestrial and underwater geophysical prospection and marine coring are planned for this task and are in a moment work in progress. Understanding land use outside the city gates requires other method combinations. Here you can see what the ILS data reveals beneath the vegetation on the island of Ceres. On the one hand, you can see geological structures because it is a karst landscape, which is why the relief is characterized by sinkholes. But you can also see a complex pattern of dry stone walls, which really fit in between these karst holes. And the dry stone walls have shaped the island's surface probably since the prehistoric times. We have already analyzed a small part of the terraces, and with the help of old plans and historical aerials, field visits and harrismetric composer, we were able to work out a relative chronological sequence and identify different uses of the terraces, for example, for the cultivation of olive trees and vine. What we did not expect, however, were long linear features that are clearly visible in the ILS visualization and marked with a red oval on the left upper corner. Without ILS data, however, we would have not been able to recognize them in the field as part of the former human land use. You can see the photograph on the right side. Due to the regular distances over length of more than 10 kilometers and a spatial connection with the Roman city of Ossor, we believe that we have detected evidence of Roman surveying and land division. We then looked for ways to get an absolute chronological dating. Since OSL dating works so well on the agricultural terraces in the Mediterranean, we tried the method at Ossor just 5 days ago, working on the premise that Roman dry stone walls have not been moved since they were built about 2000 years ago, and the sediments underneath were not exposed to sunlight at any later time. At the moment, we know that the method has been successful, but the exact absolute dating will not be known for next few months. The presumed Roman land survey of the territory of Municipium Ossor was quite a surprise, as Roman land division is normally expected on the mainland, next to the large cities like Colonia Pula, northwest of Oslo. Centuriation was a political statement and was realized in Istria after the land was annexed to Roman Italy at the 1st century before Christ. We believe, however, that the system of dry stone walls was used on a large scale not only for land surveying, but also for Roman agriculture. And this brings us to the Medulin Bay. In the south of Istria, approximately 24 square kilometers of land and underwater terrain was scanned around the bay, some 10 kilometers south of the town of Pula, during the EU project Archaeological Park Visual. At the same time, high-resolution aerial photographs of the region were taken, on which hundreds of pits are visible, recognizable as vegetation marks or as eroded pits in the vegetation-free strip along the sea. We were not the first to discover them, but it took high-resolution aerial photographs to reveal the full extent. All in all, it appears that pits were systematically laid out in the same size and at the same distance from each other over an area of at least 13 hectares. A different group of land use relics are shallow linear banks in grid-shaped layout, which were discovered in the ILS data, in the same area, but are not visible in aerial photographs. The banks preserved in macro relief are roughly just 30 centimeters high. They form a regular grid with square cells of almost 40 meter width. It is most likely that they represent heavily leveled remains of dry stone walls, which is also the reason why the banks are up to 4 meter wide. In the terrain, the banks are hardly visible with the naked eye, and there is also no archaeological material. So looking at grid-shaped parcelling and pits together, we can see some similarities. In addition to the common orientation, it is apparent that they overlap and have the same measurement units. They lie stratigraphically below all other structures on the Prematura Peninsula. There are no recognizable connections with the modern land use, but enough parallels that allow Roman dating or even an interpretation as planting pits and protective walls of large-scale tree nurseries, or for example lemon groves, of the 1st and 2nd century AD. There are several reasons for such an interpretation, and one of them is Villa Maritima in Verige Bay on the island of Brioni, which lies about 20 kilometers north of Medulin Bay. It is the largest Roman residence on the Croatian coast of that time, and was excavated already at the beginning of the 20th century. Here is a small overview over the excavation results with the main house highlighted. Luckily, the area to the east of the villa has neither been excavated nor affected by modern landscape management. So we were able to identify the grid-shaped parcelling of the same shape and size as in Medulin Bay. And similar to relics from Medulin Bay, the orientation is adapted to the topographic context, in this case to the orientation of the Roman residence. Also, the banks of the grids in Verige Bay, obviously eroded dry stone walls here too, have the same dimensions as those on Prematura. So this is actually the first physical evidence for the large-scale Roman agriculture in Istria. And these new discoveries show how effective LiDAR can be in the Croatian coastal landscapes. The fact that LiDAR enables a landscape-based approach seems particularly important to us, as this is one of the great strengths of archaeological prospection. The categorization of the landscape into on and off sites becomes, through the LiDAR data, unnecessary, as human activities are not concentrated on individual sites but have left the traces everywhere, and we can find them if we look for them. Thank you.
Our second paper in this session will be Issues of Representation in LiDAR-Based Landscape Archaeology in Mediterranean Contexts, and it will be delivered by Giacomo Fontana of University College London.
Yeah, thank you so much. First of all, thank you so much for inviting me. I'm very happy to be here today, and I will talk about Italy, actually, but a methodological perspective, therefore I hope it will be useful also in Greece and in wider Mediterranean context. Today, the presentation actually focuses on issues when we do large-scale landscape studies, very large scale, over 10,000 square kilometers. And some observation that I developed within my project, after analyzing a lot of those kilometers and seeing a lot of time maps that we do in LiDARs that do not really tackle with the issue that we have in different visualization, different type of visibility of archaeological features across large landscapes. The work actually is derived from my PhD that I finished in December at UCL, and actually the overall project was aimed at tracing Samnite socio-political organization through hill forts. Samnite is a pre-Roman society of south-central Italy, like Hellenistic period, just to give you an idea. The approach was a quantitative approach based on a multi-scale analysis that first created a new and representative data set of hill fort sites across the entirety of south-central Italy, to then investigate the monumentality and labor involved in the construction of the fortification of those sites through statistics and other methods, and then taking the labor together with other variables in order to study the variability that we have between the entire range of hill forts and different categories and different trajectories toward urbanization, non-urbanization, and so on. Everything then was studied through geospatial statistics, point process model, in order to understand the socio-environmental interactions between the sites and the landscape, and therefore also ultimately trace forms of socio-political organization. Everything, as we already saw today, is quite important, was backed up by a lot of empirical validation. Therefore, I work on 6 hill forts in the field doing intensive survey, and also a large program of ground routing. The first part, this presentation will focus on the first part, the issue of creating a new and representative data set that was suitable to develop spatial statistical analysis. And this project actually was called the Ancient Hill Fort Survey. And why it was necessary? Because, survey the mountains is quite tricky. We already saw that this morning a little bit. The Samnite is a society of the Apennine area, therefore a mountainous area that had been largely neglected by archaeological research, that had been focusing on coastal and plain regions. Something that is quite a common phenomenon in Mediterranean context, and particularly in Italy. As such, we didn't have actually a good idea of how the distribution of sites was in this mountain landscape, both due to the large and heavily forest areas that are here, and also due to the difficulties in navigating this landscape. To address this, LiDAR was very useful. To address this, what I did was doing a large-scale LiDAR analysis over 25,000 square kilometers, for which 15,000 square kilometers of LiDAR data were available. For the project, I used the LiDAR data of the Italian government. It's a low-resolution LiDAR data of 1 meter, quite problematic, but it was possible actually to start from the raw point cloud and then processing it for archaeological purposes, and then develop visualization. Specifically, I used the VAT method, the VAT method, and so on. All the methodological part is actually in the paper that you can see there. Therefore, if you want, we can discuss about that later. What is important is that a few thousands of archaeological sites came out, or better, possible archaeological sites that were quite consistent, let's say. Of those, 315 possible hill forts. And just to give you an idea, this is how a typical Italian hill forts look like, or at least in Samnium. We have the fortifications visible on LiDAR. They can be very different how they visualize. And in the field, we can go from simple earthen ramparts up to more monumental polygonal walls. And those are, for instance, walls of a site that was not known. And you can understand already how LiDAR was useful to trace a 5 meter, up to 5 meter tall monumental site that was not known. What is important is that the study highlighted 2 main biases in the previous legacy data set. On one end, there was a modern land use and recovery bias. Therefore, the large majority, actually half, was under broadleaf forest, but around 2/3 of the site were detected in areas under vegetation, under some form of vegetation. And again, you see another example of a site that was quite overgrown, but still quite monumental, with polygonal walls. And therefore, a bias on how research was done, a bias on the visibility of the archaeological record. At the same time, it came clear also another bias. There was a regional research tradition. Therefore, research focused on the Tyrrhenian part of Italy, in the area overlooking Campania, but actually largely neglect the more mountainous region facing the Adriatic, the Molise and Apulia. And as a matter of fact, we thought there were no actually hill fort sites in Apulia, for instance. The systematic LiDAR actually allowed the identification of many of those also in Apulia, really changing the perspective that we have, the historical narrative. And I think this is interesting because we are in Italy, an area that has been largely studied. It's not an explored area. Therefore, being able to identify so much in an area already studied was quite interesting from a methodological perspective. What we did next was ground truthing. We visited 145 sites on the ground, collecting materials, collecting mapping and so on, and creating actually a consistent data set. And we did 22 control samples and 123 suspected hillforts, of which 16 were possible reinterpretation. They were actually possible to reinterpret as hillforts thanks to LiDAR, sites that were known due to dispersal of material, but which fortification disappeared in the landscape. But actually LiDAR was pointing out for that. And you can see an example of one of those sites there where you maybe see the circular line that is actually a very clear wall on LiDAR. And then 107 possible sites, of which 99 were verified as a new archaeological sites. Of those, 70 were hillforts and 45 samnites. What is interesting is that from a database that was quite fragmentary, we moved from 146 to 206 sites with 40% increase. But most importantly, we had actually new typology of sites that we didn't know actually, new typology of hillforts scattered across the landscape, and also new distributions in areas that were considered as lacking this typology of site. This data set actually now is quite interesting because I think we test for intra-observer biases, a lot of testing, and we're actually using that now as a training data set for AI-based classifier, deep learning classifiers of hillfort sites on LiDAR that hopefully will be applicable also in other regions outside Italy. The issue here is that we had also thousands more other archaeological sites. And those are tricky because the visibility of those sites is very different. While we have hillforts, they have a lot of monumentality. We can always trace them more or less in LiDAR. The other site was a little bit more tricky as a situation. I will not go in detail on all the different typology of site identified. I will just use 3 case studies to show you a little bit where I am heading with this example. The first were platform farms. Yeah, you can see those are classic farms, traditionally Roman farms, built on platform areas, fortified or not. There's a bit of debate, but yeah, in platform farms. What was interesting is that we noticed in the LiDAR a tendency to not see this typology of feature in specific areas. That was mainly actually low altitudes, where the vegetation was a bit more dense. At the same time, those two sites, you can see that they look quite different in the image, in the LiDAR image. And also on the ground, we go from a much monumental type of fortification of retenement wall to something much more ephemeral. What is interesting is that those two sites are just 2 kilometers from one another, in the same type of altitude, in the same type of topographical setting, and the same type of vegetation. And this a little bit already brings up an issue on how to visualize those sites on LiDAR data, because if we have such a similar situation, topographical and so on, the sites still, they look very different, with one that is much more marked than the other. Similarly, we had a lot of settlement agglomerates. And here, we're talking with a couple of houses to fully fledged villages. And here again, LiDAR, even though we were using the same LiDAR data in similar vegetation, similar topography, similar sites, the visibility of the archaeological remains was very different from one another, even though the preservation in the field was quite similar. And we go from villages, again, on the right of the image, where you can see the single houses and you can map the single houses, to other situations where you can actually see very well that there is something because you have the fortifications around. But if we had only the southern part of the site outside the fortification, it would have been much more tricky to figure out there was a medieval village or maybe something different. And this, again, a little bit of an issue on how those sites are visible in LiDAR data that have been processed in the same way, in the exact same way. And then transhumance road. This is the last example. While the other ones are more like local, punctual features, we also had a lot of landscape features, like terracing, of course, a lot of that, but also transhumance road. Those are long-distance roads that were present across the Apennines and many parts of the Mediterranean. What is interesting is that LiDAR allowed us to remap them. Therefore, starting from the historical account and maybe some historical maps of 50, 100 years ago, remap them and actually find the most plausible real track in the landscape to the high resolution of the LiDAR. At the same time, we were able to identify new transhumance roads that were not known in the regions, like the one you can see here. But what is interesting, and this I think is important to point out, is that, again, those features, they look very different, not only among different transhumance roads, but also in the same path of the same transhumance road, as you can see in the image. And this will highlight another issue of visibility where the same feature can appear, disappear, depending on the vegetation and so on. In this specific case, the entire transhumance road was not possible to map. What we did was mapping the stretches that we could see and then extrapolate from that based on viscous path modeling and the most likely routes. Small stretches, but still it highlighted how, on the local level, the route could completely disappear, while on the regional scale, it was still there. Now, we are having, we did this study. We have a lot of large data sets of sites, but the question is, are those really equally representative among them? Can we use this data set in the same manner? Can we use the data set of field forts as we use the one of platform farms? Because the issue is that the same typology of feature appears very differently across different landscapes when they are so large. We are talking about 25,000 square kilometers, even when we use the same data in the same topographical setting and same vegetational canopy. And here there is a little bit of an issue of local versus regional, and therefore what we can see locally, it can add to local catalogs, but it doesn't necessarily produce a data that is useful for large geospatial statistics. And this was actually the aim of the project, develop spatial statistics and understand spatial patternings. That is ultimately, I think, the aim of many LiDAR projects that we have today. The issue is that we have to be a little bit careful how we use them. In the specific, I think sampling area is very useful. This is the most simple example you can see, is just using the LiDAR coverage as a sample area for the as an analytical window for all the spatial statistics. Therefore, instead of using the entire research area, just use the LiDAR coverage, and when you do statistics, just correct for the edge effect. The sampling is very simple that we use for 50 years in pedestrian survey. When we do transect, we just use the transect to do spatial statistics. But with LiDAR, it's something that still now, there are some papers that came out quite recently in Antiquity, a special issue about the also LiDAR, and that's not done. And I think it's a little bit tricky because LiDAR actually gave us this great opportunity to use that and to develop this kind of sampling areas that can actually reinforce and support the spatial statistics that we developed. For the project specifically, what we are working with is differential sample areas for different types of archaeological features. As such, hill forts, the distribution of hill forts is considered representative when we consider the LiDAR coverage. And the same for Consumers Road, because they are such a regional scale feature that even if we miss the local data, we can still trace the general distribution. Farms and settlements, among many others, are a bit more tricky. And what we are working now is trying to leverage the property of the LiDAR to actually work with it and create much more detailed sample areas to do the analysis. On one end, with farms, we're working with just a threshold, LiDAR coverage, and a threshold with above certain altitudes. While with the settlements, for instance, where we actually lack a clear patterning that we can observe, like normally, we are using confidence map. For the idea to just give a value of the quality of the LiDAR locally, and then actually use that one when we do spatial statistics. This is, it's nothing new. We've been using sample areas for so long in archaeology, but I think it's important to stress a little bit that there is a great potential in using this type of approach also with LiDAR, because there is this tendency, I think, in archaeological LiDAR that, it's an amazing tool. It's very clear that it's amazing and is extremely effective in producing new data sets that are really unprecedented. At the same time, there are a lot of pitfalls, and I think it's useful to try to discuss them and try to talk about them in order to a little bit try to further also the methodological take. And this is actually one of the things that we're also discussing in the European Archaeological Council guideline for the use of LiDAR. I'm one of the people in the committee, and the guideline will come out in a few months, and hopefully they will provide, of course it's a guideline, but they will provide a general standard for the use of LiDAR in archaeology in Europe in general. Therefore, hopefully it will be useful for the one of you that are just starting now with LiDAR, and maybe, just to pick up a little bit, which is the idea behind. With this one, I would like to conclude, and there is actually a few papers coming out about LiDAR and the integration of LiDAR with other methodology, one in Antiquity in a few months, and one in archaeological prospection. And I'm happy to discuss later about the project and other things if you want. Thank you so much.
Two papers. I guess I'll start by saying that we put these papers together here and group them because obviously they're from contexts outside of Greece. And I think that that's important to talk about since the use of LiDAR in archaeology is relatively new in Greece, whereas it has a much longer history, especially in Italy. And Nevis and Michael have been working with it for quite some time on a developmental level as well. So you know, a question that I would ask from the outset is if, you know, you are seeing this, you the speakers are seeing obvious differences between LiDAR use in Italy and LiDAR use in Croatia and LiDAR use in Greek contexts, and are there particular contributions or perspectives that you think would be helpful to apply in Greek contexts? We should have Giacomo come up here, by the way.
I can start if you agree with this question.
Sure. There should be a microphone.
So what we saw so far about this is great. Sorry? Oh, can you use it? Better? Yeah. Now, it's very interesting because one of the main issues that we have in Italy is that the LiDAR has been provided by the government. Therefore, in a sense, what the government provides is already the DEM, and then you do the things from there. And that actually created a little bit of laziness in many Italian archaeologists that just use the DEM and that applies series of visualizations. But the DEM is problematic because, as we discussed already, it's a DEM that's not being created for archaeology, but for geology, for they count out everything. Therefore, in a sense, in my case, I had to process the point cloud. It was quite tedious, but as you know, the good thing that you have in Greece is that in a way that having to commission some LiDAR, you don't go in this pitfall. And that is great because everything I saw is really like processing for archaeology, and it's something that is really quite great, I think, to see. For in that sense, it's really good. Of course, maybe you lack the large-scale coverage that we can have in Italy now. That is still very low resolution, therefore quite, it poses some limits, let's say. I don't know if
I don't know if Nevis is on and Michael, and if you want to say anything to that initial question.
Yeah, if I might give a context comment. I first thought it is different, but after seeing these presentations here, I don't see there's too much difference, of course, how LiDAR is used in Greece and in our area. The only thing I would like to comment on the lectures also before is that I think that in many cases, and that's what we try to do, you see stratification in the urban LiDAR scanning. So if two lines are intersecting, you usually can see which is older and which is younger. And I think this information is extremely valuable, and together with historic maps and OSL dating, I think it's possible to give some chronology into the landscape. And I think this is certainly an important step forward.
Questions from the audience or general comments? Oh, yes.
I changed because I needed the plug. A question for the survey in Italy. You said that you mapped new transhumance roads. You said that you mapped new transhumance roads. What's the correct? How do you know that these are actually transhumance roads? Because you said for the other ones that you had the historical accounts, you had the information, so you found them on the field. That's great. How do you know the new ones are actually also transhumans and not from some other area? Can you differentiate that from the later data?
Yeah, it's mainly the length, the width, sorry, because they are always like 30 to 50 meter wide, and therefore they are just those large, flat, roads that are very, very large. Therefore, 50 meter is it cannot be Roman, at least in my area. Therefore, for that reason, and also because they have a tendency when they go in the slope to kind of have a series of steps. In the image, it was a little bit, you could see some kind of steps, I don't know how to say. There's just like a couple of ramparts to facilitate. Therefore, in that sense, we are in a region in the Apennines. By exclusion, they cannot be Roman, and there are those very wide landscape liver features, and also because the new one, they have the same type of morphology of the old one, of the one that we know by historical, and therefore, by comparison, we can associate the new one also to that.
They're not paved, right?
No. It's just like grass. It's just grass, just flat strips of grass that are quite, from my early images, sometimes are visible, but a lot of time they kind of get lost in the field systems because maybe they are, in time. And LiDAR actually is very effective in detecting them. I think it's interesting because viability through LiDAR, of course, is always difficult to date. And also those are difficult to date, but it's very peculiar as a typology of feature, at least. It's quite interesting.
Are there any of these transhumance routes paved, generally speaking, or are all grass in Italy?
No, in the Apennines,
in the Apennines, yeah.
No, they are all like just grass. For there is nothing paved.
I have more questions on that because I'm doing something similar in northern Greece, but I'm going to talk to you later. Okay. Thank you very much.
Yeah, thank you for your paper. Actually, I wanted to follow up. It's not a question. I just wanted to follow up with a comment. You started your paper with a very, I felt, with a great methodological point. It's just extensive type survey. We have the same thing in Greece, and I know for decades, extensive type survey was considered to be a bit, chaotic, random, and where do you start? You just depend on where you can go in the maquis or the vegetation, and you kind of neglect slopes and mountains. And Alex and I have been discussing this for over a decade, and we tried different methods, even walking in lines in the maquis 20 meters apart and trying to find something. I think now with LiDAR we have a strategy for exploring all these areas on slopes, and these are dominant in the Mediterranean landscape. And I think more and more now we'll be able to include these areas, thanks to LiDAR, in the global, survey areas. And this is really super promising, I think. I think it provides a method, a way to enter these areas with ground truthing. But I think this is really new, and it opens up huge opportunities for fieldwork and understanding these landscapes. So no comment, just a quick comment on what you said.
No, it really makes sense also because I think a lot of times those landscapes are quite relic landscapes. Therefore, they're actually very promising also to develop, like archaeology, archaeobotany. They're amazing. They're like very preserved because they were so inaccessible. With also Chezeaux, Garcia Sanchez, we actually work on point sampling methods to do like intensive but systematic survey under dense vegetation. Therefore, like what we did, is of course ground truthing, but also kind of systematic in order to try to compare that to normal pedestrian survey. It's tricky, it's very difficult because it's so time consuming, but I think it's amazing, it's very promising. During my PhD, I visited 145 sites. It was 4 months and a half of travel in the forest for never again, but it's really like, it's amazing, I think.
Yes, thank you also from me for this wonderful talk. At some point you mentioned very briefly the AI classifiers, that you were experimenting with AI classifiers. And I was wondering if you could share your experience with that, or if you have any yet, and because it reminds me very much in the early days of GIS with predictive modeling and everything. And if your experience, but also perhaps if you have any warnings that you might want to express to it.
Okay, just a bit of background. I did my master in Leiden University about machine learning in Arabia. Therefore I had a background on that one. When I started this PhD, I dropped AI because I thought it was much more effective visual interpretation for the specific landscape, and also because, as I said, a lot of new typology of sites came out that we didn't know. Therefore, sites that we couldn't actually train an AI classifier with. Therefore, I think now I'm working again on that, but I'm working very much on the edge, on the fence, because it's something that can be promising. But I really don't know if, there are so many pitfalls with archaeological, we know that archaeological data is extremely fragmentary and problematic, and is, also on LiDAR, it can appear so differently. Therefore, it's very tricky. I think AI has a lot of potential to automate things. Like there is the work actually of Michael Doneus with AI for automatic classification, right? That is something that I think with local automatic classification, that I think is something that can automate a process that is otherwise very laborious. For interpretation, I think I'm still visual interpretation is still the best. Therefore, I'm a little bit skeptical, but still trying. That is my position. I don't know if it helps.
If I may add to this, I think one of the problems with AI in this kind of interpretation is that most examples at the moment are really confined to easy structures like mounds, round structures. And I think one of the big problems at the moment is that we have only very little labeled training data sets. We would need much more labeled data in order to efficiently use AI. This will come in the future, but at the moment, I think we are not right there.
But also, I think the issue is that I'm really wonder when we will have enough good training data sets. That's the tricky part, because there are some, like, you know, there are maybe sites that are so specific to specific regions, and you simply don't have the number of those. Like the Ilfords, now I have 200 Ilfords, but it's a ridiculous amount compared to what a training data set should look like. Therefore, it's still a little bit, and they're also so different from one another that is not a good training data set. Therefore, I don't know, it's an interesting field for sure, I think.
Yeah, exactly. It will need new ideas. How to generate this data.
I have sort of a related question, a more detailed technical question that maybe Michael and Nevis and Giacomo can weigh in on, since you certainly know more about it than me. I can imagine, as Michael said, AI being better at recognizing certain types of features like mounds or circular features or that type of thing. I would guess it has a more difficult time with linear features, not because linear features are difficult to recognize, but because it can be hard to differentiate anthropogenic linear signatures from natural linear signatures, which are, you know, very widespread also. So I wonder, is there an opportunity for say, training AI systems based on the recognition of intersections? That, for example, the grid pattern that Nevis presented, you would think that that type of thing would be highly recognizable. But I don't know if you have done any work about this or have any broad thoughts on this. I would love your insights.
If I can start, for the Hilfords, for instance, what we are working with is recognizing the entire Hilford. Therefore, instead of the linear feature itself, the linear feature is belonging to a circuit. And that is actually quite effective in many ways, because it's showing that it's able to go beyond a little bit just recognizing the linear feature. But we are also actually working directly on the point of the cloud point, not with the DM. Because of course, with the DM, you already have a lot of issues, and then from 3D, you go to 3.5, then you fly to 2D. Therefore, we are trying to work on the tree and try to, to use as much as possible the third dimension. That is what I think, for the linear feature, for instance, it can be the difference in Ilfords, because, you have a rampart that go up for a hill and something that enclose. In that sense. Then I don't know about other linear features. I think now they've been doing a lot of work with field systems, but like always recognizing the entire field system more than the linear component. Therefore, it's a little bit like object-based in a way, detection. You detect the entire object instead of a single component. Instead, burials, I think, they are easier because, it's a burial. It's the single component is also the single object in a way.
Yeah, I think it's also the same for round objects, because there are so many possibilities for a round object. It can be only a pile of sand or a pile of branches. Anyway, I think at the moment the main contribution of AI is to search really big areas, big LiDAR scans to direct you to potential sites, and they've looked there. With linear feature, I think Leiden and Carsten Lambers and his teams, they made, and I think you have been there anyway also, Giacomo, they make a good contribution also towards field systems. And this is very promising what they do, involving also citizen science to get training data sets. So I think they are specifically very good in the way forward.
Thank you. Any other questions from the audience? Should we move on?
I think we could, if we have nothing in line. All right, we're keeping to very good time. This is wonderful. We'll press on to our next paper, which is delivered by Tibor Tallis of University of Lausanne. Using LiDAR in geomorphological mapping, the case of Amarynthos River Valley, UB of Greece.
Hi everyone. So yes, I speak about the use of LiDAR in geomorphology and in landscape evolution study. So I'm not an archaeologist, I'm an hydrologist, so it's going to be a bit different from all the nice... you don't? Okay, sorry. Okay. It's going to be a bit different from all the nice talk we had this morning. So for this talk, I'll begin just by giving you a bit of context about our study area. And then I'll dive into first method, so how I draw this geomorphical map. I'll show you some results of this. And then we'll speak about another method that I find really interesting and which is complementary to a classic geomorphical map, which is landscape evolution modeling. And after that, I'll show you some preliminary results about this modeling. So for the context, we are working on the Evia Island, more precisely in the catchment of the Sarndopotamus, which has an elevation comprised between 0 and more than 1,100 meters. Here I put you a plot of the slopes of the catchment, just to show you a bit, so you can have a first glimpse at the different processes going on. And of course, this plot was also done with LiDAR data. It's a quite vast area, so you can understand why it's interesting to use airborne LiDAR for this kind of study. And it's also an area with a rich archaeological context. So well, you could argue that's the case of a lot of area in this country, but here it's really nice because it has been occupied since the early Neolithic, and it's also there, as Sylvian explained before that the sanctuary of Artemis Amarisia was found a few years ago. So my job in this project is to understand the evolution of the landscape and the interaction of the different processes which participate to build the actual landscape. So let's begin with the geomorphical mapping. The classic method in geomorphology is to cross different data coming from field observation, topographic and geologic maps, and also orthophotos. But obviously, LiDAR-based DM is a great substitute to a topographic map, and for a lot of reasons, but first, obviously for its resolution, but we'll speak about other reasons later. And I did some manual mapping because we had a lot of anthropic impact in this area. So automatic mapping was probably will probably have a lot of error because of all these roads that we have. So just to show you a bit how I did, so I just crossed a LiDAR-based DM with orthophotos. So we can see here we have these terraces, and we see here on the photos that it's just olive trees. So it can be classified, for example, here as farming terraces. So why it is so great to use a LiDAR-based DM for this kind of work? Well, first, as we mentioned before, LiDAR allows filtering, which is really interesting, at least for me, to have a precise knowledge of the shapes of the rivers and gullies. So this is great to draw a map, but this is also really important for the hydrological modeling, obviously. And it's also nice to filter the buildings, because in this landscape we have a lot of big alluvial finds which are covered by cities, and to remove the cities allows better understanding of the shape and volume of the alluvial finds. Well, in the contrary, it also allows the observation of human impacts, so as the terraces and the roads and the bridges. But in my opinion, the main point of using this kind of data is that we can play with the resolution. Because in geomorphology, one of the big topics is that we have different kind of processes creating different shapes at different scales. So it's not always easy to see everything. For example, if you have a big alluvial fan with small processes going on it, depending at the scale you're working, you see different processes. And with this kind of DM, you can see everything. You just have to play with the resolution, which is great. Oops. So, but it also, of course, have some limitation. Obviously, it cannot be used alone to draw a map. You still need to go on the field. You still need some orthophotos. And some features can be tricky to differentiate. So here it depends a bit the habit you have of looking at LiDAR, but here I think it's quite hard to see the difference between bedrock and alluvial fan, alluvial deposit if you're not used to, and you see that the orthophotos doesn't help at all. So you still have to go on the field and verify by yourself that it is indeed alluvial deposit. And the main problem with all kind of remote sensing technique is the confirmation bias, in my opinion at least. For example, for me, who was trained in the Alps, when I see something like that, I see a moraine, which it's completely impossible. We did some modeling, we look at the literature, and we have been on site, it's just bedrock. But for me, it really looks like a moraine, and it's just bedrock who was eroded by surface water with this kind of moraine-like shape. So it's something to be careful about. So concerning the geomorphical mapping, so LiDAR are obviously an incredible tool, much better than topographical maps, but they should not be used alone and always with fieldwork and orthophotos. So concerning the results, so this is the catchment we are working in, so we can see that it's quite simple from a geomorphical point of view. We mainly have water as transport and erosion agent. We have these big alluvial fans here at the west and the alluvial deposit of the Sarandopotamus here. Which is really interesting in my opinion, is that we have a lot of erosion at the east and the north. We can see here on the DM that the water produces much more erosion here, and this corresponds exactly to the schist area. So it means that the geology has a great control of the landscape. And we also took some course in the floodplain to verify that indeed we have more sediment supply from the schist area, and to be even more sure of the behavior of this catchment, we are doing some modeling. So landscape evolution modeling, as I said, it's a great tool to increase the understanding of the actual geomorphology of the area. Why? Because we're not just looking at the actual situation, but we are really reproducing the processes that lead to what we have today. So for that, we obviously need a precise DM, which we have, and even a bit too precise sometimes, because as you can see here, it creates some artificial sinks. This is the river and some bridges. This is a road, which creates artificial sinks that we don't want, obviously. If we want to modelize water flow, we don't want to have lakes here. So we have to remove manually those bridges. So I'm using a software which is called Lapsus, which was developed by Schurz and colleagues. And, well, I don't want to spend too much time on this, but just to give you an idea of how the model is working, just for the erosion deposition due to water overflow. So there are two main variables. There's the transport capacity and the sediment transport rate. The transport capacity depends on the water flow and of the difference of altitude between two neighboring cells, and the transport rate depends on the transport capacity and on the sediment already in transport, and from a different variable describing the eruptability, which is D, and the sediment settlement T, depending if the sediment in transport are smaller than the capacity or bigger, meaning that here we have erosion and here we have deposition. Concerning the sinks management, this model is quite simple. It means that it considers things as being natural phenomena, so it just fills them with water and sediment. So for the results of this modeling, so here you can see some areas of erosion, and of course it's the mountains, and we have some deposition in the floodplain. So why is it important to use the LiDAR for this kind of modeling? First of all, because it's really precise, and it limits the butterfly effect, because we plan to run this model for thousands of years, so a small difference in river path will lead probably to big difference in the final results. But it also has some limitations, and the main one is that this is really nice, but it's explained the future, the erosion from now on. So it could be cool if you want to build a house close to the river and you want to see if you get flood, but that's not what we want to know. So we need a paleodem, and to do that, well, it's a lot of inversion process, and for it to be realistic, we need a lot of control data. And obviously, the main control data is the actual DM, which is really precise, so we know what we're reaching for, what we're looking for, but we also took some course to provide even more control, so we know well when we had more floods, and yeah, that's all. So, yeah, to conclude, well, in a paleoenvironmental reconstruction, LiDAR are amazing tools, even if they cannot be used alone. So, in my opinion, the huge value of this tool is that you have the overview of the catchment, of the big phenomena going on, but you still can assess the details. And that's really the main point of it. And in the same time, as I said, you can perform some great hydraulical modeling because you know exactly where the water is flowing, thanks to the filtering. Thank you for your attention.
Thank you. The next presentation, I believe, will be a team-based presentation by Themis Spornas, Christos Boutsoukis, and Nikos Dalampis. And this is aerial survey with LiDAR and photogrammetric sensors in a feature-rich Mediterranean environment.
So, hello everyone. First of all, to begin with, I would like to thank you, Ms. Bonna Wescoat, as a director of American School of Classical Studies, and Alex Knodell for this invitation to this workshop. Actually, all you deserve a great credit towards the preservation of our cultural heritage. And since our data has helped a lot for those efforts. Today's presentation, it is going to be a threefold one, as you described. The team consisting of 5 and more people in aerophoto, from pilots to aviation specialists, to airborne data engineers, electrical and computer engineers, and surveying and rural engineers as well. Originally, company is operating from 1992. 1 year ago, we celebrated 30 years of operating and aerial survey capturing of data. Our head offices are based in Thessaloniki and Athens in Greece, and also in Ostendel Canton in Switzerland, with our partners of Swiss Flight Services. We are operating as a geospatial data processing company and aerial survey, showing expertise in acquisition, analysis, mapping, and delivery of geospatial information and services. We are operating all along Europe and the Balkans, and also in Greece, with a possibility of the team to be agile enough for multiple relocations around Europe. So we are servicing a broad market of sectors, providing data to land administration, cadastre, for transportation and infrastructure purposes, as-built models, of course for archaeology, documenting and digitization, for forestry and natural disaster management. But our basic element, of course, is our just culture and our team spirit. We incorporate a no-blame culture. We are all care for all our responsibilities. And of course, our cornerstone is our partners. Our support never ends upon the delivery of the data, so we are open for multiple feedback during all along your research efforts. To continue, here is a list of major projects that we have done with our partners in the last 5 and 6 years. In the dark green, you can see cells of archaeological field works and data that we have provided for you, and most of them are here today. And once again, thank you very much. Also, the last but not least is Samothrace and with Emory and Texas Tech University, and also Miss Susan from Australia that is going to capture data also around Perahora with Miss Lolos and Donati. So we are operating a fleet of 9 aircrafts and UAS, now under testing capabilities. We have a dual sensor integration with Rigl LMS VQ1562-S with phase 1 camera, RGB wavelengths, also with a Planix from Timple AV610 and IMU57, and also combined with photogrammetric sensor Ultracam Eagle Mark III. So both active and passive photogrammetric sensors on our aircrafts. As an example, it is a Cessna Caravan EX. So now Themis is going to be with us to continue with the calibration report and the more technicalities. Thank you.
Thank you, Christos. So let's say that while hardware is important to be up to date, it's equally crucial to keep scanner and camera calibration up to date in order to achieve an accurate, high quality result without artifacts, which is important to avoid this project, like you mentioned before, some false anomalies that may occur with such issues. In this brief flowchart outlining the LiDAR scanning process, we are guiding you through a standard project completion. You can, the project consists of 3 discrete parts. It's flight preparation, and acquisition of data, point cloud processing, and imagery processing. For an acquisition request, at first we need, of course, the area of interest to be specified from the partner. Secondly, the deliverables must be described and discussed. This is a two-way procedure. We need your feedback and your help with this. And of course, special requests that might take, we might need to take into consideration. We will now provide with some examples for such issues. This is an islet in Cyclades with a very steep terrain in this area, which might result in data gaps. An effective solution in this case would be to add an extra cross strip vertical to the main flight lines in order to minimize this problem. Another situation that usually occurs is the request for higher penetration of densely vegetated areas like this one. We can deal with it by doubling the side overlap and thus the density of the coverage up to 60% and avoid such issues. The scanning parameters will then be calculated and optimized using Wrigley's three-parameter module. In addition to the technical related settings, in this step, we ensure that the laser safety limitations are being respected. There are some important parameters that we should take into account for this, for such missions. The flight plan will then be finalized using top-of-flight software. This is a versatile solution, allowing us to spatially implement the customer's requirements and minimize the overall mission cost. Additionally, a large variety of a priori quality control tools is available. This sums up the flight preparation step. The data acquisition is now ready to take place. This is an aircraft trajectory example from one of our missions in Luxembourg. Accurate position calculation combined with a scanner calibration that we mentioned before is crucial for the overall data quality. After the flight, we are performing a quick quality check of the acquired data using Wrigley's reprocess platform. We ensure that our partners' requirements are being met. The final step of georeferencing procedure is strip adjustment. De facto, every strip is captured with a time difference, and thus it's nearly impossible for the scans to be absolutely identical. Sorry for that. As you can see here, Wrigley's reprocess platform has a very robust module that can eliminate strip misalignments, and thus we can avoid the creation of unwanted artifacts, false anomalies, and provide us with an increased clarity result. My colleague Nikos will continue with a description of classification procedure and deliverables.
Hello, everyone. My name is Nikos Dalambis. I'm a surveyor engineer in Aerophoto. And we're going to see things regarding the point cloud classification. And we're going to present the main steps we follow in order to achieve the best possible result. So we're going to see the ground classification, then the vegetation, buildings, and finally, non-ground archaeological features objects classification. Let's see them in more detail. First, we have the ground classification. It's a very important step of the procedure because based on this classification, vegetation, buildings, and other structures are going to follow. The main parameters, our algorithm, we use TerraScan as a software for this classification. The main parameters the algorithm use for the automated way is the terrain angle, the iteration angle, and the iteration distance. When we have smooth terrain, this algorithm works well and gives correct results, but in this case, we see in the slide, we have a very steep terrain with many hills, and the algorithm with the automated way creates holes in the ground that these holes need to be corrected. This happens with a semi-automated way. We rerun the algorithm with different parameters only to the areas where the holes are created because the second time we run the algorithm, it's very aggressive and it may give us points on the ground that are incorrect, such as low bushes, low structures. So we perform manual corrections in order to remove those points from the ground. You see the result in the second image in this slide. After the ground vegetation, we do the vegetation. The ground classification, we do the vegetation classification. The parameter here is the height of the points from the ground. Depending on the client's requirements, we classify them as low, medium, and high vegetation. In this class, we may find objects such as wires, fences, cars, maybe. All these objects may be reclassified in another class if it is asked. And after the vegetation, we have the buildings classification. We use the points from high vegetation, which are 2 meters or higher from the ground. And some parameters here are a parameter called Z-tolerance, which is the maximum elevation difference the points belonging to a roof, a building roof, may have, and the minimum building size, and others. And finally, we go to the object type classification that concerns non-ground archaeological features or objects. This process, we use the help of the DSM, the DTM, and the orthomap in order to find areas where we can locate these structures. And this procedure involves examining the vertical profile sections of the point cloud to detect and classify our points of interest. As we see a vertical profile section in the right side of the slide. This procedure, the engineer's experience in understanding the morphology of the terrain, how the vegetation points are captured, and some archaeological characteristics plays an important role here for the classification. And in this stage of the process, we want and we encourage the interaction with our partners and our clients, because we can provide to them DSM and DTM of the area really quick after the data acquisition, and when they see them and study them, they can indicate to us areas with archaeological interest in order to find and classify structures there. One more useful parameter that helps us identify and classify these objects and structures is the intensity value that the points of the point cloud have. This intensity value, if it is combined with color information, as we see in the left image on the slide, they can indicate us a wall, as we see in the right image, especially when these structures are intersected with vegetation or other objects. In this slide, we choose to highlight how LiDAR can view under dense vegetation, which is very important. This is a case from Vilos Island in Cyclades. We see in the top view the vegetation and the structures classes. We remove the vegetation, we see how the wall continues under the vegetation. And in the right side of this slide, we can see two images showing us how the wall is captured. We can measure its elevation, we can see its shape, and this wall is under dense medium vegetation. In the next example, which is from Samothrace, it's a forest area here, and we see how the wall is captured beneath dense high vegetation, as we see in the right side of the images of this slide. Next, we're going to talk about the products, the raster products of a mission, of a LiDAR survey. In this image, we can see, We can see DTM, DSM, orthomap, and the classified point cloud from Yaros in Kyklades. This is a prison in Yaros. And let's see them in more detail. First, we have the orthomap. In LiDAR surveys, we capture aerial photographs, high-resolution aerial photographs, RGB, so we can create a detailed orthomap. We know orthomap is a very useful tool for locating areas with archaeological interest and for verifying the correct classification of the point cloud. The first raster that we can produce really quick after the data acquisition is the digital surface model. We use all the points of the point cloud except the noise, elevation values, the grid method. We use the global mapper to create these rasters. The grid method, we take the maximum elevation value in a grid. Vertical units are meters. And the grid spacing bounds depends on our partners or our clients' requirements. And the visualization type here is a slope shader. We can see the slope changes. After the DSM, we produce the DTM. You can see the difference here. Only the ground points are, the data input are only the ground points. Again, the other parameters are the same, except the grid method. We use the minimum elevation value here for the production of the DTM, slope shader visualization. And then we have the digital feature model, which points that are classified as ground and those that are classified in our client's interest class, such as archaeological structures. We use them here. It's a very useful raster because it depicts the topography of the structure to the environment, and they can help us locate other areas with archaeological interest. That's all. And finally, we choose to show you two other visualization tabs. It's the Atlas shader, which provides us elevation information, allowing us to recognize flat areas, small hills, and a slope shader with a difference plating mode, which depicts the ground in black color and the objects on it on white. In my opinion, I prefer this visualization from this because I can recognize better shapes and artifacts. That's all from me. Christos will do the epilogue. Thank you.
So, thank you, Nikos. To conclude with and some food for thought and where we are heading next. Why airborne? As Ms. Knodell said, we are not a Panagia. We are trying to combine the multiple remote sensing methods, also from satellite, from UAV, from georadars, geomagnetic. But of course, the efficiency that we are providing allows the accessibility, the mapping, the classification, identification, and the documentation that it's of utmost important for you. Our cornerstone, that as I mentioned before, is we can provide high precision, high quality, and high density in timely performance while meeting the American standards for remote sensing and photogrammetry, which are revised in the previous year. But of course, we need cross-domain expertise and know-how. That's why our workflow is not a black box. So we are more than welcome to have partner interventions all along this processing flow, while proceeding with our results, which of course are enhanced visualization of DTM for feature extractions, DFM interpolation, and the fusion of multiple data sources and integrations. Now some challenges that maybe we have already faced in the past, but nowadays are hot enough. Of course, the targeted archaeological structures are difficult to be learned and ruled, like our previous discussion, so the use of ML algorithms and convolution neural networks is a challenge nowadays. We are doing steps in that direction, but of course for a wide area and for automating the building identification and structures. Because we need the manual reclassifications that are still present, and the reason is that, of course, we have to retain as much standing artifacts as possible for your research. Only, I think, one presentation today was for bathymetry LiDAR and the hydroarchaeological mapping of areas in the Mediterranean. But of course, since our waters are does not have much turbidity and they are crystal clear, we have the capability with the latest Rigel scanner VQ880, I think, to incorporate and execute such projects. And last but not least, it's a challenge also the generation and the reconstruction of the 3D objects that they are missing from ancient structures using generative adversarial networks and natural language processing such as GPT nowadays. As a reminder, we are not operating only in Greece, but our offices are also based close to Lausanne. So the areas of mapping are all around Europe. We are open to hit us a question and inquiry, specialdata.aerophoto.gr. So that's all for us. Thank you very much again. And also Ms. Bonna, thank you. Do you have any questions, or maybe in the next presentation?
Yeah, we can do the next presentation, and then we'll do a Q&A session, general Q&A session. So our next presentation is by Brody Manquin, and I hope Brody's online, because we're running a little bit early, and it's, I think, 5:30 in the morning, his time. This poor guy. But he may be, yeah, I don't know, Konstantinos, is Brody there? Oh, there he is. Hi, Brody.
Hear me?
So Brody is presenting a paper called Visualization, Vectorization, and Verification, Open Source LiDAR Methods for Archaeological Prospection and Accuracy Assessment in Mediterranean Shrublands. And this is also using data from the Small Cycladic Islands project, and in collaboration with Dimitris Athanasoulis, myself, and Tom Garrison at Texas.
Yeah, can you hear me?
Yes.
Okay. I'm sharing my screen. Yeah, so as mentioned, this is visualization, vectorization, and verification. And this is conducted as research, part of my master's thesis research at the University of Texas at Austin. As mentioned, it's part of the Small Cycladic Islands project, LiDAR research that for LiDAR acquired for these islands in orange around the major islands of Andros, Tinos, Mykonos, and Amarynthos. And the background for this research is really drawing out of work in Maya archaeology, where a lot of LiDAR survey work has been pioneered. With the increasing public availability and cheaper availability of LiDAR in Europe, and the increasing desire for large landscape surveys as opposed to single site analyses, it was we thought to include some innovations from my research, which has longer experience with landscape surveys. And one of the key takeaways that was published in this paper by Garrison et al. 2023 was that accuracy assessment standards and measures of feature classification accuracy became really important later down the line from the early stages of the research. So they found that a lot of early research that had different measures of feature classification accuracy led to different abilities to compare regions for archaeological features. So when coming into the Small Cycladic Islands project and thinking about how to incorporate some of these accuracy assessment lessons from my archaeology, we wanted to include the accuracy assessment from the get-go. And two of the questions that we had was one, more generally, was how accurate is the manual LiDAR classification, but then more specifically, what types of features will be most inaccurate, or what types of inaccuracies will there be. So our first hypothesis was that these linear features, after taking a look at the data, these linear features really popped out as having a possibility for more confusion with false positives, because it was easy to confuse terracing with all these other linear features that were popping up in the DEMs. And then two, does underlying data quality significantly impact manual classification? As we know, the data quality differs depending on vegetation, depending on slope, and we wanted to understand if this data quality had an impact on feature identification error. And my hypothesis was that this would be inversely correlated, that is, that higher data quality would lead to less error. As mentioned in other presentations, this is mostly based off of LiDAR point clouds that have been converted into DEMs, digital service models, and then also digital feature models. This is just kind of some of the data sources that we had. Most of this was done in open source technology. Some of the later work is done with ArcGIS Pro, but mostly this was done in QGIS with R and some other software packaging. So as mentioned, we created, besides the digital elevation model and digital surface model, we created the digital feature model drawn from other work in the field to include the archaeological features in our base elevation models. And as the person doing the manual classification, I found this very useful for my work. This is a comparison of the DSM, DTM, and DFM, and the DFM really pops out compared to, has the features pop out much more compared to the DTM, and has less noise compared to the digital surface model. Then when the models were created, we had a systematized manual classification protocol that was adapted from the pedestrian survey technique from previous field seasons that didn't have LiDAR. And all features were drawn as line vectors in QGIS. Some of the feature types also had polygons drawn for them. But for a lot of the error analysis, therefore, I stuck to the line features just because that included every feature that we had. Included in the classification process was whether this was a positive or negative feature, what feature type it appeared, whether it was a wall, terrace, structure, etc. And some other categories that were more useful for pedestrian survey, like the chronology, which can be difficult to determine from the LiDAR alone. We also added a category for the verification protocol. We verified all of the features using two field methods. One was a features team that documented each feature marked in the classification process. This was done via QField, which you could see on the left-hand side, where each vector that was drawn was imported and into the QField app and visited by somebody on our team and determined to be a false positive or a true positive. Obviously, this method doesn't allow for the detection of false negatives or misidentifications. So it was really useful to be doing this side by side with more traditional pedestrian survey, which was able to detect the false negative. The results from this process for accuracy standards are presented here. So this is only presenting feature types that have more than 50 classifications, but we do have numbers for the other feature types. But these ones have a large enough sample size to be broadly representative. And what we see is that the F1 score is a general measure of accuracy, and especially terrace walls and then structures are very accurate. There was less accuracy in our walls category. And looking into some of the specifics of overall accuracy, the precision, which is sensitive to false positives, and the recall, which is sensitive to false negatives, we could see a few patterns. For one, the terrace walls category was very accurate in detecting all of the terraces. So the recall was nearly 99%, which means that almost all of the true terraces out there that we found in the field were detected in the LiDAR classification. However, there was relatively a higher number of false positives in this category. And this, based on fieldwork, we could determine this was most likely from these linear bedrock features, which you can see here, that in the classification process were marked as terraces because they share a similar linear profile, but were in fact just bedrock. The opposite pattern is visible in the structures category, which we think is due to these relatively small structures, oftentimes that are built into the landscape, like this one, which in the LiDAR you can see here is pretty indistinguishable from some of the other bedrock features around it. So there's a higher number of false negatives in this category, which lowered the recall compared to the precision. So some of these key takeaways have been mentioned. Another thing to mention is that the walls category shows a low accuracy in many ways due to our classification methods. So terraces and structures all include walls. So the walls category ended up being a little bit more of a generic catch-all category for walls that were less certain. That's just how the manual classification process ended up shaking out, and it resulted in lower accuracy standards. But after doing this sort of reflective work on where error seemed to come in after manual classification, after field verification, we also wanted to look at possible sources of error statistically. So one of the possible error sources is that analyst, which isn't really testable here because it was mostly a single analyst job. If we had multiple analysts running in parallel, we could possibly test that. So what we did instead was to also look at the data quality. So this is using a confidence map, which is a measure from 1 to 6 category. It's not a continuous raster that is generated from the Open LiDAR toolbox. And it takes into account ground point density, low vegetation density, and slope to generate these categorical values of LiDAR data quality underlying a digital feature model. And as you can see on the right, there's a range of data quality on this one island with the features laid over it. To extract the confidence map values at each point, the linear features were buffered about a ½ meter to capture the archaeological feature itself, which are mostly made out of these walls. And then the CM values were extracted at points along the feature. And then also a dummy variable of false, or of true negatives rather, was also created to measure points that were not marked as archaeological features and truly were not archaeological features, just to get their confidence values as well. And then ran a logit regression model, which is a binary regression model. So it's a true positive or a true negative is a 1, and a false positive, false negative is a 0. And running this model only with the confidence values, there is some measure of significance, but it's not a very clear relationship, and the R-squared is relatively low. So the intercept, which represents confidence value of 1, has a high association with successful classifications, and the only one with a negative association is this middling value of 3. So that wasn't really showing that much interesting, and it seemed like there was a lot of other elements explaining the error. So including the feature type into this type of regression model pulled out some more detail. So this is a big data table, but what's really important are these still the confidence values once feature type is accounted for. And it does show a positive relationship starting from CM value 2 to 6. There's a general increase in the odds of a successful classification with higher data quality. However, it seems like it's largely driven by the inclusion of the feature type classification. We had one feature type classification in particular, which was called area of interest, that is included in this intercept value on the screen. And that seems to be the large driver of error, because this was an error class, a feature classification that was highly uncertain, purposely so. It was sort of a feature classification that was meant to be checked in the field as maybe there's something here, but likely not. And so some reflections on this process. Why this accuracy assessment matters. It's really helpful for comparison. Future work, I think, looking at this research would be able to tell if you just downloaded the feature database from this small Cycladic Islands project based on the LiDAR classification. Having this error information helps determine, any comparative analyses between projects to say this project has identified this amount of walls, but these walls category have this amount of uncertainty. Being able to factor that in helps understand regional comparisons, which is especially important when intensive field verification is not possible. We were able to identify each feature in the field, but sometimes that's not going to be possible. So having some spatial awareness of where error lies in the landscape can be helpful for both comparison and also planning future research into refining methods and conducting field verification. If I had to do this again, I think we would tinker with some of the feature classifications and also account for some of those polygon features, which I was not able to include in this. And that would be able to include size and height in some of these regression models as well. And yeah, thank you for your time.
We now have the opportunity to have questions and discussion regarding our last two papers, and perhaps the Aerophoto team would be willing to come up and join us. And Brody, don't leave.
And Tibor.
And, okay, and Tibor. Oh, that's right. We have
three for.
Sorry. Any questions from the floor? John Papadopoulos.
Thank you all. This is really a question for Tibor, but perhaps also for the colleagues from Aerophoto. Determining geomorphological changes through time and the evolution of a landscape is really, really fundamental to archaeology. It's one of the most important things, and it's oftentimes one of the most difficult things to determine. And I was interested in Tibor's catchment area because one of the characteristics of it was that it was so stable. One of the biggest problems we had at the Ancient Methone archaeological project was a really, really dynamic landscape. A landscape where you've got the confluence of three major rivers, the Axios, the Louvias, the Aliakmon. The Aliakmon is the longest river that's totally within Greece. And you've also got the Gallikos a little further north. In the 1920s, they had to move the delta of the Axios because the writing was on the wall that Thessaloniki would no longer be a port city. It would be completely landlocked. And added to that is also the erosion on the coastline. We have Bronze Age into early Iron Age tumba sites. And there's one just south of Makrigelos, north of ancient Pydna, which 3/4 of it has collapsed into the Thermaic Gulf. So one of the things we did was using an aerial photograph of our area from 1945, using military maps and then doing our own LiDAR survey, which we began in 2014, we were actually able to map 7 different coastlines since 1945. 7. And every year we go back, it gets worse. We're probably up to about 13 now, if we were doing this on a yearly basis. So how do you deal with a landscape that is really changing dynamically, like before your very eyes?
I guess in this kind of situation, the best option would be just to do some course. And so you have like every steps. And if you do a lot of course, then you can have a global overview of your site, probably.
We did a lot of cores, and it really made it much more complex because oftentimes, we had a full Holocene sequence, for example, in the cores, but the Anthropocene levels really did affect a lot of the pre-existing levels in a very critical way.
Well, in any case, I wouldn't go into like landscape evolution modeling. If it's so active, I guess it's gonna be wrong, because a model by definition, it's always wrong. You just want to make it as close to the reality as possible. And if the reality is really seems a bit chaotic as you're describing, I mean, it's super hard to have a realistic model in this kind of situation. So I wouldn't do that in any case. And the best is still the coring, because at least you have the data which is correct. And if it's complex, well, it's great. It means that you have an interesting area with a complex sedimentary dynamic. It should be really interesting to work on it. But yeah, that's
maybe not modeling, but maybe simulation. Maybe like agent-based modeling as a simulation tool to see different landscape approaches. Try to simulate different events, and maybe that could be interesting. But it's very, computationally, very complex. Yeah, no, it's just like, it's the idea to see what happened with different events and see maybe something your data fit more or less. Therefore, it's more like an exploratory tool instead of a solution. Because
yes, I completely agree that it's clearly something you can do. Just explore some hypothesis and see if it corresponds to what you see. Yeah, indeed.
Yeah, adding to this, actually,
by definition, our acquisition is going to be time-specific. So in that phenomena, maybe a revision of it should help. But then the cost is going to be rise. But such methods that's described for simulation is going to help also.
I think Tom Brogan.
Hello, yeah, Tom Brogan. How do you, when an archaeological team, this is a question for the Aerophoto team, how do you, when a project approaches you, how do you begin the conversation of costs so that they know how to attempt to raise money? So I think the first time I heard a LiDAR presentation was here at the school, maybe 10 years ago. And I asked at the time, I think it was like 60 or 75,000 euros for 1 or 2 days. And I know it's been coming down, and you mentioned that it was coming down, and there are some ways to mitigate the cost. But how do you begin the conversation? I'm not trying to put you on the spot, but it must be an obvious topic.
Yeah. Actually, the LiDAR is a high-cost remote sensing methodology, of course. When it comes to a request, first of all, the area, and if some areas are going to be some tens of square kilometers, then we prepare a cluster of them, and we organize them flew together with other requests. And then comes the point density, the strip side laps, and depending on the terrain, also if some chrome strips are going to plot it also. Do you want to add something?
Yeah, and another issue that we face is we normally suggest the minimum data possible in order to do your job in a good way. We don't make a hobby of flying too many strips or whatever. If you can work with from higher level with lower side lap or whatever, it's the first thing that we propose to do. What do you want to do with your data? What do you want to achieve? What is the spatial resolution that you need for your request? Yeah. So this is a way that we also treat the partners initially.
So what would be the minimum and maximum costs of these projects? I can ask it a different way.
I work for a foundation that pays for projects. So I have a real interest.
Yeah, it's a more theoretical, I guess, one, not an actual, but since those requests are kind of expanding in some tens of square kilometers, and not so many archaeological areas are for wide area mapping, like Italy, of course, some old data. Then you can say like 30, 40 or 20,000 euros up to, let's say, some tens of thousands. So, yeah, it depends on the request, and of course, also because you are updating and upgrading our equipment, new cameras, new aircrafts, and also the software. Of course, it's a time of discussion. Yeah.
And of course, another parameter would be how urgently you want the data to be acquired. If you ask for an acquisition the next week, there might be, yeah, it's if we can wait and combine maybe projects, it would be ideal for everyone, single mobilization of the aircraft.
I actually have a question for Brody. if you're there, you mentioned that feature type was one of the areas where you had error, and Samothrace is a brand new project, and you could even begin to make those decisions. What, based on your experience, what would you say you would, in a new project that you're just starting, do differently?
Well, I think I would, keeping feature classifications types either somewhat more simple or at least tiered is something that I've considered. So as mentioned, one of the categories of high error were both the walls category and the area of interest. I think I would keep the area of interest. I think there is value in having an uncertain classification type for manual if feature verification is possible. I think, however, simplifying some of the categories between walls and structures, for example, and having some sort of tiered system where a first go around is just to identify these are walls around a feature, and then doing interpretation of, is this a terrace system, is this enclosure walls, etc. Just having that walls category was increased it showed more error than I think is necessary. So I think just having kind of a more streamlined approach, and then also maybe more of a tiered or subjecting these categories to a secondary classification, perhaps, where the features, once identified as walls, are then interpreted, could just be a little more of a clean process, as opposed to what was done in the project I presented, where the typologies were assigned as the initial classification happened.
Thank you.
That's actually precisely what we are stressing in the European guidelines, that there is a difference between a vectorialization, therefore identifying there is something and drawing it, and interpretation. Because of course it's two different things. Therefore, when you assess your interpretation, you're not actually necessarily assessing if you draw the line in the right spot. And that is actually something I'm really stressing a lot in those guidelines. And also the issue of, also try to evaluate the analyst in a way. With we are proposing. We are offering inter-observer and intra-observer test for biases. That would be just like you start with the interpretation, and then after you go back and you reinterpret what you already did. At the same time, you work with teams, therefore multiple interpreters, and that's actually quite easy to organize with fieldwork, because always, you always have students that are interested in that. But yeah, it's a lot of, this is a very technical also maybe issue, but they actually get a lot of repercussions, I think, at the end when you actually say, this is a site, this is not, or, yeah.
Yeah, thank you, Brody. I also wanted to piggyback off Bonna's question. So what I really enjoyed most about your presentation was when you started saying, if I was to do this again, I would tinker with it. And you really didn't get into the tinkering. And all I want to say is, I would urge you to publish that tinkering, because that is what's really important in our field.
Thanks. I'll keep that in mind.
I have a question for the folks up on the stage here. So Tibor's a geomorphologist, and the aerophoto team, you're working with people in many different disciplines. So I wonder if you have any kind of insights coming from other disciplines that you think would be useful for archaeologists to think about, based on what you've been seeing in your work directly with archaeologists, but also what you've been seeing in your work with remote sensing data from other fields. Are there things that we're not doing that other people are that would be useful for us?
It's a bit hard to answer that because I'm not aware of the complete state of the art of the archaeology, but I'm convinced that in all the remote sensing techniques that have been developed for earth and environmental science, there is a lot of potential for archaeology in general, especially landscape archaeology. So all this satellite imagery, now they're getting much more precise, and you can play with different wavelengths, make up a lot of different information. So that's something that could be interesting. Not with Landsat, because Landsat's not enough precise in terms of spatial resolution, but with some new kind of satellites, perhaps.
Yeah, that is, Alex, thank you for this question. That's exactly what we're thinking all the time while being here. For each presentation is adding something to our general thought. For example, Brody's presentation was, that is what we were just discussing, was, is of great importance for us to get such a good feedback regarding the classification of features, of archaeological features. And of course, it also adds another subject of discussion between us and our partners in the future. Should we do this classification and target for more precision maybe? Do you want the recall to be higher, like Brody presented? Yeah, it's a foot. We have a lot of things to process after that, so I can't give you a very relevant and significant answer right now, but we will share whatever we have in mind with you.
Yeah, and also lately we are been operating for corridor mapping projects for train, for electricity wires, market sector like this, transportation also. I think archaeology wants also applications having to do with AR headsets and virtual fly-through inside open space remnants of archaeological features, or also the discussion we had about how we can explore and facilitate ML techniques for feature identification, especially in wide area, large-scale mapping. And, but apart from this, still much initiative is taken from the rest of the presentations. Yeah.
Again, to follow up on what you said, Alex, I mean, what is great to have, well, we have Tibor on the team for the survey. It has been a huge plus for us because he also field walks with us. And I know that in field survey, I mean, people have worked with geomorphologists for decades. But when you get a model like the one he showed today, which is a dynamic erosion model, and then you start plugging in all the layers with surface densities of sherds and tiles and structures, and it becomes really incredible. You get into a more complex understanding of your landscape evolution and where human, build stuff or don't. And I think using LiDAR in the future, you'll be able to produce more models of that sort and to compare it with the archaeological surface data we get.
Can I add something very briefly? Coming back to funding. It really is a huge issue, especially for example, I have a background in smaller projects. So it's not only the funding for the 20,000, 30,000 for the flight itself. You also have to think about personnel costs, etc. So 20,000 euros is more or less, say, a pre-doc for 2 years who has to process everything. And for example, Stefan Bienert, who has processed all the LiDAR data for the Kephissos Valley project, can tell a tale about that. So this is also, so it's at least have to double the cost for especially smaller projects. And that brings me back to the question of what happened, or how did people do surveys before LiDAR? there's, of course, a huge value in doing survey also without LiDAR, but LiDAR has that very, very incredibly valuable added value. So I just wanted to add that aspect when you think about funding or applying for funding.
Just with respect to issues of funding and when you make the decision to pursue LiDAR is when it's urgent, and you really can't get the product you need or want in any other way. I think that's a fair assessment of value.
Finally, I want to add that our social responsibility in the company, our photo is in high standards. Multiple data sets have been provided already in National Technical University of Athens in the laboratory of remote sensing, also for the Old Coast area in ancient Corinthia to the Ministry of Culture. So we have done many steps contributing to limit down possible high costs, especially back in the first steps of LiDAR in archaeology, because I remember the first attempts for LiDAR capturing archaeology is dated back in around 2000. So, yeah.
There's one question online about ground verification of LiDAR data, especially in densely forested areas that are difficult to access. I think, well, various people could probably speak to this. Yeah, it can be difficult, right? If you see an anomaly in an area that's particularly tough to get to, but I think most of the time, you will be able to kind of confirm or disconfirm if that anomaly is archaeological or not. I don't know if anyone else would like to speak to that, Brody, or I'm sure Tom Garrison could say a lot about that. I see that he's on the Zoom right now.
Yeah, hi, good morning. Yeah, I'm coming to you from the Maya world where we only deal with forested situations for ground truthing, and so it is just really sort of part and parcel of the work. And I also just wanted to piggyback on the issue of cost as someone that's, has 7,000 square kilometers of LiDAR data. Yeah, it's extremely expensive. And in our case, we ended up, going with a private source to fund that amount of coverage. And in the end, the cost of it per square kilometer ended up being way cheaper in the long run than doing, manual ground survey. But it's a very different environment from you guys. And I think it's exactly what Bonna was saying, where it comes down to, what you need and what your project goals are. And yes, it's expensive as a single payment, but when you think of it as the money saved over years of trying to assess a landscape, it can add quite a bit of value. So, for us, we were able to cover in a single day of LiDAR what it had taken us 8 years to map. And so, it's sort of zooming out your budget to a multi-year scale and, trying to think about, and, I heard the comment about small projects, and yeah, it's tough. It's just not there yet, I think. Italy's got a lot of national coverage. I know in the other project Brody and I are on with Sue Alcock over there, I think we got our LiDAR for €2 because it had already been acquired by the government for other purposes. And so, sometimes it's a question of waiting for some sort of national program, and they're coming everywhere. So, there's no easy answer to the issue of cost, but I can say in the Maya lowlands, we've had the great success through finding private sourcing for the funding, which introduces some other issues.
I think that it's a great way to end our morning sessions, and we will reconvene this afternoon at 2:45 for our afternoon papers. The speakers who would like to join us in Loring Hall for lunch are welcome to do so. And those of you in the audience, we look forward to seeing you just before 2:45 to resume our afternoon sessions. Thanks so much to all the speakers and good questions this morning, and look forward to this afternoon.
If you're interested in mankind, if you're interested in society and how it should function, then you would do well to study the past.
There are certain moments in history where the human spirit just kind of bubbles up and goes.
Whether we're talking about democracy, art, philosophy, it doesn't really matter what the subject is. It begins in Greece.
The school acts as a gateway to not just a different place, but sometimes a different time.
We bring Greece's past to life to really help shape the world's tomorrow. Preserving, protecting, promoting all aspects of Hellenism from ancient times till today. And we've been doing it for 135 years.
There were educated businessmen, lawyers, financiers who truly believed that the study of the Greek past was of a great good for the general public and that it needed to be advanced. We exist by virtue of the philanthropic efforts of individuals like them. We had pioneer women archaeologists leading research teams in Greece. We are international, multicultural, and intercontinental in terms of the networks of collaborations that are carried out.
We're a consortium of almost 200 leading academic institutions in the United States, all of whom support the school.
We draw from that membership, whether in Texas or Hawaii or Massachusetts or Florida, to bring people here.
In a place that has, 3 world-class libraries within 100 meters. When you're in Athens, it feels like the center of the universe.
I would rather do this here at Athens than anywhere else because the major monuments are here and it's very inspiring.
You feel what a contemporary Greek would have felt standing on the Acropolis with the Parthenon right next to you.
What you're doing is creating the next generation. They're all going to be high school teachers, they're going to be professors, they're going to be scholars, and they are the ones who are going to pass on our understanding of antiquity. We have the pieces that were necessary for the working of the democracy, and those are the people of Athens speaking to you directly over thousands of years.
We have about 1.5 million items digitized.
All of that information can really be disseminated to new audiences, to the global classroom.
The American School gives you a place where you can kind of explore your own passions in a way. You have people who are so passionate about the material, they create tools to study it. When you see what can be done at a single site, then you realize, well, why can't we do this across all of Greece and have all of Greece accessible in that way?
There's hardly a part of Greece that some American school project is not operated in.
We've got 300,000 catalogued objects to educate our students, but also for research so that we can come up with better interpretations. We're also developing ways to present this all to the public. So we're creating a management plan to create an archaeological and ecological park, educational programs for children in the States, which we translate into Greek so that students in Greece can also use those same materials.
The collection is about the history of Greek genius through the ages. It is very important to find ways in which to attract people, to make them understand that there is value in the old books and secrets that are hidden in there.
Our mission is essentially a rescue mission. We're creating time capsules for future generations.
It is important to be able to share this through exhibitions, scholarly presentations.
We carry out many synergasias, collaborative projects with archaeologists in the different inspectorates of the Ministry of Culture. We conduct research together and publish together.
We're at a moment of revolutionary change in archaeological science.
Using sophisticated techniques, we dig deep into the past.
We can now tell not only what a person had in his last meal, but where he lived.
I guess I've always been pretty interested in different things, but the school gives you the opportunity to really explore all of those things.
You come over as an American and you leave feeling much more like a Greek. You really do get a second home. Το δεύτερο σπίτι.
In the beginning was the Word. Then he spoke, and the sea was born. And I saw, and I marveled. And in it he sowed small worlds in my image and likeness. Stone steeds with manes erect, and serene amphora, and dolphins slanting backs. Ios, Sikinos, Seriphos, Milos. Each word a swallow to bring you spring in the midst of summer, he said. Greece is a small country, but its tradition is immense and has been handed down through the centuries without interruption. The Greek language has never ceased to be spoken. It has undergone the changes that all living things experience, but there has never been a gap. This tradition is characterized by love of the human, he said. Many wise men and learned foreigners write about Greece. For myself, it was but one thing that pushed me to do so. It is that this homeland, we all share it together. Wise or ignorant, rich or poor, even the humblest folk. We are in the we, not the I.
The night before we got to Greece, I couldn't sleep because I was so excited. And I went down to the bottom of the ship where there was a sailor down there, and he had a big door open, and the sea was rushing by. It was totally dark. You couldn't see a thing. But all of a sudden there was a light on the horizon. And he looked over to me and he said, "Alava."
The whole purpose of the foundation of the school really was to get American scholars, students over to Greece to experience firsthand the sites, the museums, the phenomenal buildings, and the topography. The academic program is the core of the American school.
The Mellon professor is the person who sets the tone for the whole program.
I took the time to read old notebooks, so I got a sense of the historical trajectory. And I was so pleased to be able to serve in this long progression of people who had brought to life Greece for so many students.
This tradition started in the very first year of the school. The first director of the school in the fall of 1882 was William Watson Goodwin. He was not an archaeologist, he was a philologist. But he quickly realized that it would be a waste of his time and a waste of the students' time to spend that time reading ancient authors. That's something they could do back in the library in Boston.
People who were students in the 20s and 30s, they would tell you all sorts of stories. They would take all day to get to one site.
We heard stories from them about what it was like to travel on the trips by donkey.
You had to take something like a sleeping bag with you that you would tie around your neck to keep the bed bugs out.
We ate turkey. Turkey for breakfast, turkey for lunch, turkey for dinner, because that's all the food that they had.
Much as we all love Athens, it's so good to get out of the city and see the great variety and the many, many layers of history that Greece has to offer.
Autopsy is everything. How do you move an army from Athens to Thebes? What pass do you use? How are you going to get there?
When you come over here, you have to think about how you approach a problem from a different point of view, rather than just an American point of view.
You become very aware of the importance of mountain passes and sea passages and all of that. So it's important to have in that position somebody who knows the sites very well, but is deeply familiar with all the literary sources and also how a particular spot fits into the topography of Greece as a whole.
Our Mellon professors are the top Greek archaeologists in the world, and they lead our students around approximately 10,000 kilometers.
The Corinthia, the Argolid, we go all the way down to the Mani and the Peloponnese, all the way to Epirus. We go all the way up to Thessaloniki, to Thasos. We spend time in Crete.
It's got to be the best teaching job in the world, because all you do is go around Greece and visit the sites every year with a group of highly motivated and very well-trained graduate students. So many of them become your good friends by the time you're done.
These connections have stayed with me my whole life, and I have very warm and direct relations with many of the students.
When I was a student, the professor of archaeology was a man called Eugene Vanderpool. He got interested in how the Battle of Marathon was fought and how the army got out from Athens. And pretty much every weekend, we could go out with him and help him do his research on the battlefield. He was a fabulous role model in terms of love of Greece and the kinds of things that one should be studying. Particularly Ron Stroud followed in his footsteps with his love of epigraphy, inscriptions, and topography.
Rob said, "Oh, you're so lucky you'll be working with Ron Stroud." And I had gone to graduate school to be a Latin specialist, and I had to say to Rob, "Who's Ron Stroud?" And Rob said, "Oh, you'll get to know him. He's the preeminent epigrapher in America." I took a seminar on epigraphy with him, and I can say, to whatever degree I'm an epigrapher, that's due to Ron Stroud.
I was fortunate enough to be invited to excavate at Corinth as a student, and I was put in the sanctuary under Ron Stroud and Connie Stroud, who were digging there. Until that time, my interest was purely prehistory, and suddenly I was working in a classical sanctuary. It changed my life.
Ron made great friends with a great number of people, and he was always very, very sort of generous with his time with them.
He was tough as nails, but every once in a while, he would pull me aside and say, "How are you doing?" And as a graduate student, your answer is, "Well, I'm working on that last chapter." And he stopped me and said, "No, how are you doing?"
We all come to the school as students, and we think about our Mellon professors as being the people who are going to teach us about the past. And Ron did that, and he did it really well. But he also taught us about the Greece of today and how to approach Greece as a holistic thing, a holistic entity, and to appreciate the language of today, the culture of today, and to interact with it, because we study both the past, but we also live the Greece of the present.
This is irreplaceable, this kind of experience, and it's transferable. It's something real. It's not some picture in a book. I'm totally convinced that it makes you a much, much better teacher.
We have 5 trips a year,
and we start right away. So I get to know them very well. They're learning how to look at the landscape, and it's wonderful to see this first contact. And you can follow their evolution over the trips.
There's no substitute for this. You're dealing with direct ancient evidence. Being lucky enough to be there for the discovery of a terracotta figurine or a pot, when you're the first person who has actually held that thing in almost 3,000 years.
Being in Greece for 1 year helps you build this mental map of Greece, and this is something you will keep forever. Students will remember scenes and smells and visions from these sites for a lifetime.
Students have come up to me and said, "You were there at that place?" And many of them say, "I want to go to that place. I want to be there. I want to see that." Being on the spot and carrying away with you something about being on the spot is one of the key things that the American school can do for you.
I suppose we can just get right into things. Our first paper is going to be presented by Jesús Garcia Sanchez, and it's co-authored with Thierry Lucas, João Fonte, Liv Donnellan, and Jutta Wagen. It's called Drone and Airborne LiDAR in Greece, Mediterranean Perspectives on Processing Techniques and Cultural Landscapes. Jesús.
Okay. Thank you very much, first of all, to the organizers for the invitation. I will take this opportunity to talk a little bit about several projects, some of them here in Greece, conducted with other colleagues, like, for instance, Jette Vagen from Amsterdam University in Halos. Also with some colleagues that you probably already know, like John Bintliff, who worked for several decades in Beotia, with Lucas Terriu during his stage at the French school in Athens. I would like to offer some comparisons with other ongoing projects that we have in other parts of Europe, in the central Mediterranean area, in Calabria, but also in Portugal. Portugal probably could be used as a comparison to the LiDAR situation in Greece, since we are also facing some problems, the lack of national coverage and the need to develop our own archaeological strategies to get our hands on LiDAR data and to proceed with site or landscape studies. I will start with this situation. Well, as you see here in Portugal, so we have a little bit of coverage in some areas around Lisbon, mostly the coastal area, and so on. Some municipalities in the northern part of the country already generated their own data, data that was used to counter the fire risk and some other geological, hydrological risks as well. As in Italy, that's exactly the same situation. Now in 2014, 24, 25, the country is trying to update the coverage, and the country has been divided in 4 areas. And I hope that in the next years we are going to have a national coverage of the whole country. We already know the potentiality of LiDAR data in the study of cultural landscapes in Portugal, especially in the southwest, a landscape which is very, very similar to what we have in Spain. So it's an open oak forest with scattered trees in a very flat grassland. So as we already got very good results in the Iberian part, in the Spanish part of the border. So we hope that in a certain moment we will also be able to jump into the Portuguese landscape, because it's the same historical landscape. In Italy, Giacomo already stressed some of the problems of the LiDAR data in the country. So the partial coverage, well, it's almost 80%, right? But there are some key areas that are interested for archaeology that are still missing, like the upper part of the river basins, like the upper Volturno Valley, where some of the Samnite hill forts, some of the most interesting Samnite hill forts, as La Romana or so on, are still missing. So we also did some experiments, like in Monte Vairano, also really large Hellenistic Samnite urban sites, and well, I won't comment nothing else about LiDAR, the national LiDAR data in Italy, because Giacomo already did, and he did very well. So in those countries where we still lack very high accurate LiDAR data, we are in need to develop our own strategies. So in some of the places, like in Calabria, and in the Valley of the Muses in Beotia, the data recording has been done with airplanes, with small airplanes like this one from an Austrian company from Aerophoto, as we already saw. They also created the data for Beotia. And in some areas here, our colleagues from Amsterdam University did a very large LiDAR survey in Halos. And our colleagues from Archaeology also use different kind of drones to acquire data from specific sites in Portugal. So if in Italy and Spain we have some data to compare the different resolutions, different processing algorithms and visualization as well, so between national data and our LiDAR drone data. In other places we have nothing to compare with, like in Portugal or in certain parts of Greece. Why is this that important? So we are trying to approach the problem of landscape studies with LiDAR data in two different ways. First of all, is to solve specific historic questions relating to sites. Here we have not so old drawing of the Roman siege on Kephissos de Vallamonte in Portugal, near the border with Spain. And you can already see how sketchy it is, so it just demonstrates the very raw perimeter of the site, the movements, or possibly movements of the troops and so on. But the recent LiDAR flight with using one of these micro drones equipment also created a very detailed picture of the location of the site, the fortifications, probably also the siege, and so on. Here in Beotia, we also did some of the experiments. Lucas Tegui collected the legacy data, and with the new processing of the LiDAR data, we were able to improve significantly the results of and the understanding of the Hellenic city as we see it there. In Alos, our colleague Jette Wagen from Amsterdam University and the 4D lab approached the problem a little bit more experimentally. So they focus on these two areas, Platonikotiki and the Iron Age necropolis down there. Well, this is a little bit of what they did, also employing DJI drones and processing systems. So what he's trying to do in this area is to try to change, use different parameters to see the final results of different ways of acquiring data, but also processing data. So here we have at the left the default settings, perhaps that he is using with the DJI equipment, and at the right, so we have another more detailed recovery of data of the same Acropolis area. Well, the result on the LiDAR data is, of course, that once you start experimenting with different algorithms, different ways of acquiring the data rather than the default settings all those equipments have, are really there are real implications of the quality of the data that you get, and also the improvements on the detection of certain features and so on. There is another way of approaching the studies of cultural landscape with LiDAR data, which is the scale of landscape. We already saw very interesting approaches in Italy as well. So here there's a little bit of what we are trying to do in a couple of location areas, mostly in Italy, where the Austrian company is collecting LiDAR data around this Piano di Goya Tauro in the point of Calabria, and this data is being used to assist the implementation of a traditional field survey in the area with the goal of analyzing the impact of Greek colonization on Bronze Age communities in that area. One of the main points of this combination of LiDAR survey and field survey is the difficulty to get field information about certain features like terrace landscape that have been abandoned for decades already, and that it's very difficult to obtain information one way or the other. So we hope that this combination of LiDAR data with satellite imagery could highlight at least some areas of interest that could be visited in the next campaigns. Those campaigns are carried out by Livet Donnellan from Melbourne University and the Micmac project. On the contrary, in the Valley of the Muses, in Boeotia, John Bintlis has been doing a field survey there for decades, and the idea of this small project in combination with the French school in Athens was to try to get more grasp on the configuration of the sanctuary, locating some of the elements that were already known, but also a general understanding of other elements like enclosures, probably hopefully new buildings that were unknown, or at least they were mentioned before by the legacy data and so on, but at least what we are trying to do is to understand a little bit better the configuration of the landscape. Well, we also try to, sorry for the mistake with the font. So what we were trying to do here is to also approach the problem a little bit more experimentally. So trying different ways of processing the data and checking the results both in Akrifia by the work done by Lucas Segui and the processing of the LiDAR data in the Valley of the Muses. So we use LAS tools, which is not open source, but we are trying to customize a script. And once we have LiDAR data processed with different parameters, we check the quality using other tools like Fusion, which is open source tool, and that could, Fusion data creates those maps of density and assess a little bit, gives us some information about the performance of our application. Then we jump to interpolation, so this the step previous to the visualization. We are using white box toolbox, right, that allow us to interpolate large areas. So we are trying also to combine different elements. Some of those could be used within QGIS and so on, but we are trying to do it going to the fundamentals of all those tools, especially the capabilities of scripting LAS tools through the console simply. So those are some of the results, very, very basic visualizations of some of the stoas that were excavated a long time ago, and that contribute to a better understanding of not only the configuration of the sanctuary, perhaps in the old times, but also for heritage purposes, like the consolidation of structures and so on. Well, just briefly, I want to stress the similarities of the problems that we are facing here, working with Greek data and other fundamental problems that we have in other parts of the Mediterranean basin, like in Portugal, where despite the creation of a national coverage is still ongoing, there is still a little bit of concern or understanding about the capabilities of LiDAR tools to improve the archaeology, or landscape archaeology, or the understanding of specific sites. So there is still a lot of work to do there, with not only with with funding, with the universities, but also with the archaeologists themselves. In Spain, well, as we were discussing before, so we have two national coverages, but we are still exploring how to improve the data, not only by acquiring new data with drone or airborne sensors, but also with processing and visualization techniques. Well, thank you very much.
Thank you, Jesus. Our next speaker is Anastasios Kazolias, along with Vaya Panayotidis and Nikolaos Zacharias, on LiDAR and Landscapes in Archaeology, the case of Palaeokastropylos, Greece.
Yes.
Yes, good afternoon. My name is Anastasios Kazolias. I'm a PhD candidate in University of Peloponnese and member of the Laboratory of Archaeometry. I'm about to present one part of my PhD thesis, the aerial scanning using LiDAR on Paleokastro Castle or Old Navarino Fortress in Pylos. This site is situated in Messenia, specifically on the Kephissos Peninsula, at the southern end of the Voidokilia Beach in the Navarino Bay, in the southwest region of the Peloponnese. Paleokastro has an important place in history as it was built during the Frankish occupation in the Peloponnese in the 13th century. It is remarkable that it was built on the top of the classical Acropolis of Pylos. The castle, which stands on the hill of Kephissos, has undergone many changes over the centuries. The shape of the castle is trapezoidal, covering an extensive area of approximately 50,000 square meters. The outer walls and many of the towers have been preserved. The interior shows the earlier phases with scattered ruins. A notable feature is that the transverse wall that divides the castle into separate parts, the north and the south. The northern part, located at the top, holds the remainings of the ancient citadel and probably represents the original Frankish castle. In contrast, the southern courtyard, an addition made much later, contributes to the overall architectural complexity of the site. On the eastern side of the castle, where the absence of walls is intentional, the natural fortification of the cliff itself provides plenty of protection. It's here, that part. There we have steep cliffs. So LiDAR technology has allowed us to make the layout of the castle, identify changes over time, and identify the purpose behind its modification. Paleokastro today has a number of challenges that we must face in order to survey it. The area is characterized by dense low vegetation, as you may see, which makes it difficult to conduct ground-level surveys. In addition, the location of the castle creates difficulties in terms of access, adding a level of complexity to the research process. Furthermore, the multi-level morphology of the terrain in the area and the complex structures within the castle add to the challenges. These factors highlight the importance of advanced technologies such as UAV LiDAR to address these obstacles. To capture the details of the castle and its surroundings, we used cutting-edge technology, specifically the 3D T-Scanfly Light X. The LiDAR features a scan rate up to 640,000 points per second and ensures accuracy within 5 centimeters when post-processing kinematic solution is used. The inertial navigation system, the INS, enhances the accuracy, providing high accuracy level of pitch, roll, and heading measurements. The LiDAR system is mounted on a DJI Matsas 300 RTK drone, and in addition, we use the Topcon GNSS receiver to receive RINEX data for accurate post-processing kinematic solution. Now, the next step is the planning and execution required to scan the whole of Paleokastro. To cover the entire scan area, we designed 2 different flight missions. By maintaining a constant flight altitude of 60 meters above the ground, these missions allow us to capture the terrain features accurately. The chosen altitude achieves a balance, allowing for detailed data collection, optimizing the efficiency of the LiDAR scanning process. A key feature that enhances the efficiency of our aerial survey is the ability to follow the terrain from the drone. By dynamically adjusting the drone's altitude to track the natural variations of the environment, we ensure that our LiDAR captures a consistent and accurate representation of the terrain. Throughout the flight mission, the GNSS receiver continuously records its position, creating a spatial record in a RINEX file. And the sequence of the flight is as follows. First, we have the takeoff. The drone rises to the specified flight altitude, starting the aerial survey. We have a forward heading at 5 meters per second. The drone follows a systematic forward course at a speed of 5 meters per second, calibrating heading. Then we have a figure 8 maneuver that included in the flight plan to calibrate the inertial navigation system. This calibration step ensures that our LiDAR data remains accurate and aligned with the drone's movements. Then we have the execution of the flight plan at 3 meters per second, that we have checked that this system is more accurate. And then when the flight plan is over, we have another figure 8 maneuver in order to calibrate backwards the whole flight mission. And again, a forward path at 5 meters per second, and then we have the landing, which means the end of our flight mission. This flight sequence calibrates the LiDAR system INS, ensures that the LiDAR operates with maximum accuracy. The first step of post-processing, where the LiDAR, the INS, and GNSS data are combined and aligned, and then we have the point clouds. Now we move on to the colorizing of point cloud, adding photorealistic colors to the data collected from the mapping. After the LiDAR has captured millions of points, colorization converts the point clouds from grayscale to true colors. Using high-resolution images captured simultaneously with a scan, we overlay textures onto the LiDAR data. Our next focus includes the process of point clouds strip alignment and bore site calibration, critical steps to ensure the accuracy of consistency of the LiDAR data. After LiDAR has captured extended point cloud strips, alignment of these strips is essential for a consistent representation. Through advanced algorithms, we align each strip with its neighbor, creating a single compact point cloud of high accuracy. Bore site calibration focuses on the correlation between LiDAR bore site angle and the INS behavior in order to correct the alignment between their bodies. Now we discuss the classification of the point cloud into distinct categories, each representing different features across Paleocastro. First of all, we have the ground, represent the ground surface, vital to understanding the topography of the site. Then we created a low vegetation category, includes low-lying vegetation, providing information complementary to the ground. Then we have medium vegetation, includes taller vegetation such as bushes or small trees. High vegetation that includes larger trees and dense foliage, indicating areas of significant vegetation cover. And finally, we have the buildings, represents the structural elements of Paleocastro necessary for understanding the architectural layout and historical significance of the site. Now, let's look at some profiles. Profiles offer a vertical cross-section of the entire area, providing insight into variations in elevation and terrain features across the site. By analyzing these profiles, we gain a deeper understanding of the landscape morphology, identifying high and low points, as well as details beneath dense vegetation. Profiles inform site planning and excavation strategies, guiding researchers in identifying areas of interest for further investigation. The next 4 slides presenting the results processed with ArcGIS Pro and Relief Visualization Toolbox, the RVT toolbox. On our left, we have the orthomosaic of Paleokastro, a stitched together georeferenced aerial image providing a detailed overview of the castle. And on our right side, we have a hillside relief, a visualization showing variations in terrain elevations, helping to identify fine topographic features. From that part, you may see that here in orthomosaic we cannot see anything beneath the vegetation, with the bushes and all the medium vegetation. And here we can see that we have some structures inside in the interior of the castle. So move on, we have the shaded relief on our left, which highlights terrain features through simulated illumination, providing a clearer representation of the landscape. The color ramp indicates altitude changes. And on our right side, we have the multi-directional hillside, interpolation of multiple hillside perspectives, enhancing the visualization of terrain morphology. Next, we have on our left side, we have the openness, provides insight into diffuse illumination and average horizon elevation angles within a defined radius. And on our right side, we have the sky view factor, highlights the proportion of the sky visible from specific points, helping to identify terrain features such as ridges and depressions. And finally, we have visualization of the archaeological topography, VAT, a comprehensive visualization technique that combines hill shading, slope, positive openness, and sky view factor. VAT uses predefined calculation and blending settings to enhance specific features of the terrain, aiding in archaeological analysis. These results providing a detailed understanding of the topography and characteristics of the structures of Paleokastro and will be used as a basis for further research. I want to thank the director of the Laboratory of Archaeometry, Professor Nikolaos Zacharias, and Dr. Vaya Panagiotides. Thank you all for your attention.
Again, thanks to everyone for being so on time and clear and crisp. We're ahead of the game, but that's great. Our next paper is entitled UAV-Based Survey of Ancient White Marble Quarries on Mount Telecon, Challenges and Successes of a LiDAR and Photogrammetric Survey in the High Relief Environment by Scott Pike, Cassie Drawson, and Adelaide Kemp. Oh, it will be presented by Scott and Adelaide.
Well, thank you. Thank you to the organizers for having this conference. It's really nice to have all of us who have been working in LiDAR to come together and learn from each other and learn of challenges and successes and talk about where we're going to go forward. So my this project is going to be a little bit different than the other ones because we're not looking for an archaeological site. It's one that we know is already there. It's in existence. It's like the previous paper. This project, I should start, is funded by the National Science Foundation's International Research Experience for Students. So in designing this project, I was also designing it so that I could fund 4 undergraduate students from my university at Willamette University bring them to Greece to spend 6 weeks to have an international research experience. So Adelaide was the lucky one, or unlucky one, I don't know, to join me and presenting our research at Mount Pentelicon. So Mount Pentelicon, just outside of Athens, has been a very large marble quarry, a resource. First opened up in around 490. We believe that there were some 5th century architectural structures and sculptural material excavated. But on a large scale, it wasn't until about 490 BCE when the Athenian people went out to this quarry and started extracting on a large extent. I have here just plans of the older Parthenon and the later Parthenon, thinking that it was the older Parthenon that probably was the impetus to start excavating or exploiting marbles at Pendeli on a large scale. Just in terms of placement, one of these is an arrow, there it is. The Pendeli quarries lie to the northeast of Athens. They're about 18 kilometers away from the Acropolis. And even though they're relatively close, it was quite an expense and an accomplishment to be able to bring marbles from the mountain. First, they had to quarry the marbles, obviously drag them down the mountain, but there were 2 rivers to cross and 18 kilometers of landscape. And in many ways, you could argue it might have been easier to extract marble from Paros, for instance, and put it on a ship and then bring it over. But Pelion marble was getting expensive, and I do believe Athens wanted to use their own resource to build their monuments. The most famous quarry at Pentelicon is the Spilia quarry. It has a nice early Byzantine church in it. But this quarry is visited and by rock climbers as well as people who just want to spend some time outdoors. And I wanted to show this image because on it you might be able to see, and I don't know if we have the resolution, that there are tool marks visible on the wall. So these are quarries, tool marks that are visible. So when at Pendeli there are over 130 individual quarry pits, many of them still preserve these ancient tool marks. So we know that they were active in antiquity. But the quarries were also active up until the 1970s. So many of the quarries, maybe the ancient quarries, were later extracted, and evidence of ancient mining may be gone. We also just have very, very large pits, which may or may not have been in the same areas of as the miners in antiquity. So as part of the Parthenon reconstruction project, Manolis Korez, through personal communication with him, had told me that he was very interested in going to Pendeli and finding the ancient quarries that supplied the marble for the Parthenon with the intent of possibly using that same marble for the reconstruction. And he went up to the mountains and made a map identifying the ancient quarries, identifying the modern quarries, and came up with a elegant, simple solution to how the Athenians would have quarried the marble in antiquity. In building his map, he used a topographic map that was available from IGME. It was developed in the 1970s, and I'm assuming that map was generated from airplane data, some photographs, and then they have draftsmen generate these maps, so they were probably hand-drawn. But what Korez speculated was that the first large quarry that you come to that shows ancient tool marks at Pendeli is right here. It's Spilia, the quarry I showed you previously. And Korez called that quarry Lambda 1. It was the first quarry. And after the construction of the Parthenon, they built the Propylaea. So they went up the hill and opened the second pit for marbles for the Propylaea. And as they finished and exhausted that pit, they went up to the third pit uphill. The argument being, why work harder when you had the marble lower down the mountain? So when they exhausted Lambda 1, they went to Lambda 2, and Lambda 2, they went to Lambda 3, and up the mountain they went. I I'm a geologist, and I was doing my dissertation research on Pendeli, and I was interested in seeing if there were geochemical signatures within the very large very large quarries that would allow us to distinguish different regions of the quarry, different parts of the quarry. And I started with Corrèz's map when I went out to collect my own field data and my own reference collection to sample. As I was working, I realized Corrèz's map didn't fit with the quarries that I recognized. So I had to make a new map, and this is my somewhat embarrassing map that I generated back in the 1990s, based simply on triangulation and triangulation. I didn't have the use of a GPS. I didn't have any technology other than a transit and a barometer. And this is the map I generated. The red quarries are the ancient quarries. The blue quarries are modern quarries or ancient quarries that no longer have any ancient tool marks, so I wasn't certain if they were ancient or not. So when I applied for the NSF for the IRIS grant, my goal was to improve this map. What can we use? How can we improve this map using drones, using LiDAR to map it accurately? And what can that LiDAR tell us? What new information can the LiDAR tell us? So here's Spilya, just as a landmark to show you the extent of the quarries. So the research goals that I had was to identify, record, and quantify all the known and maybe even identify some unknown quarries at Pendeli using this digitally derived LiDAR data. And is it possible that some of this quarry area up on the mountain, maybe there's some quarries on the side that have been missed by previous research? So maybe the extent of the quarries is actually larger than we think. From this data, we could generate contour maps, DTMs as well, and then delineate features of the quarry roads and other landscape features that would have supported the quarry work. The other thing I ultimately want to do is start determining the volume of material excavated from the ancient quarries to give us a sense of the amount of material that would have been exported through antiquity. Now, for the LiDAR and for the purposes of this conference, the methodological goals is to determine the ideal mission parameters to record these quarries. And to do that, we needed to build an efficient workflow and to process the data. And then because I had students with me, we could also process that data and then go back to the quarries and ground truth what we saw or what we identified. Some of the challenges in this particular field is that we had it's a high relief area. And from the bottom of the survey area to the top, it's actually 700 meters, not 350. 350 is the halfway point. So in just 2.5 kilometers, we gain a lot of elevation, so it was difficult to map. There's also lateral elevation differences as we fly, going into quarry pits and going up above quarry pits. So that was a challenge we had to consider. Also, a LiDAR unit on a drone is very heavy, so it uses the battery power, quite a bit of battery power, so we only had short duration flight times of up to 15 minutes. We're also working with very large data sets on portable computers, so that was a limit. And as we saw, we had pockets of vegetation that the LiDAR was a bit, had some challenges. And it's windy. We're in high elevation, particularly later in the day. The drone that we had actually cannot fly in high winds. The equipment we used was a LiDAR manufactured by LiDAR USA called a Surveyor 32. We attached it to a DJI Matrice 600 Pro. And for those of you interested in the dynamics of the drone, 32 channel, 2 returns, collecting 1.2 million points per second. And at 60 meters, which is the elevation we flew at, the accuracy was sub 2 centimeters when we were using a GNSS. We also flew a Matrice 3E to capture orthophotos, and also with the intent to capture the surfaces of the drones, try to see if we could record, the surfaces of the quarry walls, to see if we could capture the tool marks. We used two different, we used both RTK and PKK as well to to correct for our positioning. The LiDAR workflow we used Google Earth to plan our mission using nodes, and we transferred that to flight mission software called Litchi. It was free, and there we used automatic ground terrain so that the drone would fly 60 meters consistently across the landscape. We also, again, used the 3E to using the DJI flight management software. The LiDAR data that we captured, the LAS data, was processed, corrected for PKK using ScanLook, and then we used ScanLook PC to join the LAS files together. And then Pix4D to generate our georeference orthophoto. And then took the data, imported it to Global Mapper Pro, where we colorized the point cloud, classified the point cloud, and then generated our DTM and contours. So this is just a quick view of what the data looked like. So this was in the Litchi showing each of the nodes and the 60 meters above the surface level. Also note we did a gridded pattern to get proper density. And then this transferred it back into Google Earth just to show you the height elevation above the very topographically high relief of this region.
The processing software that myself and the other student researchers used to process all of the LiDAR data was Global Mapper Pro, which immediately colorized all of our LiDAR points by just simply elevation. So our first step in our processing workflow was to colorize the point cloud based on the RGB values obtained through our photogrammetry missions. So we uploaded our 3D orthophoto produced through our Pix4D photogrammetry processing to Global Mapper, and then used the Apply Color to LiDAR tool in order to colorize our point cloud. And our photogrammetry and LiDAR mission survey areas didn't perfectly line up, but this didn't impact our results as all of our areas of interest were within the colorized point cloud. These are zoomed in screenshots of our colorized point cloud to demonstrate the resolution. The image on the left displays the Spilial quarry site, and you can see the modern and ancient roads converging leading to the mouth of the cave, as well as the quarry walls and spoils piles. The image on the right displays the area a little bit farther south of the ancient quarry road, and you can see the road really clearly in the colorized point cloud, as well as spoils piles. And in the top right of the image, you can see the discarded column drum off to the side of the road. The next step was to classify our point cloud. This was the most difficult processing step for us. We used the auto classify ground tool in Global Mapper, but we had to significantly adjust the classification parameters due to the high relief environment and really kind of jagged landscape. We did a lot of trial runs on much smaller survey areas in order to define our classification parameters, which ended up being a bin size of 0.25 square meters, a maximum deviation of 0.3 meters, a maximum height delta of 400, and a maximum terrain slope of 70 degrees. This 70 degrees was the variable that took us the longest and was the most challenging to finalize because the quarry walls obviously had slopes of up to 90 degrees, but the rest of the terrain had much shallower slopes that made it difficult to fully classify the ground. So we ended up on 70 degrees, and the other student researcher, Cassie Drazen, who was working on the Pendeli as well, she went through and manually reclassified all of the quarry walls as ground. So then once we had our ground classification done, we moved on to vegetation, as you can see in the image on the right. And this we were able to do with all of the default parameters. Our next step was to create a DTM and 5-meter contour of the survey area, which were both very simple functions in Global Mapper. We did, however, only use the LiDAR points that were classified as ground in these two functions, and we disabled all smoothing for appearance functions, but everything else was done with the default parameters. Because of really high vegetation density in some areas, removal of vegetation was successful in generating contours in a DTM, but would not have been high enough for more specific goals such as further quarry road or quarry feature identification. The last step of processing for me, because my project focused on the ancient quarry road descending south from Spilia, was to upload the 5-meter contours as well as the orthophoto onto ArcGIS Pro, and then used the create feature class function to trace and outline the quarry road as well as all of the identifiable post holes, column drum, the loading dock, and the ancient cobbles. And the creation of these files, geolocated files, allows for them to be uploaded into mapping software such as Google Earth and to be shared that way.
And then finally, so Adelaide mentioned she was focusing on the quarry road. My other student, Cassie, was focused more on identifying quarries beyond those that were already known. So on both my map and Correz's map, there were some quarries that were missing near the top of the mountain. So Cassie actually outlined those quarries and gave them numbers. So we were able to extend the ancient part of the quarries up the slope. This is near, for those familiar with the mountain, this is near the radar tower, very close to the radar tower. So just to sum up, the aerial LiDAR and photogrammetry were successful at providing high accuracy survey mapping in this high relief area. And we were able to map these negative features with high precision. We did note that with the we did the cross-gridded path in the lower portion of the quarry, but we did not do it in the upper portion of the quarry. And our data is much thicker. We have a thicker data set with the cross-gridded pathway, which makes sense. We were able to identify and extend the ancient quarry area, which was one of our objectives, but the LiDAR was not able to pick up any of the tool features that we were able to see with the Mavic 3 RGB sensor. So our next goal is to go back to the quarries and make photogrammetric models of the ancient quarries, and then integrate that with the point clouds from the LiDAR to have a final, to have a more extensive database of the ancient quarries. And I'd just like to acknowledge the NSF and our colleagues, and thank you very much.
All right, thank you, Scott and Adelaide. Our final paper in this session, before we move on to a discussion period, is on using UAV LiDAR to reveal quarried landscapes on Naxos. It's by Evan Levine, Halvard Ingjerd, Steinar Christensen, and Magna Samdal. And Evan will be presenting.
Yeah, and this is going to be a different kind of quarry landscape compared to what you just saw. So, good afternoon, everyone. We're excited to share the results of a 10-day pilot season of the Naxos Quarry Project, which concluded just over 2 weeks ago. So considering the whirlwind turnaround between data collection and presentation, this paper is going to focus on introducing our research objectives, highlighting preliminary results in our LiDAR data collection, presenting a series of classification tests, and exploring where aerial LiDAR survey sits within a broader suite of interdisciplinary fieldwork. Before continuing, I'd like to extend the appreciation of our entire team to our colleagues at the Archaeological effort of the Cyclades, especially Dimitris Athanasoulis and Irini Lagaki, with whom we're collaborating on this project. Our sincere thanks goes out as well to our partners at the Archaeological Museum of Naxos, support from our home institutions seen here, and generous funding from the Museum of Cycladic Art. Naxos is the largest island in the Cycladic archipelago with an exceptionally resource-rich landscape, especially when compared to its smaller, generally more arid neighbors. Deep, nutrient-dense soil and varied topography made Naxos singularly famous for agricultural cultivation in antiquity, especially viticulture. However, its geological and mineral landscape was as important an economic factor in the story of the island's economy, and it remains so today. Exploitation of Naxian geological resources began as early as the lower Paleolithic period at chert sources on the Stelida Peninsula, but the island is perhaps better known for its rich sources of a large-grained, exceptionally vibrant marble that allowed for the regular extraction of significantly larger blocks than other contemporary Aegean sources. In addition, mines on the island's north and east coast are the only sources of Emory in the Aegean, an abrasive that was not only required for local marble extraction and stoneworking, but a key economic export in its own right. While Naxian marble was sourced for sculpture and architecture from the early Bronze Age, systematic and extensive exploitation of these resources began in the 7th century BC, bringing a level of prosperity to the island that was symbolized through rich dedications at home and throughout the Greek world. These dedications made ready use of the enormous blocks of marble offered by the island's particular geology, leading to, or perhaps reinforcing, an impetus to build big. This is evident in the development of a particular architectural and artistic style that made use of long, relatively thin slabs to prioritize monumentality, as seen in dedications both abroad and on Naxos itself. The stone used for these monuments was primarily sourced from 2 quarries on Naxos, marble outcrops near the villages of Melanese and Apollonas. These quarries are well known, especially for and long thought about and studied, especially for the presence of 3 colossal sculptures that were abandoned during facture and transport, including the absolutely enormous 11-meter tall figure at Apollonas that you see laying in the landscape on the top. While often referenced, these kouroi and the quarries in which they're found have never been systematically studied and had all of this data brought together, and many fundamental questions remain that limit the amount to which they can be integrated into broader conversations about the island's economy, political history, and local multifaceted landscape setting, due primarily to the extremely rugged topography, dense vegetation, and sheer size of the objects under study, which every paper has spoken about today. So the Naxos Quarry Project aims to fill this scholarly lacuna by bringing together a truly remarkable team of experts to answer a series of discrete questions concerning marble quarries on Naxos, while exploring best practices for the documentation of quarries as archaeological features embedded within complex landscapes. To do so, we first isolated these 2 survey areas, encompassing the known evidence for quarrying at Melanese and Apollonas. Our primary engagement with these spaces was through a combination of intensive and extensive fieldwalking, documenting the traditional subjects of regional archaeological survey, ceramics, architecture, and of course, a wide range of evidence for stone quarrying. However, fieldwalking was undertaken alongside a series of specialist studies that provide a rich interdisciplinary data set for our understanding of these landscapes. So in brief, Vasiliki Yanevlavi is conducting a comprehensive geological survey of both areas. Torsten Jakobich is undertaking a historical ecology of the survey areas, exploring the botanical implications of intensive quarrying and the transition of these landscapes into agricultural spaces. And he also produced the 2 most beautiful results from the project, which are these 2 very rare orchids that seem to only be growing in quarried landscapes, which is kind of interesting. Rosie Campbell and I are focused on the documentation of archaeological features within our study areas, including topographic surveying, handheld laser scanning, and general study of the broad range of architectural and archaeological material culture. Rebecca Levitan and Nikos Yokas are documenting the colossal sculptures in each quarry and the many fragments of sculptural material documented during our survey, while Jessica Pega and Jean van den Broek are studying the architectural material. These 4 are also focused on isolating evidence for particular quarrying techniques, areas of intensive extraction, and broad implications of this behavior. Florence Liard undertook in-field ceramic documentation, developing a chronological range of activities at the survey areas and highlighting one of our most interesting results, that these landscapes, which present exceptionally dense, multifaceted evidence for anthropic activity across all periods, was almost entirely devoid of surface ceramics. So it's within this broad interdisciplinary network of approaches to archaeological research that my co-authors, Magnus Samdal, Steinar Christiansen, and Halvar Ingjerd, developed an extensive program of aerial LiDAR survey. These data were collected using a DJI Matrice 300 UAV with a Zenmuse L1 LiDAR sensor This was a relatively inexpensive and compact system for aerial LiDAR scanning with a takeoff weight just above 7 kilograms and 45 minutes of flight time per battery, although they would probably argue that compact is not the right word to use. The sensor is capable of a maximum of 3 target echoes or returns and up to 480 kilohertz of point collection at 2 and 3 returns. One aim of the Naxos Quarry project was to test the differences between these collection settings in an Aegean landscape, and we will, at a later date, also compare it with 5 return systems like the Rigel Mini VUX3, which is commonly used in archaeological recording at other projects. RTK corrections were provided by an EMLID Reach RS2 set up at a base station outside our hotel in Chora on the west side of the island, transmitting NTRIP data through EMLID's open source NTRIP caster software. So this functioned flawlessly. We were really excited about this, providing corrections to both the drone and other EMLID rovers used for feature documentation at both locations simultaneously and with several things happening at the same time without the need for commercial corrections. In total, 19 flights using the LiDAR sensor covered close to 200 hectares, while 5 photogrammetry missions collected data from 70 hectares. Topography, vegetation, and archaeological ground traces were markedly different between Apollonias and Melanese. Apollonias displayed lower vegetation, steeper slopes, and more visible worked bedrock, while Melanese presents a diachronic cultural landscape with a larger variety in vegetation zones. The goal of this field season was to test to what degree the LiDAR sensor would be capable of penetrating the low maquis shrubs that are ubiquitous in Aegean survey areas. A quick glance at the raw point cloud data seen here, captured at Apollonias, gives a clear indication of our results. The freestanding trees along the road and the taller bushes in the Rema provide ample second and third return data. The medium-high maquis in recently abandoned agricultural terraces has some second returns, while the dense low maquis in the uncultivated hillside generally only produced a single return. However, we wanted to investigate this data in more detail. So in Melanese, we delineated a small test area of 0.7 hectares for repeated flights under different parameters. This area was chosen to encompass as many distinct ground and vegetation types as possible, including freestanding olives with bare soil, high and low maquis, stone walls, and structures, amongst several other. Here we flew the same mission with 2 and 3 returns at elevations of 30, 60, and 90 meters above the ground level in order to compare the sensor's vegetation penetration capabilities and to create a data set for classification testing. At 2 returns, we see that an altitude of 60 meters provides considerably more second returns than 90 meters, which is unsurprising. However, the difference between 30 and 60 meters is far less distinct. For all altitudes, the initial assumption from the Apollonias data holds up. The areas with freestanding trees and medium-high vegetation create some second returns, while the lower maquis does so only to a low degree. The density of second returns is similar in the data from the 3-return flight. However, in this area, there are very few third returns at all. The sacrifice of resolution for the possibility of reading an extra return does not seem to pay off in these particular landscapes. Multiple returns in vegetation penetration is, of course, mainly an aid to be able to separate the collected data into meaningful classes, as you've seen several other papers discuss. So we wanted to explore some of these automated classification algorithms. A general issue that we encountered is that most of these algorithms are optimized for high altitude, lower resolution manned aircraft LiDAR data. While the principles remain the same, the features that we're aiming to capture, and I think Scott's quite similar, offered some trickier questions for us and how we were gonna pull that off. So we wanted to develop algorithms specifically targeting close range aerial LiDAR for things that are a little more subtle, like tool marks and quarry zones. Still, sometimes the automated classification workflows resulted in meaningful divisions, even if the assigned classes were not strictly correct. So you can see here, for example, how the built-in classifier in Metashape is fairly good at separating out stone walls. However, it categorized them as cars, which is not correct. Using the point cloud from the 30-meter 3-return flight, we tested 9 available classification algorithms, some of which have been presented here already today, and built digital feature models based on all classes except high and low vegetation. The output of these algorithms differ. Some only classify ground points, while others separate the data into several natural and man-made feature classes. So let's take a first look at the digital surface model generated in Metashape from all the points without any classification or return filter. Here we see the dense vegetation cover at different heights, with low maquis in the south, higher bushes and small trees in the northwest, and freestanding olive trees in the northeast and southwest. The footpath and unobscured stone walls are clearly visible. Metashape has a built-in classifier using 6 predefined classes. In the feature model generated based on all but high vegetation, we see a successful removal of the freestanding olives, but very little information is preserved in the areas with low and medium maquis cover. By comparison, we ran the same processing on the data from the 60-meter 3-return flight. This is similar to the 30-meter result, but considerably less ground data is preserved in areas with medium vegetation cover. Next, we use the open source Canupo classifier tool, available as a plugin for Cloud Compare with 3 different classification models: vegetation semi, bedrock semi, and vegetation super. These were all more conservative than the other models that we used, trained to target specific subsets of topography, and would be better employed in combination. But as expected, we see that the vegetation semi classification is quite successful at removing the medium-high maquis. And you can note specifically here that it reveals more of this wall that is otherwise obscured. The built-in ground classification tool in ArcGIS Pro is a binary classifier dividing the point clouds into ground and unclassified points. It does a very good job at creating a digital terrain model where everything but the ground is removed. However, this means that the features we're interested in also tend to disappear, but this would be a good starting point for further refinement of the remaining points. Using DJI Terra, the software that we use to read and export the L1's raw data, results in some smudging and artificial edge effects, but it does recover a lot of ground points, and features like the stone wall running below the vegetation are visible, albeit as a negative impression. Finally, we used a combination of algorithms in the LAS tools package, LAS ground, LAS height, and LAS classify, which were run through its QGIS plugin. Of our tests, this produced the best combination of vegetation penetration and the preservation of non-vegetation features, creating a sharp DEM with little interpolation and smudging. Looking at the 3 last algorithms in comparison, we see quite clearly the difference between the ground reconstruction in the DTM from ArcGIS Pro and the feature preservation in LAS tools. Note how clearly the stone wall we looked at stands out in these examples. We also wanted to compare the results of our LiDAR survey with traditional UAV photogrammetry. We generated high-quality point clouds from photos taken with the L1's integrated camera using Agisoft Metashape based on depth maps. All point clouds were then classified using the built-in automated classifier in Metashape. Digital surface models were exported from the raw point clouds, and digital feature models were generated using all of the points except for high vegetation. Using this area as an example, we see that the results do not show marked difference between these methods. We calculated difference rasters comparing each DFM to the flight's respective DSM to see how much vegetation was removed in each case. Neither are capable of reconstructing the ground in the dense low maquis, and in the areas where the LiDAR does manage to penetrate the vegetation, so does the photogrammetry thanks to the oblique angle of photo capture. Only in the open areas with freestanding trees in the northern parts of the view, which overlaps with the test data that we brought up above, do we see considerably better results from the LiDAR data. However, a lower altitude photogrammetry flight mission with a stronger oblique angle would further increase photogrammetry's ability to recover ground under vegetation. The leftmost image is a difference comparison between the surface models created by photogrammetry and the 3-return LiDAR. Apart from freestanding trees, the entire area falls within plus or minus 5 centimeters in difference, and this shows how accurate the RTK positioning is and how consistently accurate structure for motion and photogrammetry has become. To further illustrate the comparison, we calculated the difference between the results in the LiDAR DSM and DFM difference maps and the structure for motion photogrammetry DSM DFMs. This highlights again that LiDAR is most effective compared to photogrammetry in areas of higher and more open vegetation, while differences are minimal in areas of dense, low vegetation. And we see that here. A final takeaway from our testing is the enhanced level of detail that can be extracted from photogrammetry using point cloud processing and visualization otherwise reserved for LiDAR data. This offers the opportunity to highlight the subtle changes in surface topography, like tool marks, necessary for the documentation and interpretation of quarry landscapes. I'd like to conclude by reiterating that these are only early results from an inexperienced team, and we welcome comments from scholars with more experience working in these conditions and with these tools. In the meantime, our next steps are developing our own classification algorithms to work with our particular data in these particular landscapes, and we plan to test for seasonal variability in vegetation by conducting additional testing in the fall. We would also like to compare the results of UAV LiDAR with manned aircraft data, and of course, we'll be processing a series of industry standard visualizations like VAT and local dominance and all the stuff that we've seen throughout the day, using our classified DFMs as the underlying data set. And when the time is right, which is not right now, we look forward to sharing some of the actual results of our fieldwork in the quarries with you all. Thanks.
I think, yes, go on. Evan, join us here, and if we could have the other speakers from this afternoon's session come up and open the floor for questions. I think we have a question over here.
Hello. It's a question for Anastasis for the Paleocastor project. I'm interested in I'm just going to photograph your slide because that's the only way to remember. The last layer you presented, the one with the, how did you call the visual archaeological topography. So I suppose you just overlaid the 4 previous layers. But how exactly you managed to produce this?
No. To be honest, it's the RVT software that did the combination of the layers. So I'm not right now ready to answer that the algorithm behind this combination, but this uses the visualization of hillside, of slope, of openness, and the last one is the sky view factor. Yes. I think it's the algorithm that enhances the structural data.
So there was no manual adjustment. You just fed you're feeding the 4 layers, and it's producing the 5th one, really.
Yes.
Okay. It was a pretty impressive results for no manual adjustments. That was questioning, but they're looking really good. So yeah. Thank you.
The most difficult part in that project is that we have a lot of work to do also again, but the interior part, the most difficult part is the classification, because it's very complex, and we had a lot of medium vegetation that covers all the structures, the ruins, and with ArcGIS Pro, and also adds of MetaShape. We had a combination with manual classification. It's a lot of work that we did in that part, the interior part of the castle, in order to classify the ground and structural points.
Thank you.
You're welcome.
I have a question for you two. I guess that when you are dealing with quarries, there is a lot of information from the vertical cliffs that you cannot see in a ortho map or in a plan. How do you deal with that?
Yes. The vertical walls are very difficult to deal with, and the LiDAR would pick up some walls and not others. So what the processing did was simply to call it ground, and we lost any other detail in that.
Okay. Is there any chance to work with the LiDAR data in a 3D environment like Blender, or?
Perhaps. I haven't used Blender. In all honesty, I had the LiDAR in my possession 6 days before we flew it over here. So I was learning it as we were operating it as well. The data processing, we were able to get a license for Global Mapper only in the fall. So we're learning the software as well. But this conference has been wonderful because I've learned quite a bit talking with you.
Yeah, we did one experiment with the Italian data in Puglia, and we were dynamically changing the illumination, the lightning with Blender. So maybe that's an opportunity.
We've done that with the DTM, with the hill shades, and it does have some features certainly pop depending upon where you place the sun. But the quarry walls themselves, the 40 meters of vertical, we just didn't have the data that the LiDAR doesn't pick it up. But the photogrammetry does, the SFM. So again, hearing that last paper where you're blending with the, using the photographs and creating a point cloud from those is an interesting strategy to try to deal with these vertical features.
The work I saw there is a lot of discussion about the filtering of the point cloud for the issues of how filtering and so on. I think there is a very interesting paper of Michael Doneus in 2022 that is Human in the Loops. That is actually does adaptive filtering locally, automatically through AI on Python. For that is something that I think, I just wanted to mention that because it's something that I'm playing with that, and it's very, very effective, I think. Therefore, because it's able to really work on the complex topographies. And it's open source for just Python. Therefore, it's something that I thought was could be interesting for all the people struggling with filtering, including me.
Now that you say that, I also want to say that when we were working with drone data in some places like in Portugal, so the point density was so high that it was creating a lot of noise or artifacts. So we had to lower the data quality in order to have readable or data so that we could interpolate in a meaningful raster. I don't know if you had the same problem.
We tried that as well, but had we done that, we would have lost features like the post holes to the quarry road. So again, I think it probably in processing you'd want to do both and not work towards one end goal, but to have different maps to identify different features.
So you mean that you lower the point spacing of the
decimation?
Okay. In order to get smoother results.
Otherwise, it would be maybe too crispy or too.
Yes.
I have a question, thinking from a surveying perspective and especially about coverage. It sounds like you were all sort of using different equipment that had different flight times, but 60 meters is sort of a standard flight height. what are we talking about with these respective flight times in terms of coverage of a single flight? So if you have 15 minutes of flight time versus 45 minutes of flight time at 60 meters, are we talking about covering a hectare or half a hectare? Do you have a sense of that off the top of your heads?
So I'm from the University of Oslo, so I did part of the work with Evan. When we did the larger coverages, we flew at 100 meters height, and then each flight was about 2.5 to 3 hectares for one battery set.
It's more dependent on the drone than the LiDAR unit. And your...
If you're collecting photogrammetry at the same time, if you're doing the photographs and yeah, so for example, ours was able to capture photographs and LiDAR data simultaneously by stopping, taking a photograph, collecting LiDAR, and continuing. But then that was starting to impact the resolution of the LiDAR data because it was oversampling at various points. So we ended up doing separate flights. So, these things are endlessly, modifiable flight. Yeah, exactly, right? And it just depends on what you need it for.
Can I add something to your question? With 3DT Scanfly, it weighs around 2 kilos. So the flight mission is about 20 minutes with the calibrations. So the area that we cover is much. I think I have to calculate because I don't remember the exact number. But the flight plan in our occasion, it's 20 minutes with the battery set.
But it also matters on your flight plan and how much overlap you have. And if you have, we were flying in this high topography area, so we squeezed our flight plan, flight paths together, I think 50 meters apart. And I know that there's some flight paths that are maybe 100 meters apart. So the topography also matters.
The strip distance between the strips. We cover around 60%, that it's high. But we want that because we have medium vegetation, bushes and low vegetation, so in order to get more points off the ground with different angles. So that's why we decided to go with 60 meters above the ground and 60, if I remember well, 60% coverage from a strip to its neighbor.
I do have one more question, if I may. I was really interested to see in the final paper the comparisons that you all were doing, especially between the LiDAR and photogrammetry results with respect to vegetation, because we've sort of been, taught to believe that this is the kind of unique capability of LiDAR to get this kind of vegetation penetration, but it seems like you were getting quite similar results with the photogrammetry, including in vegetated areas. I wondered if other people had the same experience, if you were also surprised by that on your side, or what you think this means for how we decide to apply our tools and resources.
Yeah, so we chose probably the worst season to conduct LiDAR on Naxos, which is an extremely well-watered island. It was raining several of the days that we were there, and the vegetation was like in full bloom, right? So literal ground visibility was quite low. Now, that said, we're also working at a significantly more constrained scale, right? So when we're interpolating bare earth patches to find digital surface maps, like for a project of even like a skip size, right, where you have like an island-sized landscape and you're not looking for particular quarry marks, because we're also not dealing with quarried landscapes in the same way that Scott is, right, which are these big open areas. I mean, these were like very like easily exploited surface nodules that are getting quarried. So the interpolation that you're doing from this kind of extremely fine resolution data, is producing the kind of like messy DSMs that you're seeing there. Now that said, I mean, like several of us have said, we also were trying this stuff out for the very first time, and this is probably like not the end of our like exploration of whether or not we can like have the magic LiDAR penetration situation on Naxos, and this is why we said like going back in the autumn when things were a little bit drier and seeing if the surface topography is better there. But yeah, I mean, I think you're right. Like one of the tests that this testing that we did that said, well, photogrammetry is actually quite good now, and for surface topography, and then running visualizations with photogrammetry data that we would normally only use with LiDAR data for things like quarries is showing, you know, some really cool results in terms of tooling and extraction areas and subtle topography and stuff like that, because you're working both with zenith photographs and these oblique angles that are producing results that are not dissimilar to what we're getting with LiDAR. So it's interesting. It's surprising.
Can I just add to that? So you saw the almost entirely green field where we were comparing photogrammetry and LiDAR from 100 meters. And I think we were all a bit surprised by that. In one sense, a little disappointed, but in another sense, it's great because it means that this much cheaper tool can actually give us, in this area, in this vegetation cover, in this topography, really good data for cheaper. And as Evan said, apart from the freestanding degrees, everything was within plus minus 5 centimeters, but more than that, the vast majority was plus minus 1 centimeter, which also says something about how accurate the RTK system here is, and how good structure for motion photogrammetry has become now. So we were only using RTK. We had ground control points just as control points. We didn't use them for calculating the surface model at all. But they were also, of course, then showing very, very accurate data. So yeah.
I think if there are no more questions, let's adjourn and have a coffee break. Well, with the plan of returning for our paper at 4:45, so it gives us a little over half an hour to take a break and have some coffee downstairs. Thanks everybody for an excellent session.
My own view is that nothing has changed since antiquity except the technology. You take it through Europe to the Renaissance, from the Renaissance to the Romans, from the Romans to Greece, and you get back to Athens in about 500 BC. And then you can't go any farther in time or space for how we do things. Our whole political system and most aspects of modern life is very familiar in the period around 500 in Athens. The Agora was the center of those origins, if you will. Within the Stoa of Atlas, those storerooms are essentially a great big research center where literally hundreds of scholars come every year to look at the material we found and the records that are there. What makes it special is that everything we've ever found is in the Stoa of Atlas together with the records of its recovery. And that's very rare on this scale.
We have material from almost every single historical period. And so this makes the Agora's collection kind of a reference collection for the rest of the Mediterranean. You'll be talking about something, some piece that you find, or there's some question or something, and you'll go to John and you'll say, John, what do you think about this or that? And he's like, well, let's go look. So we're using an iPad now in the field to record all our excavation data. And then what you can do, it's very nice, you can just select an area with your finger and it'll show you all the excavations that have taken place in that area. And this became so useful to the excavators. They said it was like having John Camp there all the time, telling you what was happening. And so the nickname came about that we started calling this camping an area. So I asked John if he minded if we turned his name into a verb, and he said no.
We found an inscription, and the next thing I knew, we were down on our hands and knees, and John whipped out his notebook and started transcribing the letters on this gravestone from the 17th century.
If you ever have a chance to visit an ancient site and you can bring only one person, you should bring John Camp. And if you can bring two people, you should bring John twice. He's thinking, how can he fit this to your experience? I've seen him lecture to senior citizens and I've seen him lecture to elementary school kids, and he reaches them at a personal level.
When he speaks to a politician, he can talk about how the democracy was working here. If he speaks to a layman, like my father who came here and visited, John can tell my father, who's a do-it-yourselfer at home, about the waterworks, the pipes, construction. What John sort of can give you is the big picture.
The original Stoa of Atlas was a shopping mall, and it dated to 150 BC. Underneath it, we recovered 7 bronze discs like the ones you see here. The inscription says, Psephos Demosia, public ballot. And these are used in the law courts. And if you were a juror, you would be given 2 of these, one with a solid axle, one with a hole through it with a pierced axle. And you would hold them this way after you'd heard the case so nobody could see which way you were voting. Throw one into the pile that counted, one into the discard pile, and a verdict was arrived at. We have good reason to believe that one of the law courts of the city was right here. That's important because, as in the American system, it's the court that has final power in the state. We don't get all the pieces of the puzzle, so we get to move the pieces around and try a different story. It's constantly evolving how you look at the evidence that you have, because it's by no means complete. The primary goal is to find all the public buildings that faced onto the great open square, which was the Agora. And to do that, we've taken out 400 modern houses. And then we had to dig down 5 to 8 meters to get to the ancient remains. We still have 2 buildings and 1 street to remove, and then we will have seen all the public buildings that faced right onto the square. We're all small. We want to be treasure hunters. A handful of us continue looking for things. But by the time you get to being an archaeologist, there's no treasure involved. It's knowledge, it's objects, it's inscriptions, it's information, which is very, very gratifying. If you like to solve puzzles, this is a very good business to be in. You don't get rich, you don't get famous. You have the pleasure of working with really interesting material. You forget about it, but you're reminded at least once a week as you walk to work and look up and see the Acropolis right above you. You have to think, wow, this is a pretty good place to spend your life.
All right, we're back in business. Welcome back, everyone, to the final session of the day. We're on the home stretch of this long day, but thankfully we have an excellent lineup of papers. We'll have 2 papers, then a discussion break, and then 3 more, and that's it. Our first paper for the afternoon is going to be delivered by Anastasia Ducouri-Hild of the University of Virginia, along with her colleagues Stephen Davis, Athos Agapiou, and Eleni Andrikou. The paper is entitled Exploring the Rural Landscape of Attica Using LiDAR and Remote Sensing, the Case Study of CASP at Ancient Aphidna. Natasha.
Yes. Okay. LiDAR has been used in Greek archaeology in the last few years with increasing success, as this conference clearly demonstrates. This paper presents the result of airborne LiDAR analysis within the 2019-2021 footprint of the Kotroni Archaeological Survey Project, hereafter CASP, as part of its broader multimodal survey methodology. CASP seeks to understand the relationship between the natural and human landscape of Athena from prehistory through the present, and how such rural communities contributed to the economic, social, and cultural life of larger, quote-unquote, core centers in the region. As one of the constitutional demes of classical Athens, Athena was steeped in the foundational history of the Athenian polis, which saw in it a primordial ancestral place tied to the myths and legends. It accommodated a Middle Bronze Age cemetery, a Mycenaean or Late Bronze Age citadel, a classical Hellenistic fort on the citadel, and a geometric, archaic Hellenistic and Roman settlement. Now, we know this, of course, through the survey. Furthermore, it was later settled in the form of Byzantine and Frankish monastery estates, Turkish chifliks, Arvanite villages, and the contemporary community of nearby Kapandriti. Being that our area of interest is both remarkably well preserved due to construction prohibitions necessitated by the nearby Marathon Water Reservoir, this artificial lake we see in the image, and features a diverse history spanning 4 millennia, it is an excellent case study for human landscape inquiry, understanding diachronic inhabitation and changing meanings of landscapes in the longue durée. Important tasks in this direction have included clarifying the spatial extent, chronological framework, and nature of settlement, as well as the environmental affordances of the landscape, the combination of which permits what might be called a thick description of its cultural history. The main method for this investigation was intensive pedestrian survey. Science-based methods include geological study as well as geospatial informatics, focusing on satellite and aerial imagery, as well as LiDAR-derived digital terrain models. Here, of course, we present some of the LiDAR outcomes given the focus of this conference, arguing that airborne LiDAR holds immense promise in the study of Greek landscapes at all stages of archaeological inquiry, prior, during, and after ground truthing, especially when revisiting underexplored areas and employing a multimodal, or so-called third wave, survey methodology. The latter weaves in a multitude of analysis, both conventional and digital, and integrates old and new data. First, the how-tos. We will spare the audience of a detailed excursus on data processing here, given time limitations. Also, I'm assuming a little bit of familiarity with the processes, since the vast majority of people here have actually worked on this type of data. In brief, though, the LiDAR data was commissioned for and tailored to the CASP survey footprint through a commercial operator in Greece. The data was initially processed by Aerophoto and received in the form of a raw point cloud for the area of interest at 35 points per square meter over an area of about 24 square kilometers. Noise filtering had already been applied as part of this initial processing, but it was too harsh given the nature of the prevailing vegetation, resulting in substantial gaps of the triangulated irregular networks. This necessitated reprocessing and ground filtering of the LAS files. A gridded DTM was subsequently created using the newly processed data. Ultra-high resolution aerial images acquired in tandem during the LiDAR flight were used to produce a colorized point cloud. Subsequently, the ground filter tiles were downsampled to provide a gridded resolution of 0.25 meters or 16 points per square meter. Conventional hill shades were prepared in a GIS environment and visualized through the construction of a virtual raster. A 16-direction hill shade, sky view factor, or SVF for short, and simple local relief model, or SLRM tiles, were then built. SVF so sky view factor, is usually especially useful for the identification of anomalies where sudden changes of elevation are present, such as walls. SLRM was used to emphasize features noted in the other visualization methods. Following best practice, potential archaeological features were then mapped in a GIS environment using a combination of visualization methods, primarily a semi-transparent SLRM overlay draped on either the SVF or multi-direction hillshade in a grid-wise fashion. Digitization of potential archaeological features resulted in separate shapefiles for the area, linear, and point features that we saw in the data. In terms of some results now, probable proxies for a lost, quote-unquote, lost Middle Bronze Age tumulus excavated in the 19th century were first revealed through NDVI processing of high-resolution multispectral imagery, as well as by comparison with historical imagery. And as a note here, I'm saying lost because we, over the course of time, scholarship had lost the precise location of that tumulus, but of course it's still there. LiDAR proved very useful in highlighting suspected proxies, as well as in identifying possible features in the vicinity. Two relatively dry round areas are visible in this area, and I'm talking about these spots here. One in the east part of the unit, the other one in the west, besides the thickly vegetated stream bank. These circular marks are both visible in the 1962 and 1970 photos as well. While the 19th century antiquarian map, Carton von Attica, which is what we see here in the background, would place the tumulus roughly at the location of the western proxy, the LiDAR indicates a knoll in the area of the eastern proxy. So in this area right here. Further to the northeast of this area, a number of prominent spots in the landscape, knolls perhaps, highlight areas of interest for future research. These undulations are similar or the same features mentioned in passing by earlier visitors to the site in the late 1970s and early 2000s, most notably Hilde Stavropoulou, who's also worked at the site, and Hope Simpson and Dickinson. Consistently with descriptive information noted in Carton, at least some of these knolls could represent additional funerary remains, although not necessarily Bronze Age ones. In fact, we know that these here are probably classical or later. A sizable medieval structure was also detected in the DTM immediately east of these landscape features. This is what we're looking at here. We were able to inspect the structure, which was actually noted in Carton. You can see the outline of this building here, but remained invisible in thick vegetation only after an infamous destructive fire swept through the area of interest in the summer of 2021. It appears that this is an undisturbed collapsed medieval structure, complete with a thick layer of roof tiles sealing off the structure interior. The beneficial synergy between aerial and satellite imagery and LiDAR was clearly manifested in several other areas outside of the tumulus district. The study of old aerial imagery revealed several linear features on the west, southwest, and south slopes on the ancient citadel of Athens prior to the construction of the road leading up to the chapel there. This is the chapel right on the top. These linear features coincide with LiDAR-derived traces of terraces. I'm referring to these lines here. A rocky spur seen on the west side of the Citadel Plateau, also seen in the LiDAR relief, is at least partly a natural feature over here, but is likely to have formed part of the Citadel usable space. Aerial imagery from 1970 shows a continuation of the spur surrounding the Citadel slope along the northwest, southwest, and south sides over here, clearly delineating the Citadel and extending below towards the plain to the southeast. There does seem to be a possible break in this rocky outcrop in the southeast corner of the Citadel over here, defined by large, seemingly natural boulders, which is conjoined with an alternate, perhaps earlier ascent to the top. In addition, over 25 kilometers of linear anomalies were identified using LiDAR. And here we are showing you only just the most important ones. There are literally thousands of these. By far the most common category were terrace remains, including some likely recut examples around the citadel itself, and others less visible examples. The latter, now hidden in dense vegetation, are likely to be of greater antiquity. Some of these terraces identified through LiDAR were used in the field in 2019 for optically stimulated luminescence sampling and eventually produced dates ranging from prehistory to the Frankish era. So the LiDAR really saved the day there, made us immediately identify which terraces were most prominent and just go to these and target these specifically. On the Gurma and Riomeni hills, southwest of the citadel, an artificial-looking, at least partially artificial-looking L-shaped plateau was identified in an area hidden in Maki. This is this feature I'm talking about here. Ground truthing revealed a largely, roughly dressed in-situ wall with 3 to 4 courses on the east side of this feature over here, hiding in the bushes, with additional lines of loose boulders extending to the east, all the way down to the modern path in this direction. Significantly, this tract is situated just north of a series of survey tracts which yielded an abundance of prehistoric finds. And just for reference, this area I'm talking about is right here. Visual inspection of the DTM helped identify likely enclosed build structures as well. For example, rectilinear anomalies consistent with a large building or enclosure were identified in a thickly overgrown and inaccessible area south of the Gurma-Driomeni hill. Right here, you can see the outlines of something here and perhaps also nearby on the north shore of the lake. These coincide with faint, barely noticeable initially linear vegetation proxies in the 1962 imagery. You can barely see those here. None of that is visible in the more recent satellite imagery, however. Once again, highlighting the importance of comparing different data sets. Additional substantial enclosed structures have been identified in other areas covered by LiDAR flight, but not included in the 2029 and 2021 survey footprints. Is a good example of that. We're not really sure what we're looking at here, but it's some kind of enclosed or carved structure, and it's just at the edge of even the LiDAR data set. So there's plenty more to explore in the future based on the data we have collected. To the north of the citadel, we detected the subtle remains of a likely northeast-southwest oriented structure that is completely concealed by vegetation, associated with terrace walls and fronted by an artificial-looking plateau. I'm referring to this kind of jagged line, which seems to have orthogonal corners here, possibly a well-built terrace wall or something of that nature. The location of these proxies is immediately west of a survey tract that produced abundant pottery dated to the classical Roman eras, as well as several moved orthogonal building blocks pushed to the size of the tract in recent times, could suggest that the portable finds and the blocks emanate from a possible structure somewhere over here. And as a reference, this is the distribution of some of these blocks and the area, the tract that actually produced all that pottery. The LiDAR combined with historical imagery was also useful in documenting known monuments, such as the Agia Saranda Chapel area, which is seen in the LiDAR right here, and which stands in place of an earlier chapel and even incorporates more ancient building remains from it. This area yielded abundant surface finds dating again to the Roman and early Christian eras during the survey, but has been unfortunately disturbed by invasive earthworks as part of the chapel's renovation in recent years. The historical imagery shows a likely proxy for a large structure, we don't know the date, possibly medieval, possibly earlier, which is actually noted in Carton. And here in this image, I would encourage you to squint and look at the fine outline in the back, the red lines that we see here. So it's a long structure that has some kind of enclosure on the south side of that. Now, this is also seen in the composite image of LiDAR and the ultra-high resolution orthophotography, just immediately south of the cultivated zone in this area. So we see something is going on here, perhaps blocks that have been pushed aside since and are now defining the boundaries of some of these tracts. Importantly, the combination of various data sets has produced tantalizing details unknown to the meticulous surveys and authors of Carton, Curtius, and Cowper. For instance, the rectangular plateau south of the building they noted, this area right here. This detail could suggest a larger structure than previously suspected, or perhaps some kind of additional structure hiding in the lush riparian vegetation by the lake shore. Finally, we were able to better document the condition of an extent of a standing Frankish tower at the Pyrgos locale on the southern edge of the Athenian peninsula fronting the Marathon Lake, using a combination of LiDAR, ultra-high resolution aerial imagery, satellite imagery, and ground truthing. This building is oriented northeast-southwest, rising to an approximate height currently of 2 meters. while the eastern part was depicted in Carton, and we can see traces of this remain right here, today is quite dilapidated. Nevertheless, it is now clear that originally it formed part of a wider structure that included an outer boundary seen in the LiDAR. So this is the corner of the tower, and this is the boundary I am referring to, combined with the 2018 aerial imagery and World Review 2 imagery from 2010. And so this is WorldView. This is our ultra-high resolution aerial photography from 2018 that was co-registered with the LiDAR data. An additional piece of evidence was actually furnished by a 1920s ground photograph of the locale that was recently recovered in the archives of the Greek Water Authority, or AVAP. And here again, you can see the tower, but also the surrounding ancient or peribolos that actually defined this feature. So some of the challenges and limitations encountered in acquiring, processing, and deploying LiDAR data in the field have included the high acquisition cost, of course, of ad hoc airborne LiDAR, combined with the lack of extant governmental data sets available freely for research purposes, currently at least. The large data size of the files requiring down sampling for day-to-day use in the field, especially in an online cloud-based GIS, which is what we did. We used the AGOL platform. And the necessary vetting of LiDAR data by the Greek army. Although some of our data was trimmed during the vetting process to protect certain areas of strategic significance, fortunately the impact was not significant because it did not interfere with our survey objectives. However, the benefits have been manifold, and the heuristic value of LiDAR in our project was not diminished by these challenges. Multimodal investigation combining traditional methods has permitted novel insights into the broader Athenian landscape beyond the citadel. The combination of all these data sets have produced evidence of several rectangular, circular, and linear features, including terraces, as we see, building fragments, possibly the tumulus, and also the integration of this imagery in a GIS environment allowed for a better understanding of the defensive qualities of the citadel, especially the west and south sides. The synthesized data were useful in all stages of the project. Having the data available before even setting foot in the field allowed detailed logistical planning, for instance, by gauging accessibility, barriers, or other limitations, and person-hour and time requirements. The combined data also guided the detailed drafting of tracts ahead of time, taking into account a variety of factors such as cultivation type, natural or man-made boundaries defining the tracts, topographic characteristics, and elevation difference between tracts. Further, they permitted the formation of initial hypotheses, for instance, in comparison with Carton, and the tentative identification of high-interest areas suitable for detailed field-based exploration. The integrated data further helped identify earthworks for sampling ahead of fieldwork based on accessibility, preservation, and topographic factors, and to complete this aspect of the project in a timely and efficient manner under time pressure. During fieldwork, the data permitted further scaffolding and refinement of CASP inquiry. They served as a springboard for forming and testing new hypotheses about detected or suspected archaeological features and allowed digital glimpses into areas that were deeply concealed by vegetation and impossible to access even take a peek at while on site. Finally, upon the conclusion of fieldwork, these multi-layered data were used to evaluate artifact distributions and the find spots of loose architectural membra throughout the survey, guiding a holistic and diachronic interpretation of the Athenian landscape. And with this, I end, and thank you so much.
Thank you. Thank you very much. And so we have our second paper also online. Konstantinos, are they ready? That paper will be the LiDAR survey of Agraphia in Boeotia, methodology and first results given by Thierry Lucas.
Okay, can you see the screen?
Yes.
Okay. So following Jesus' general presentation this afternoon on the LiDAR surveys conducted under the aegis of the French School at Athens in Boeotia, I would like to focus with more details on one specific site by presenting the research that I recently led at Agraphia using a LiDAR-based survey to study the urban layout of this relatively unknown city. The general aim of my communication will be to present briefly the site and the results of this project, as well as the methodology that I use to achieve the results. For the presentation of the site, you can see here a general map of the region, and Akrefia is a small to medium polis located in the northern part of Beotia, in a landscape that is deeply shaped by the lakes, and notably the Copais Basin. Due to its very modest size, it is not frequently mentioned in the sources, but compared to other cities of the same size in Beotia, Akrefia had a regional influence owing to the presence on its territory of the oracular sanctuary of Apollo-Ptoios. A more detailed presentation of the Cora of the city shows the relation between the Asti itself and the Ptoion, about 1 hour of walk from there. In between lies another extra-urban sanctuary, the sanctuary of Kastraki, dedicated to one hero, Ptoios, which worked in close relationship with the more important sanctuary of Apollo. In the following communication, I will deal only with the urban center of the city, on which the LiDAR survey was focused. So first, we know very few on the city of Akrefia from the written sources. There are only 2 mentioned by Strabo and Pausanias. An interesting point to note is that both authors emphasize the fact that the town lies on a mountain, which corresponds to the topography, but also means that it was an important feature of the urban layout. Another point worth mentioning in the text of Pausanias is that he avoids the term polis and uses instead polisma, thus characterizing Akrefia in Roman times as a very small-scale settlement. From the 19th century onward, the site was frequently visited by travelers, for instance Leek, attracted by the numerous inscriptions reused in the medieval church of Aiosiorgios. Among the 19th century descriptions, a special mention must be made of the very comprehensive description provided by Lolling in his notebook in 1876 or 77, which includes, for the first time, some graphic documentation with a sketch of the wall and some drawings. The École Française d'Athènes has been involved in the region since the 19th century, with the early research led by Maurice Solo at the sanctuary of Apollo-Ptoios. The French excavation in the region also led to an interest to the epigraphy and archaeology of the city itself, leading to a first excavation in 1936 led by Pierre Guillon and Michel Fayel. This excavation, here represented on the orthophoto, did not yield any significant results. Guillon and Fayel thought they had found the site of the agora, but there are no clear elements to substantiate that claim. This early research led also to a first map of the city, unfortunately unpublished, showing mostly the course of its fortification. In 1965, a small excavation was led by Yvon Garland on the city wall, which led to the discovery of one of its towers, pentagonal in shape. Last, in the 1990s, Christel Müller made an extensive study of the city and its territory, for which several maps were produced for the territory, the sanctuary of Apollo, and the city wall, with a much more accurate result than the previous attempt. A last important fact to mention is the large-scale excavation on the necropolis of the city, led from 1974 to 1996, mostly by Angeliki Andriomenu. More than 2,000 graves were excavated, in total in several phases, making the necropolis of Akrefia one of the best known in this region. As you have noticed, the documentation of the site is quite lacunar. We have a very clear picture on the necropolis, a general map, and basically that's all. Almost no remains have been clearly identified, and the city wall has been often described, but lacked a full study, and that was the main project I carried out at the French school from 2019 onwards. However, the situation on the ground is really bad. All the Acropolis is covered by dense shrubs with persistent leaves, giving a very low visibility on the ground. Because of this, and also because of erosion, on the higher part of the hill, a survey was almost impossible. After a visit on the site in 2019, John Bintliff suggested using LiDAR to have a clearer view of the city. To achieve this, LiDAR data of the Acropolis were acquired in 2021 thanks to a contract with the company Aerophoto. This is what we could call an intensive survey, the aim being not to identify new extra-urban sites, but to focus on the Acropolis and its surrounding. During the same mission, another site of Boeotia was covered, the Vale of the Muses, near Thespiae. Let's now turn to our LiDAR dataset and the treatment used to reach some results. In 2020 and 2021, I took advantage of the COVID crisis to learn how to treat the LiDAR data by myself. One of the secondary aims was to provide a full workflow, if possible, using only open source software to process the dataset, from the raw LiDAR data to the final visualization. And I must thank here Jesus Garcia Sanchez for the valuable suggestions and advice. The first step was to choose a method to filter the ground points, as the data provided by Aerophoto were raw last data without classification. Several articles have been devoted to benchmarking some of the algorithms available on the market. I quote here one of them by our Slovenian colleagues, Ediza Lozic and Benjamin Stular, specifically devoted to archaeology. But I felt that I had to make my own experiments due to the context of Acrafia, with dense low vegetation and important variations in slope. Among the algorithms I have tested are TIN from the well-known LastTool software, Whitebox slope-based filter, PMF, MCC, and WLS. As you can see, the two algorithms that perform the best to remove low vegetation were Whitebox implementation of the slope-based filter and the progressive morphological filter. I retained Whitebox solution owing to the fact that PMF had a strong tendency to introduce type 1 errors by erasing crests and slopes. The treatment was further improved by applying 3 successive iterations of the filter of the dataset with different parameters. In turn, the choice of the algorithm decided the software to use. QGIS for the GIS software, the free part of Whitebox for the LiDAR treatment and DFM generation, QGIS plugin Relief Visualization Toolbox for some advanced visualization methods, and QField for ground truthing. All of them are free and open source software and can be used as QGIS plugins, which makes the whole process coherent. Let's now turn to the results of the LiDAR survey. This is currently a work in progress, but you can find some preliminary remarks in the 2 field reports we published with Jesus Garcia Sanchez. For Acrafia, the LiDAR data also provided the backbone of the thesis I submitted to the French school at the end of my stay. One of the reasons that led to the choice of a LiDAR survey was the presence on the satellite imagery of lines clearly visible on the vegetation and of heavy terracing works that still mark the landscape today. However, the LiDAR data from Acrafia gave spectacular results, much better than anticipated. On this picture, you can see the DFM with linear structures that clearly pop out. First, we can focus on the northern part of the Acropolis, the northern slope of the hill. The first thing that is visible is a set of 8 evenly spaced terraces oriented east-west. These terraces are cut by north-south axes that are much more difficult to read, but that were definitely there. Given the topography, we have to suppose that these north-south streets consisted of stairs, and in fact, there are 2 specific spots where such stairs, one of them carved on the rock, are still visible today. So we have here the case of an orthogonal grid directly adapted to a slope. From place to place, this orthogonal grid is interrupted by diagonal streets, probably intended for heavier traffic. Another important feature on this northern slope is a large trapezoidal terrace at the bottom of the urban grid. On its center, several traces of smaller terraces or foundation of large buildings can be seen on the LiDAR data. It must also be noted that all the major traffic routes of the city converge towards this area. There can be little doubt that this was an important space in the city, and I believe that it was the Agora. This interpretation is further confirmed by a large circular depression on the western part of this terrace, which was the theater of Acrafia. This theater is attested by epigraphical sources, but the LiDAR survey allows us to locate it on the ground. It is rather small, with 30 to 40 meters of diameter, but this is what can be expected for such a small city. Other traces can clearly be seen on the Acropolis plateau itself. It includes a city wall, which can be traced quite accurately, even in places where there is no remains to be seen, but also, here again, an orthogonal grid. In the central part of the Acropolis, this plan is very regular. The persistence of this grid on the ground can be explained by the fact that the Acropolis plateau is not exactly flat, and here again, the builders had to create terraces to set up their plan. In the central part of the plateau, where erosion was less severe, these terraces have been preserved in the topography. Lastly, it must be noted that there are traces also inside the grid which correspond to buildings, maybe houses. One can note, for instance, a cistern cut on the rock and several linear features inside the urban blocks. Another benefit of the LiDAR data is that it gives access to a high-resolution DTM that can then be used for other purposes, for instance, to estimate the least cost path between various points of the city, and thus to assess the mobilities inside the town. For this, I used an approach developed by my colleague at the French school, Sylvian, whom I thank here, the cumulative focal mobility network. This approach, during ground truthing, led to the identification of some important stretches of the ancient road that link the Acropolis with the lower city. The main difficulty with the LiDAR data is that without any other elements, they give only one picture, which is in reality a patchwork of several phases. For instance, there were two distinct urban grids, one on the northern slope of the hill and the other on the Acropolis plateau. They do not share the same orientation. Do they correspond to two different phases of urban development? Did they work together? These are questions that need other elements to be answered. We have therefore to turn to other clues to better understand the evolution of the ancient town. One of them is the city wall. Its main phase consists in a large circuit, mostly built in isodemic ashlar or trapezoidal masonry, here in orange. An interesting point to note is the distribution of towers along the wall. In the southern part of this course, 3 towers can be identified, either through traces on the ground or through the presence of a small postern already mentioned by Lolling. It seems that the towers are synchronized with the urban grid, one north-south street out of 2 leading to a tower. The 2 projects were thus connected and are probably roughly of the same date, which allows us to connect the main phase of the urban grid with the construction of the wall as expected. This leads us to the conclusion that the main phase of occupation of the Acropolis should be dated to the early Hellenistic period. After that, the town probably declined and shrunk to the northern slope of the Acropolis. The result from the LiDAR survey at Acrafia, combined with the architectural survey of the city wall, provide us with new insight on the urban layout of a Boeotian average polis. This survey shows the relevance of an intensive LiDAR survey on an already known site to better understand its topography and organization. I thank you for your attention.
Thank you, Thierry. Can we get both speakers back on the Zoom and we'll have a short discussion before, we have 7 minutes, I think, before we start again? No, 10 minutes.
Even 12.
12 minutes. So questions for the first two papers here? Yes, Jakob? No, you need the microphone so that they can hear you on Zoom. It's especially necessary in this case.
Actually, it's very true. I have a question for the first speaker, actually. I was just curious because the OSL dating of the terraces. I was curious if you were actually able to identify different typology of terraces from LiDAR and then connect different OSL dating and maybe try to have a different chronology for different type of terraces. I'm asking because it's something that I'm trying to struggle with a little bit in the central Apennines with very alternative results, to be honest. But I was curious if, in your case, LiDAR allow you to identify specific types that then you data to specific periods, maybe.
No, actually it did not. So the only way in which LiDAR was helpful to us in that regard is simply just identify where the well-defined terraces were that were likely to not have been, say, the result of recent earthworks, because there's also a lot of recent ones there. In fact, in many ways, the dating of the terraces defied our expectations. So we didn't expect to find prehistoric terraces, and we were greatly surprised when some of them proved to be Middle Bronze Age. And these are all terraces that are probably undefined in terms of stone structure. So it's just the earth that has been piled up over the years. So far we can't say that there's any typological difference, let's say, that might establish a chronology based on the LiDAR. It's mostly the lab analysis that told us that.
Thank you.
Other questions? I was interested that both of these papers were making quite extensive use of historical documents, especially maps, and the Karten van Attica in the first paper, and plans drawn by visitors in the second paper. And that makes me think about more systematic ways to combine remote sensing-based spatial analyses with historical materials in the documentary record. And I wonder if I might put Syl Fachard on the spot a little bit, because I know that he's been working on a big project related to digitizing the Karten van Attica materials for some years. And I wonder if he's thought very much about, or even worked actively on combining that digitization work with different forms of, contemporary remote sensing.
Yeah, thanks, Alex. Well, I've been working with the Karten van Attica for a while now, but we couldn't use them for the Mazi survey because the German topographers just stopped 100 meter south of the Mazi plain, so we couldn't use that source of information. But for the rest of Attica, I've been using it for some time, and I combine it with DMs and 3D visualization, and it helps a lot. Of course, now there's a DPLON. I'm associated with the DPLON project for the Karten van Attica online. And for those of you who don't know about the project, I really encourage you to go and check it out. It's a wonderful web GIS project now. So all the Karten van Attica are online, freely available. You can zoom in. You have digital imagery too there. And what they did is that all the commentary in German have been translated into Greek. And you can really click on each feature within Attica, and you have the Greek text and the German also text. So it's a wonderful tool now, and I really encourage people to use it, especially those who work in Attica. For other regions, we have, for example, the French Morea mission, Mission de Morée, as you probably know. That was actually before the Karten van Attica. It was a continuation of the Morea cartography project done by the French mission, and it was extended to Boeotia up to Thessaly. Now, they only produced one by 100,000 map scale, but in Paris, I've been working for several years now with the minute, so the individual maps, drawings that have a higher scale, and I've been using them in Ubea, and they're absolutely incredible. So I use them with the LiDAR data to as a layer of information, and that helps a lot, especially for roads, because all these paths and roads were used before dynamite and bulldozing and all of this. So you have a wonderful layer of information there for communication. I could go on. I don't want to tire people, but yes, obviously, whenever you have this, amount of data in your region, you should definitely use it. And don't overlook it because it's a treasure.
And I must say, if I may add to that, Sil, I was really surprised on some level that Carton proved to be so incredibly accurate. In my experience, I didn't have to do much rectification to actually make features align. So it's truly exceptionally accurate.
Rosie Campbell had her hand up a moment ago.
Sorry, it was just to add to that. There's a lot of work happening in historic maps and using them for detecting, especially using machine learning, archaeology and heritage in South Asia, run with Professor Cameron Petrie and Hector Orengo as well. And they've been working on that, I think, for some 10 years now or so. I think we've georeferenced something like 2,200 maps from the Survey of India. Obviously, we're quite lucky in South Asia that we have these excellent survey maps for the whole of the subcontinent in a very high scale. But it was just more of a comment to say it's an extremely valuable resource if it's possible to, and you'd be surprised what kind of archaeology from early Bronze Age can exist on them. It's yeah.
Will?
Yes, also I just wanted to thank you, Alex, for bringing that up with historical records, because this is also something that I wanted to bring up. One brief addition, of course, concerning the Karten Fanatica. Just coincidentally, I was reading up on Hans Lohmann just last week, and he was basically saying, who of course worked extensively with the Karten Fanatica years ago, and basically saying that they missed a lot. And I was wondering whether your research now with that detailed region could actually add to what they could actually survey back then, because they were not archaeologists in the end. They were engineers, or they're going through a military career, and they had to survey everything. So and this is something that I think I forget the statistics. What Lohmann was able to come up with, but I was interested in whether you could add to the Karten, and also just a shout out to Isan Habo Lolling, who's been everywhere in Greece, and also including the Kephissos Valley. And so on the way to the Kephissos Valley, running through Boeotia, and we could also very much share the same experience, basically, that so whatever he could record, we could also see with our modern methodology, we could confirm that. So yeah, just a brief question and a comment, I guess.
Sorry, is this a question for Sil or for us?
For you.
Okay. Yes, I mean, I think we shouldn't delve in the idea that these early maps are nostalgically perfect, a fiction, let's say, of a perfect past that was preserved in these maps. Of course, there's a lot of things missing, but at least in the experience of my survey, again and again, there have been cases where I was just surprised by the accuracy of the representation. And I'll give you one more example that I didn't really talk about today. When we surveyed in 2021 the southern part of the Athenian Peninsula, Carton was noting marmor blocken, so small marble pieces, and they were referring to chips of marble that were found distributed throughout the area. And that area in 2021 were still replete with these kinds of little marble pieces. So maybe they weren't perfect at defining, the nature or the characteristics of what they were seeing, but they were really good at putting down on paper what they actually observed on the ground. And I think in that regard, it's tremendously valuable. So yes, whenever that map is available, I would say absolutely look into them.
And one thing I could add about Lolling's drawing is that in my experience at Acrefia, the sketches are wonderfully accurate. So we could identify several spots of the walls that he saw and drew. And also the general map, it's only a sketch, but we must keep in mind that the vegetation is becoming worse and worse in these last decades because of the lack of pasture of animals on the Acropolis. And so we must be aware that Lolling saw things that are no longer visible because they are overwhelmed by vegetation. And so he notes some very valuable information on parts of the walls that are now completely lost under vegetation.
Well, thank you very much for our two speakers and questions. I think we'll move on to our last session, which will begin with the paper, Seeing the Trees Through the Forest, LiDAR Analysis and the Identification of Ancient Sites in the Busy Built Environment of Southeastern Rhenia. And the paper will be by Zosia Papadopoulou, Vangelis Samaras, Pavlos Philaktos, and Alex Knodell.
Thank you for inviting us to participate in this very interesting workshop. Dear colleagues, I changed. Rhenia, or Megales Diles for the Myconians, was a place with a special history in antiquity. Part of it belonged to the territory of Delos and functioned after the two Athenian purifications as a cemetery and birthplace of the Delians. At the same time, in Rhenia, there were 10 farmsteads that belonged to the Delian sanctuary of Apollo, along with 2 sanctuaries, one dedicated to Artemis and one to Dionysus. The ancient city of Rhenia was in the northwestern part of the island, with its sanctuaries, cemeteries, farmsteads, and various sources of wealth. Limited but important excavations in Rhenia were carried out in the late 19th and 20th century, included at the pit of the purification of Delos, while investigations in the Delian necropolis were also carried out by the French School of Athens in collaboration with Hellenic Archaeological Service. Despite the obvious importance of the island, it had not become the subject of systematic research until the beginning of the Rhenia Archaeological Project, RAP, in 2019. RAP is a research project of the Ephorate of Antiquities of the Cyclades, with the participation of French School at Athens, several Greek universities, and the University of Napoli. Some of the key concerns of this project are the boundaries of the territories of ancient Delos and ancient Rhenia, the identification of the farmhouses mentioned in the Delian inscriptions, the extent, topography, and chronology of the Delian necropolis, and the location and extent of the estates of the sanctuary of Delian Apollo and of the two Delian sanctuaries on Rhenia. To date, almost 500 structures from various periods have been recorded in the course of survey, including farmhouses, towers, burials, possible port facilities, stables, threshing floors, wells, roads, quarries, metallurgical galleries, etc. The number of pottery sherds counted is now close to 108,000 sherds, of which 6,000 have been collected. A more detailed investigation of areas of special interest will be carried out after the completion of the survey. This is already in progress for the area, in the area of the Delian necropolis. having as a result the creation of a database with more than 5,000 records, structures, walls, architectural members, columns, altar bases, sarcophagi, etc. LiDAR data. LiDAR data acquired in 2022 provide a tremendous set of resources, but also invite a range of new questions. We have followed the program of LiDAR classification and analysis laid out previously for elsewhere in the Cyclades in collaboration with Alex Knodell and students from Carleton College. The island was divided into analytical units of 500 by 500 meters, where analysts traced feature lines and classified the data according to the methods presented earlier today. We are very grateful for student research assistants at Carleton College who honed their GIS skills, tracing and classifying nearly 3,000 individual features. Several general trends can be observed. In the first place, the built environment of Rhynia is denser than just about anywhere else in the Cyclades, with the possible exception of Delos. The LiDAR data shows an exceptionally rich built environment with 341 kilometers of terraces, field walls, and other constructions covering its relatively small area of about 14 square kilometers. The initial classification showed some 245 kilometers of field walls, 39 kilometers of terraces, 123 threshing floors, 405 buildings, 148 roads and paths, and dozens of other features and areas of interest, several of which may represent the signatures of buried ancient structures. The LiDAR mapping of the area of the cemetery, for example, is stunning and provides an opportunity for comparison with excavation data and traditional mapping, as well as different types of remote sensing. Across the island, many features clearly date to the modern period, but many are also ancient. Differentiating between the two is a major challenge, especially since reuse of foundations of older construction was likely quite usual in the landscape. Nevertheless, the preponderance of agricultural features shows a rich history of habitation and agrarian use, while the cemetery, towers, and sanctuary features shows multiple specialized uses at particular sites. The remainder of this paper focuses on three areas from the southeastern part of Rhynia. In the first place, we examine the boundary zones of the Delian necropolis. Second, we look at two sites close to the southeastern end of the island. One is a small building near what may have been one of the access points of the island at the Bay of Philadi. The other is a small ancient farmstead close to the Bay of Pikragouria at the southern part of the island. One of the major research questions of RAP concerns the extent of the Delian necropolis and its relationship with the activities or areas surrounding it, in particular the farmsteads that could possibly be identified with some mentioned in the Delian inscriptions. Another important issue is the access to the necropolis and the communication with the rest of the island. Thanks to RAP's systematic research in the necropolis, it is now clear that its extent is greater than originally estimated. Its northern end reaches as far as Cape Claropunda, where a large stepped monument is visible. Ken described this as a lighthouse, but both its position and the discovery, both its position and the discovery of a funerary inscription near it argue for its funerary character, possibly a heroine. As in the north, so in the east, the natural boundary of the necropolis is the sea, which here has covered the eastern end of at least 20 meters due to the rise of the sea level. As far as the southern boundary of the necropolis is concerned, it seems to extend well beyond the Bay of Catu Generale, as was believed by earlier scholars, and appears to extend to the foot of the hill Dubari, north of the small cove of Philadi. Indeed, it is likely that both buildings located at the top of this hill, a circular one with a diameter of 4.5 meters and a rectangular one 20 meters further south, are connected to the cemetery, acting very probably as the southern boundary of it. The form of these buildings and the existence of marble fragments in the area exclude agricultural use and suggest the existence of significant monuments on the summit, reinforcing their connection with the cemetery. These two structures are visible in all high spatial resolution data of the visible RGB spectrum. However, in cases of low quality data, such as Google Maps, the second building is difficult to identify. Sorry. As far as the DSM and DTM data are concerned, the circular one is perfectly distinct with great clarity, especially as regards its shape. The latter is presented, as in other cases to be seen below, as a protruding area or a small tumulus. The similarity of this shape supports the case for the creation of patterns identifying ancient building remains across Rhynia. The western boundary of the necropolis is more difficult to determine precisely, as things here are more ambiguous due to modern agricultural activity. It was originally assumed that the boundary of the necropolis was almost identical with a modern field wall running from north to south to a distance of 150 meters from the sea. However, burial structures are also present further west of this, as far as the hill of Homasovouni, where it has been assumed that the location of the Artemision and Niso of the Delian inscription is located. We note, therefore, that the sites of the necropolis that do not reach the sea are marked around by peaks with monuments that should have been visible from sufficient distance. The Glaropouda Hiron to the north, the monument of Homasovouni to the west, the building at Tubari to the south. Another interesting observation is that the necropolis was accessible by sea from many different points as it is today. Two bays on the north and south side of the necropolis seem to have functioned as access points to it and to other parts of southern Rhynia. The first is the Bay of Philadi, which is the most southeastern landing point on the island, especially when the weather is rough and the passage of the Marmarokopio Cove by small boat is difficult or even impossible. Associated with the access control in this bay is possibly the building that was identified during our survey in 2021 at a distance of 20 meters from the coast of Philadi. It is of relatively large dimensions and more than one rooms are distinguishable. The abundant pottery found around it, which includes many fragments of amphorae, indicates its dating to Hellenistic times. Some of its walls are clearly discernible in all visible spectrum, RGB, based backgrounds. Nevertheless, in the LiDAR data, the structure is quite difficult to detect. Sorry. 50 meters south of the building, an ancient marble quarry is located. It is worth mentioning that the quarry is clearly visible in the visual data RGB, as well as in the DSM and DTM backgrounds. Especially in the latter, the large anthropogenic fronts resulting from the quarrying are evident and are very differentiating from the nearby environment. A building similar to the one in the Bay of Philadi was found last summer at the north boundary of the necropolis, next to the Cape Glaropunda. This building is not distinguishable in the visible spectrum data, but it is clear in the DSM and DTM LiDAR data as a small outcrop of irregular oval shape. On the other hand, A large wall is distinct in all types of data because as a straight section of great length, it is differentiated from its immediate surroundings. About 200 meters north of the small but safe bay of Picragouria in the southern part of the island, at an altitude of 25 meters, parts of a building can be discerned, which probably dates to the classical and Hellenistic times. The visible architectural remains do not allow the identification of rooms and a clear understanding of its architectural characteristics, but in combination with the topographical observation and the surface pottery, the site can be identified with a high degree of certainty as a farmhouse. This feature can be identified in all the remote sensing data applied to date. In the LiDAR-derived DSM and DTM, the building appears as a small outcrop, which on its southern side creates small plateaus. While in this case the masonry is not apparent, the anomaly is nevertheless significant, and field observations provide chronological information that may help us to identify chronological patterns. About 200 meters northeast of this ancient farmhouse and 50 meters higher is a modern farmhouse, a χωριό in local parlance. The comparison of this χωριό with the ancient farmhouse allows some observation about the settlement and agricultural organization in Rhynia over time. Both ancient and modern farmhouses are generally located not on the coast, but on one of the low hills of the island, and are positioned in such a way as to ensure specific features. Firstly, the provision of drinking water by a variety of methods, such as collecting rainwater in cisterns and digging wells, and some very large pits in the ground, laches, with a sloping side to provide water for livestock. Secondly, access to the coast, as communication with the world outside Rhynia for all imports and exports took place exclusively by sea. Even within the island, communication and transport in many cases is even today easier and faster also by sea. Thirdly, the loss of the least possible land suitable for agricultural purposes. Thus, for example, we observe that the ancient farmhouse here in Picragouria is placed very close to the stream that leads to the bay of Picragouria and at the edge of the flat and arable land, while the modern χωριό is placed on a small plateau on the top of a low hill above the bay and exactly at the point where the rocky and uncultivable land begins. In areas where these elements are readily available, two or more farmhouses may be located within a short distance of each other. However, the norm is that the farmhouses were isolated and relatively spaced apart from each other. On the other hand, it seems that during the classical and Hellenistic periods, as well as during the last centuries, there were not a few large farms, but many relatively small ones. It should also be pointed out that the production of Rhynia was not limited exclusively to agricultural and livestock products, but other sources of wealth were also exploited, as is shown by the iron mines and the quarries of gneiss, granite, and marble, as well as the exploitation of purple mentioned in the ancient inscriptions. This way of dividing up the land and organizing production resulted, at least during periods of intensive and systematic use of the island, such as those to which we are now referring, in its entire area being exploited, supplying Rhynia itself, as well as its powerful neighboring islands, initially Delos and now Mykonos. To sum up, in the case of Rhynia, comparing field observations with LiDAR data show that field observations cannot always be cross-checked with LiDAR data, and that LiDAR and surface survey are best viewed as complementary techniques. This is particularly evident in the area of the necropolis, where the systematic mapping of the visible remains offers a very good picture of its organization, but the LiDAR data reveal that there are many more elements that must be await the archaeological investigation to come to light. Also, in the case of several sites, such as ancient or modern farmhouses, LiDAR data can provide a lot of additional information that was not documented in the field and can provide valuable information on the organization of the agricultural economy, production possibilities, and more. Regarding the analysis of archaeological features, in areas with low vegetation, such as Rhynia, visible spectrum data play an important role as well, as it enables the identification of most of the ancient structures found during survey, a practice which is extremely difficult or even impossible in areas with dense vegetation, as in forested areas. In the present study, LiDAR is very useful in the observation of ground anomalies, which may be largely the result of human intervention. Therefore, the individual researcher can be trained in the recognition of patterns of ancient structure, which is a very helpful tool to use in the course of fieldwork and interpretation of the landscape. In conclusion, it should be clear that various types of remote sensing form a set of complementary tools which can supplement and guide but not replace archaeological fieldwork. At the same time, LiDAR analysis has identified several areas of interest that need greater attention in the field and that were not apparent through other methods. Finally, the study of remote sensing data across the island as a whole yields quantitative and comparative insights into patterns of land use and the built environment. Thank you very much.
Thank you very much. We'll move to our next paper, which is LiDAR analysis and phasing at multi-period sites in the Cycladic landscapes, examples from the islets of Amarynthos. Rosie Campbell will deliver the paper, and the co-authors are Dimitris Athanasoulis and Alex Knodell.
Thank you. As mentioned, I'm Rosie Campbell, and good afternoon, or I guess evening it almost is now. Is this going to... Okay, so in keeping with the other papers of this session, we focus here on the analysis of LiDAR data at the scale of archaeological sites. This is partly inspired by the work of some others in this session, and then also by presentations that we saw in Vienna at the Mediterranean Survey Workshop, and also by Neve and Michael Dunas, and where they presented on the detection of phasing at multi-period sites in Croatia, which we saw a little bit on earlier today. At that conference, and as well as at the Archaeological Institute of America's annual meeting, we presented the initial results of our fieldwork from 2023. The present paper also relates to a wider program of research led by one of us, Dimitris Athanasoulis, concerning Byzantine Cyclades. Previous work inspired us to see what we could actually do better to address issues of chronology and phasing using LiDAR data at multi-period sites as documented by SCIP. So in particular, we really wondered about the effectiveness of chronological interpretations for different periods, and whether the environmental circumstances of the Aegean Islands, being very much less vegetated than other environments, especially those documented by SCIP, might allow us to make more subtle interpretations maybe of complex built environments using LiDAR. So at this point, team members have already presented the general parameters of the project. So we'll just note here the place of this paper in the wider program of LiDAR analysis. One of the key goals is to collect data that allows us to investigate archaeological questions at a number of different spatial and conceptual scales, ranging from the artifact to a building, to sites, to individual islands, and then of course to the entire region of the Cyclades. Here we're focused on archaeological features and sites in the vicinity of Amarynthos, and in this paper, we combine different data sets to analyze multi-period sites featuring mostly dry stone architecture. The objective is threefold. Firstly, to construct a general stratigraphic sequence of the built environment, Secondly, to detect possible signatures of walling from different periods. And thirdly, to better understand how site reuse and continued occupation across periods affects the preservation of architecture, as appeared in LiDAR. We examine LiDAR data and aerial imagery alongside ceramic and other finds from the survey in order to examine whether phasing and chronological information can also be inferred from particular remote sensing signatures. And to those ends, we present 2 comparative case studies from 2 different areas, and in total 3 islands. The first is from Anidros, where the 2 main sites on the island show complex phasing, and the second comes from Antikyri Islands, where each island sports complex sites surrounding churches. But Kato Antikyri has a much longer history of reuse into the present day, while Ano Antikyri has seen little subsequent development. So on to Anidros, which literally means without water, is perhaps the most remote island in the whole of the Cyclades. It's located 18 kilometers from Amorgos. Anidros is also about equidistant between Anafi, Santorini, Ios, and the small Cyclades, which are each about 25 kilometers away. And if you can see it right there. All of these islands can be seen from its central plateau. It's got an extremely commanding view. And topographically, the island is divided into a lower western peninsula and a higher central plateau that extends eastwards. A very steep cliffy climb separates these 2 areas, and the flatter areas are sparingly covered with extremely low vegetation, extremely dense, as we're all very familiar with by now. And as the name implies, there's obviously no obvious water sources or major drainages. Despite this, the island boasts a very large number of cisterns and several surprisingly dense areas of occupation that date from the early Bronze Age into the medieval and early modern periods, and especially with focus on the Roman. The Western complex has 2 main components that were looked at in this study. A series of low structural terraces in the west, where buildings were turned into small agricultural plots or animal enclosures, and an area of a large building with magazine-like rooms in the east, with high densities of fine later Roman ceramics, as well as several large cisterns. Some parts of this large building were modified into a later animal pen, which we can see clearly here. Overall, the best represented period is Roman, and they're mostly late Roman, though a small amount of classical and Hellenistic material is present as well, along with the early modern agropastoral structures. In the southeastern part of this complex, we have a much more heavily defined Roman composition. To the eastern complex of Anidros is divided into 2 distinct areas, the northeast and the southeast. The southeast is covered extensively in building rubble, possibly covering an area of about 2 hectares, but walls and structures are mostly preserved in the area of later reuse, is an early modern structure, and again for agropastoral complex. Depressions in the central enclosure show the outline of large cisterns, and the area contains many fragments of hydraulic mortar, ceramic ducts and water pipes, box tiles, and probable fragments of marble revetment. Substantial double-face walling is also visible in ortho photos, but it's too flat and buried in the soil for LiDAR to detect, and the large amount of building collapse makes it extremely difficult to make out a clear plan. The ceramic material in the feature is mainly late Roman, with an early modern component again. A little further up the hill from the main complex is another area of building collapse, covering about 0.4 of a hectare on the hillside. The preservation of the structures is much poorer, but traces of architectural terraces and structural walls can be seen. Interestingly, the northeast has an entirely different composition, both in its appearance in the LiDAR and in finds. It was built on structural terraces directly on the bedrock, with some large structures, and seemingly dates to the geometric, archaic, and classical periods. Though we don't have much time to go into so much detail here, a third site at the plateau of the island seems to have revealed a heavily deflated early Bronze Age component with traces of architecture, limited, heavily eroded ceramic, emery, and obsidian tools. And onto phasing on Anidros, the only area where detailed phasing of stone walling is possible using remote sensing is the southeast complex of the island, where walls and buildings are better preserved. This shows that the small church complex has two periods affecting the preservation of architecture. We examine LiDAR data and aerial imagery alongside the ceramics and other finds from the survey. The latter associated with the transformation of the area into agripastoral complex. So we can see the very clear early phase, the second phase. It's very obvious, I think. An additional benefit of visualizations determined from LiDAR has been the ability to clarify some collapsed structures. So, as you can see, in areas of immense building collapse where building plans are difficult to determine in ortho photos, as well as in the field, the VAT DTM has aided in clarifying walls within collapse, for example, here in Anidros's magazine rooms, as well as on the upper plateau area. Onto signatures. From the study of Anidros, we can ascertain several distinct signatures in how different periods appear in LiDAR imagery. Prehistoric and earlier ancient abandonment have similar traces, both being built into bedrock terracing, but the earlier ancient architecture appears slightly more raised. We find that from the Western complex, large amounts of architectural rubble and collapse blur and make things pillowy, and the architectural remains of ancient double-face walls and, of course, cisterns and depressions are markedly clear. Early modern walls and later walling is easily identified, largely due to its height, but it's also much looser construction methods. More recent single-face terrace walling is also relatively distinct thanks largely to its effect of the erosion processes around it, which retain more clarity of the structure. Moving to the Antikyria Islands and a much smaller case study, Ano and Kato Antikyri are two small islets in the south of Keros and northwest of Amorgos. They are divided by a very small strait, but have very different histories of anthropogenic activity, which makes them an interesting case study in terms of looking at how LiDAR and archaeological questions of preservation. So here, rather than a wider site overviews, we'll just focus narrowly on two comparative structures. The Antikyri Islands each have a small basilica nearby their coasts. They're about 700 meters apart and very indivisible. And while the basilica on the eastern island of Ano Antikyri has seemingly been abandoned in antiquity, Kato Antikyri's church in Archaeological remains in use today. On Anto Antikyri, a medieval three-aisled basilica has been rebuilt in more recent times. And large amounts of collapse are found in its interior, likely stemming from this later period of use. The modification from its reuse sits on top of the central nave of the original church, and it's easily visible in the LiDAR. It actually extends out to here. And the modification from its reuse sits atop the central nave, and the visible signature of this early modern reuse is very similar to what we saw in Anidros. And however, the southern wall's definition is challenging due to both collapse, poor preservation, and the thick marquee. The area around the church of Chios of Kato Antikyri has a far more diachronic picture in the ceramics collected, perhaps due to disturbances from the agricultural activities in the zone. The basilica has three distinct architectural phases, and much like Ano Antikyri, the first phase appears to date to the early medieval period. For the more complex architectural strata on Kato Antikyri, various visualizations from the LiDAR were useful in tracking some of the basilica's phasing. While the multi-directional hillshade gave clarity to the current phase, the VAT DSM highlighted much more subtle wall footings from the earlier phasing. This short case study from the Antikyri Islands shows the way LiDAR visualizations and remote sensing can be used to aid in the documentation of building phases from the Cycladic Islands, albeit quite limited. It's further shown the way in which later building constructions can preserve earlier architectural elements, though such anthropogenic disturbances change the way earlier phases appear in the imagery. Furthermore, it's not necessarily the active reuse that can hinder detection, but rather what the reuse is for. So to the main questions of stratigraphy, signatures, and preservations of reuse, this preliminary work suggests that while LiDAR-based remote sensing from construction of stratigraphic sequences of the built environments is possible in some cases, especially sites with later components. On other sites, the method sheds much little light. Where this wasn't possible on the western regions of Anidros, for example, this is largely due to the spoliated nature of the site and massively disturbed areas of reuse, particularly those that build on top of earlier wall footings. In general, later walls are much more easily distinguishable as early modern to modern, but more subtle deterministic factors, such as the incorporation of spolia, require actual ground truthing. Detecting signatures of walling from different periods can be achieved using a combination of finds associated with features, alongside general pottery collections from associated survey units. However, this may only apply to the single island landscape, rather than across the actual whole archipelago, and more testing is certainly necessary on other islands, which all have very different abandonment processes to Anidros. While fine-grained signatures are not possible to detect, it seems to be possible to make a generalized chart of characteristics for local signatures of wider epochs, such as the prehistoric, early ancient, ancient, medieval, and early modern, again, at least in Anidros. This study has also provided a better understanding of how reuse and continued occupation across periods affect the preservation of architecture as seen by remote sensing. To no one's surprise, this can be complex, and a site and wider islands' continued use or relative abandonment have a big impact. The Antiquary Islands show us that a building that has been reused into the early modern era may clean up artifacts related to its initial occupation and reuse, or modify ancient wallings, but this in itself can help to preserve the original architecture and the way it appears in LiDAR, more so than the abandonment with moderate reuse, which can then destroy and complicate the building's signature, though better preserve the relationship with the related finds. Overall, LiDAR-based remote sensing for analyzing dry stone walling in the Cyclades can be fruitful. In particular, the different visualizations used can greatly aid in clarifying walling under collapse, and it's possible to determine stratigraphic matrices, and modern structures. And we can come up with some generalized signatures on how certain sites may appear. These methods are especially useful in scenarios such as on Skip, where fieldwork is extremely limited in very remote locations. The pitfalls of this process is that it can be timely and consuming and less fruitful in more ancient sites where walls are more pillowy. It's almost impossible to detect with the resolution of LiDAR that we have actual stratigraphy in these areas. And this obviously requires support of fieldwork for both ground truthing and recovering more specific information about chronology, which is obviously a conclusion I think we have all come to by ourselves. Overall, LiDAR for cycladic dry stone walls is an excellent tool in the remote sensing toolkit, but without the cross-validation from the artifacts, orthophotos, site studies, and wider remote sensing, it holds very little actual meaning. Thank you.
Thanks, Rosie. Our final paper of the day is called LiDAR Applications in the Australian Paleohora-Kythera Archaeological Survey, Workflows, Paradigms, and Limitations. And this is by Konstantinos Trimis of King's College.
Hello. What a better way to close a conference or a workshop with a trip to Kythera. Also, it's a great way to close a conference with a paper that has no results yet. So, anyway, I think Alex could put this paper either very first or at the very end of the workshop. And not just because there's no results. It's because it's a paper that is very it's a project, and the LiDAR applications here are very different to what we've seen the whole day. So, in the previous paper, there was a very little infographic saying remote sensing, fieldwork, interpretation. In our case, which is pretty much what we've seen today, LiDAR applications embedded in the project design from the beginning. Now, APCAS it's a quite old project. It's been established in 1999 by Professor Timothy Gregory from Ohio State, Lita Georgopoulou from the Australian Archaeological Institute, and Stavros Paspalas, also from the Australian Archaeological Institute. In 1999, I was 12. And I was in Kythera as a student, but not part of the project. So initially, APCAS was focusing only in the blue area here, and it was mainly trying to examine the relationship that the medieval capital of the island, that has been destroyed and abandoned in the 16th century, which has been called by the locals Paliochora, hence the name of the project. So the relationship that the medieval town had with its immediate environs. So Paliochora located here. I don't know if you are any familiar with Timothy Gregory's survey methodology and proposal about less is better, but it's a bit different to the grids that we have are more familiar today. So we have, it's a site-specific area, very intensive, that follows an extensive to intensive way. The yellow areas are the intensive locality-based survey areas, where the rest of the areas hasn't been surveyed. Now, the project has two main phases, one from 1999 until 2007, which is the blue area, and then between 2016 and 2021, when I joined the project as initially the prehistoric specialist of the project, we expanded to the north and to the south. And the area here, it's been surveyed pretty much in the same period by the very famous Kythera Island project of Cyprian Broodbank, Vagilio Kingazi, Andy Bevan, James Connolly, and the rest of the dream team. So this is it's not an unknown area, okay? So very early in the 99, remote sensing was embedded in the idea of the project, mainly using a technique that is quite known to the Greeks in the room, and I suppose to many of you that you're not Greeks, and it's what we call photointerpretation or photoerminia in Greece, which is stereoscopic interpretation of old army aerial photographs. And the whole point is actually to detect medieval features or fortifications or sites so they can go and do intensive surveys in these areas. So this is the northeast corner of side of the island. This is the port village of Agia Pelagia. And there's a little area here and slightly bigger there. This is the locality of Agios Georgios Kolokithia, and here is the locality of Vithulas. And as you can see from this sort of photo interpretation way, they located fortifications that we cannot date, but they are there. And in Vithulas and in Agios Georgios Kolokithias, we know that now it's 12th century. And then intensive survey followed. In 2016, because a group of remote sensing geeks jumped on the project, including myself, John Fardoulis from Richard McNeil from La Trobe, from Michigan, John Fry from Michigan State, which is now taking over Isthmia, and a few other people, we decided that we will make this project very intensively remote sensing. And our main concern was to see the areas that they were outside of these site-specific surveys that have been already undertaken. We kind of worked with quite a lot of local people that they fly drones because we were trying to get them engaged with the project, and we also brought our own equipment to the island. We said, okay, let's make a workflow and try to publish this workflow as the blueprint on how remote sensing should work in this sort of environment. So we came up with this workflow that, first of all, we're gonna get and analyze the 10-meter resolution satellite imagery that is freely available for research. That's the Planet portal that many of you may know. We downloaded, we used Sentinel imagery and Landsat data for the big questions, for example, terracing or vegetation coverage, etc., hydrogeological networks. Then the second level is to use the declassified hexagon satellite imagery that is 1 meter resolution, and hexagon imagery in Kythera, over Kythera, covers a period from the late 70s to the early 80s. So quite a lot of the areas that they are now very densely vegetated, back then they were still agricultural land, so you could, or farming land, so you could see a little bit more. And then the backbone from 2016 until to 2020 was remote piloted aircrafts, or drones or UAVs, or call them as you like anyway. So things that they fly without a pilot in them, structure for motion photogrammetry survey. However, and that's the reason that we are all in this room today, the problem with the SFM survey is that you cannot see below the vegetation. And if I get you back to our picture here, a main reason that these areas hasn't been surveyed is because there's a really, really dense, very dense Mediterranean jungle. And there's forests, high shrub, bushes, it's impenetrable. So we experiment with different ways on the RPA, and then we get up with a solution that I'm going to talk to you about in a second. But post-2020, we said, all right, the only way is LiDAR. And we decided to follow 2 extra steps in our workflow. Once RPA photogrammetry shows us that the site has a potential, then we decided to run RPA LiDAR surveys. And then if we have features on the ground, use these fantastic things that Apple has created the last couple of years with the mobile phone-based LiDAR sensors. And then we run feature-specific LiDAR to record features. And sometimes this can be extended to micro landscapes, and I have an example for you at the end. But before that, up to 2019 season, the backbone of our remote sensing was flying drones with modified cameras, and then use the vegetation suppression algorithm to try to remove vegetation. And I'll give you an example from this fantastic tower or building complex that is medieval, and we know that from the survey. And you can see the little tree popping there. Now, on the modified ortho, you modify the camera so vegetation appears in magenta, and then you run the vegetation suppression algorithm, and then the tree is gone. But it works only in very little things like this, or in very large areas, like on Landsat images. Here, if you try to remove vegetation, in areas you might get manually to remove some of the bushes, but you get no information, it's just blurry, or very little information as it down here. Or there, you just get a purple hue on your ortho. However, in places like here in the Pyrgos, or there in the apsidal form of this church that we discovered next to the Pyrgos, to the tower, and here is the wall that was surrounding the place. It works, but it doesn't work that well in most of the cases. It works only in very specific cases. But anyway, that was what we've been doing, mainly because that was cheap, quick, and dirty way. It didn't cost us any money. We could do it ourselves, and funding was always a problem. And that's the field survey around the tower. You can see the medieval scatters. Now, in 2020, we came up with the idea of let's fly a drone with a LiDAR sensor, COVID happened, we couldn't come out of the field for a couple of years, and then we managed to do this just 2 months ago. And that's the reason that there's no a lot of classification to show you tonight. But we had a Rigel Mini 3 UAV sensor with an RGB camera. It gives you 5 echoes, up to 5 echoes, so it seems that it would be a good option. I'm not going to get into the details because we've been discussing this all day and it's pretty much similar to what we've been hearing. But I'm going to show you a locality as an example about the problematic of having old survey data, areas that has been already surveyed, and then you use LiDAR in order to contextualize what you've been seeing. And that's the Cambi area, which in the jungle there is an opening, and this opening is pretty small, so it's about, let me get the scale right, as you can see it's about 50 to 100 meters wide. And in this 50 to 100 meters wide, you have a very dense terraced landscape. You have a Middle Bronze Age chamber tomb that has been excavated by the F48 in 2000. And then you have our team in 2019 doing sections in the terracing and OSL dating that proved that these terraces are at least built in the 2nd millennia. And then they have a phase of rebuild in the classical period until you have a 3rd phase of rebuild in the 17th to 18th century. So another thing is in this gorge you have water mills, you have water management systems. So if I show you a picture, in this little area you have one mill complex down there and a spring complex, a random building here, another spring complex, and then you have the terraces, the grave, that's our units that we managed to survey. Very high yield of prehistoric pottery and classical and Roman pottery. And then you have jungle, in order to come down here when you have a second area of activity that we could survey. So you get random terraces that they're built in the 2nd millennium, Middle Bronze Age, with lots of Bronze Age pottery. And then it's like a little window in the jungle, and then you don't know, you cannot contextualize it. So here is, for example, is where we flew one of our LiDAR case studies, trying to see what's going on and trying to contextualize this data. This is the raw point cloud, the last file we got, which is okay, but now so far, and this is how far we've been, it's my experience working with LiDAR data, it's mainly the open source LiDAR data that you get from the OOS Ordnance Survey that pretty much covers the whole UK. So you get already classified data that you can work with. And now it's my first time that I'm trying to work with a LAS file from the beginning. So what I did is I tried to run the algorithm that in QGIS, using LAS tools, that I'm using in the UK. Not surprisingly, this is what I got when I went down to bare ground. It's full of holes. So first lesson is the UK algorithms that I've built for UK case studies, where you have high canopies, bigger leaves, but no shrubs, they don't work down here. So I kind of playing with the echoes and the height of the beam. What you can get is if you go slightly off the ground, you have buildings popping out from the last file. But again, the data quality is not great. So as I said to you, I don't have results to show you really much. What we know so far is there should be a building here, potentially a mill complex very close to the spring. The spring is there, so this is the white plateau of the spring complex, which is there. So the building should be in here. Actually, it's there. You can see it now. It's still a question. It's a work in progress. We got this data in early February, and I just realized that I have to pretty much start from the beginning and forget what I knew doing LiDAR processing in the UK. So today was actually a very good session for me to be here. We had a lot more success with the feature-specific mobile-based LiDAR. Now, the sensors in the iPhones and iPads are classified by Apple. So it's very difficult to write a paper because you cannot talk about the specifics. We kind of assume the sensors, and this is the I don't know how if you've been to Kythera, but this is the landmark that it was in the first picture. Is this English British period lighthouse, and then the British period optical telegraph, the cymatorion, as we say in Greek. Now there was a lot of associated buildings that we didn't know exactly here in the terraces, right on the cliff, that they have a very high yield of pottery, 19th century pottery, no pottery that goes after, and no pottery that goes before the 19th century. We have British Protectorate pottery alongside British Protectorate buildings, so we assume that these buildings that they are deep in the shrub, they're also from the same period. Now, this is the conventional side photography. Okay, I placed my scale wrong here, so they should be in this side, but I think you can get the scale. And I did this in about 12 minutes, having my daughter on my back. By myself. You get a very good actual coverage, and then you have a pretty accurate ground plan where you can see the buildings and even the division walls. Now, doing a little bit of archival work, because the Kythera archive it's quite well preserved, we found out that these buildings are associated with the lighthouse keepers' families. So there's most possibly their barns, their pens where they're having their animals. So it ties well with the story of 19th century pottery. But I think the handheld sort of LiDARs, and it can be used more than recording an object. And in these cases, you can record the whole micro landscape, and then you have a quite decent ground plan without getting into the point of flying a drone to get a photogrammetry, for example. Because tying this into, for example, with handheld photogrammetry in Metashape, it would be, if not impossible, very difficult, because you have a cliff here that you cannot walk, so you get the full coverage around. Some early observations. As I said to you, this is a very, very recent work in progress. We're still in the data acquisition phase. LiDAR, RPA LiDAR, airborne, UAV LiDAR, is very easy to run because if you're familiar with flying any drone, you can fly a bigger LiDAR handling drone, but it's still costly, so the equipment still costs a lot. Now with the new Zenus 2 camera that DJI came out, I'm really keen to use it because it's the first time that the LiDAR sensor that gives you up to 5 echoes, so similar with the Rigel that we used here, it's about 1/10 of the price of the Rigel. So now we have a pretty affordable camera giving you the same sort of echoes with a high-end camera. For the RPA, one thing that they came straight away, and I'm not sure if this is it's in our case, but you've seen this in yours, is we didn't get the point cloud we expected. So what we've seen in the specs of the machine, it's not matching what we get from the ground. And I don't think, I'm not sure if this is a vegetation issue because we ran the drones in the thickest areas, or has other things the other things that are happening. For mobile device-based LiDAR, the major limitation we observed is we've done quite a lot of laser scanning, and you get the sort of shadows, particularly in shrubby areas with vegetation. It's not when you have a nice building to record. So you get these ground shadows. This thing seems to be the same for handheld LiDARs. Then, for me, coming from photogrammetry into the LiDAR regime, it seems that we're still lacking, even if now hardware becomes cheaper and more accessible, still the software, you need multiple software applications in order to get a good classified result, compared to the structure for motion photogrammetry that is becoming the bog standard now for the industry, that you have a single software or a couple of softwares to go. It's very straightforward to use it in order to get some meaningful results. Finally, and I forgot to put the DM in the presentation, when we've compared the DM from the LiDAR application and the SFM application in the Cambake-Ramari area, there was not much difference. So it seems that you can get pretty much the same results with structure for motion photogrammetry. Now, the APCAS has been supported all these years by the Nicholas Anthony Aroni Trust, so we thank them a lot. And personal thanks to Lita and Stavros, who got me involved in the project, and to Tamar, who now really pushes us to publish this thing, and it's going to be a big volume coming out at some point next year with everything in there. Thank you very much.
All right, should we have the speakers come up to the front, and we'll have our final discussion section and Q&A? While people are coming up here, would anyone like to ask a question? Yeah, Sil?
This is probably a bad question. I heard several times today the term stratigraphic sequence, and it was just, I thought it might have been a bit misleading to use it, especially if there's no excavation involved. And I wondered if that's entered, I mean, if it's a technical term, I'm just not aware with it, but it looks more to me like, you know, architectural phasing. So I don't know why you choose stratigraphy in this case.
Yeah, that's a great point and a good question. The term comes from primarily the paper from Neve and Michael. They were using that term, so I think we were continuing on with it. But indeed, phasing is probably more of it. I think it comes from the Harris matrix that, although I didn't present, that we had been creating and was created from that. So I think it's just simply translation coming, but indeed, phasing is probably a more accurate. Yeah.
Other questions?
Excuse me, may I give a comment to this? Because I was directly also addressed, or I feel directly addressed with this question. It is okay?
Yes, of course. Thank you, Michael.
Okay. What we're actually doing here is stratigraphy, because the stratification is not only deposits but surfaces. And what we finally have in an urban laser scan is surfaces of deposits. So if you have a bank, you have a deposit, and what we see is the surface. If it would be covered and excavated, you would get the same surface in the stratification. Now, if there's two surfaces intersect, we can see which is old and which is young, and we can build the Harris matrix. So it's a perfect stratigraphy, however, not with excavation. So I think the term is right here in this case.
Thank you. Other questions? Comments or final thoughts?
If I'm still on, I would like to make a comment also to the last presentation, and there was one before. I'm a bit afraid that sensors like the Minivux, they are not strong enough to penetrate this kind of dense vegetation. And we've seen this, of course, in the presentations. There would be stronger UAV-based or drone-based sensors, like, for example, the VUX. There's also others where you could get maybe 2,000 points per square meter. However, the costs are, of course, much more increasing. But I'm afraid in this kind of dense vegetation you would need some kind of this sensor. I'm afraid that maybe also 5 echoes would not be sufficient.
I had not a question, but a comment on the busy built environment of Renia, which I didn't expect to be nearly as busy and as rich as you demonstrated. So thank you very much for that. And this is just not a random question, but a curiosity. When you talked about farmsteads and all, I was reminded that the French excavators of the Sanctuary of Apollo have suggested that Renia was a place where the hecatomb of cattle were kept in advance of the sacrifices. And I wondered if you found any sizable enclosures that might be a kind of waiting areas for 100 cattle or so, or if they were all small-scale farms.
In general, the farms are small scale, except of one area, the Pallia Vardia, with a very large enclosure, which is at the top of a low hill near the necropolis. In the beginning, we thought that we could speak about Pallia Vardia, but at the end, we decided not to do it, but there was not enough time. But I don't think that this area was something as you mentioned, for keeping the livestock for the sacrifices. I think it was something easier, as it is today, small farmsteads with the animals, and then they guided all these to the boats to go across to Delos. I don't think that there will be a very big enclosure for all this stuff, and mainly, yes.
Thank you.
We don't have any traces of such a place.
Can I ask one other question? And I might have just missed this at the beginning of your talk, but you pointed out the major funerary monuments all along the coast, and there was a red line that ran along there. Was that a physical marker? Or,
No, it's not a physical marker. It is a schematic one. There is no perivolos or an enclosure of the necropolis, but it seems that there were some peaks, some monuments that marked the ends of the necropolis, visible from Delos. We believe now that the visibility between Delos and Renia was very important, and we think it's early yet, that many questions concerning the extent and the position of the farmsteads, even the 2 Delian sanctuaries in Renia, there were 2 Delian sanctuaries, Dionysion and Artemision and Niso, Artemision the island, had a visual contact with Delos. But no, there was not an enclosure. We haven't found one.
Any other questions?
Could I say something else?
Yeah.
Yes.
So I was thinking about this whole day, or at least the part that I saw once I woke up at 5 in the morning. As an outsider, just coming to work in the Mediterranean, I've done some work with Syl, a lot of work with Alex, and now getting involved in the Samothrace work. You guys use LiDAR very differently than we do in the Maya area, which is understandable. It's clearly more of a tool in the Mediterranean. Rosie kind of highlighted that it's another tool in the Mediterranean Archaeologist toolkit, and it needs to be used in this complementary way, which I think is very appropriate based on, you know, my own experiences on skip. I do wonder, you know, how we can use LiDAR at sort of a regional scale in the Mediterranean in an effective way. And, you know, I think the point of Brody in my paper earlier with the ground truthing results is that the only thing that's really showing up regionally at a sort of acceptable accuracy from a traditional, you know, remote sensing ground verification is the, you know, the agricultural terracing. And I do wonder, you know, is there an interest in doing sort of broader analytical studies of LiDAR-based research as opposed to maybe more site-focused? LiDAR is sort of a tool, it improves methodology for survey and documentation, but, you know, what are the sort of steps for like regional LiDAR-based analysis? And I guess I would just pose that as a general question to anyone that wants to respond.
If I may jump in, Tom, because your question actually connects to a question that I have, is first of all, to respond to what you just said, I think that is largely determined by cost and just the availability of public repositories of mass regional scales. I suspect that is the main obstacle here. And then the other question I had, of course, is if we were to go that way, let's say if the geographic service of the Army eventually flew a mission over the entire country and we had wonderful repositories like the ones in Spain and other parts of Europe, what would we do? You know, I think that's an avenue of really interesting research. And of course, I think we also need to think as practitioners of LiDAR in this field, what do we do with the data that we already have? How do we share that? How do we curate that instead of having them partitioned and siloed in individual projects here and there?
Yeah, I also, you know, that also reminds me of, you know, this is really great that you are all getting together to talk about how you use LiDAR now. And I do think that thinking towards a future of sort of broader comparative analysis, you know, coming together maybe in a separate workshop and you know, thinking of sort of basic standards that any project would want to record. You know, this is something I know when Brody presented earlier, he was talking about if he had to do it again. And now, you know, we are kind of doing it again as we take our lessons from Skip and start moving to Samothrace. And there are things that we want to update, but we're also very cautious that we want to maintain some of the baseline stuff we were recording from Skip with the idea that we're growing, you know, a sort of data set for comparative analysis. And I just wonder if, you know, there would be a good time for projects using LiDAR to get together and start thinking about sort of baseline standards that people want to be recording in terms of classification and ground verification, so that, you know, at least at a very coarse level, data will be comparative in a future.
Giacomo, you talked a little bit about some forthcoming standards that you've been working on. Will you say a little bit more about that?
Yeah, there is a committee of the AEC, the European Archaeological Council, that actually has been working. We are around 30 people. There is also Michael Doneus, there are Zigali, you know, there are a lot of people much better than me that actually we have been working on those, and there is actually a guideline that is coming out in a few months. We actually were discussing the cover of the book a few days ago. Therefore, that one will actually be, you know, it's a collaborative effort. I have to be honest, a little bit mainly based on researchers that have been working in temperate Europe, and is a little bit underrepresented the Mediterranean side, because we have people from Spain, people from Italy, but other than that, yeah, unfortunately, you know, when it started, yeah, maybe it just, you know, just how it is. But those will come out in a few months, and the aim is actually to discuss a possible standard for the processing. For instance, for the visualization, we are suggesting VAT, that I think many of you have been using, and I think is very effective. Therefore, you know, there are a lot of, maybe that, you know, of course it's a guideline. It could be a starting point to then actually see what has been done in Greece by many of you, and see if it actually can be compatible with those guidelines or standards, as you want to call them, that have been developed for mainly based on other parts of Europe. But I think, you know, it's interesting because there is a lot of discussion in those by people that have been working with LiDAR for 20, 30 years. And there are a lot of, I think, observations that are not so 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 fast to see. A lot of reflections on that. And just to just a second, just about the Mediterranean landscapes, we actually have quite my project in Italy, but also in Spain, we actually have 2 or 3 very large LiDAR scale regional projects that cover thousands of square kilometers. Therefore, those can be maybe something to something that is starting, and actually they are largely due to the fact that we have open source data. That's very true, because if we had to pay for that, it would not have been possible. And I think Portugal will be the next to have I know of many also Chezeaux here working of big project that will come up on a very large regional scale, thanks indeed to the data that will be free.
More of a comment here, which it's also my personal kind of struggle at the moment. So I'm an archaeology surveyor, but I became one in the UK, where everything tends to be standardized. So if you're interested of doing something, I was working in a company, like an archaeology provider company, and then a client came in and said, I need this data analyzed from LiDAR. I had zero idea about LiDAR 5 years ago. I mean, I knew what it is, but I've never worked with any sort of data. It takes about 2 days to learn how to create industry standard results. Because there are many standards and guidance and courses you can go for a day or 2 days, or your company can send you that what happened to me, and you get a bog standard, and these standards work well for the UK vegetation, geology, geomorphology, the Ordnance Survey dataset. But if you come out of this context, you're lost. You need to learn everything from the beginning. So I don't know, but a good suggestion from, and when I read the workshop initially title of today's event, I was thinking that it should be something like that and not as like a mini conference. But it should be interesting if someone for the Mediterranean that has different geomorphology, different hydrology, vegetation, land coverage, or even structures, comes up with, I mean, we don't have the intense terracing, for example, in the UK or in Northern Europe in general. It sits down and writes a sort of a standard guidance of data acquisition to data processing and then data publication, and then people can refer to that. I don't know. I don't know where we are in the process, and I'm a very late comer to the party. But I believe people that are working more on this, we need to start thinking towards that, because nothing, I mean, I'm not going to open that discussion, but even archaeological excavation is not standardized in this part of the world. So.
Yeah, maybe standard is not actually the right term, because those are guidelines that actually are theoretical guidelines in large part. They explain which are the principles behind the processing of LiDAR, behind all the, it's just like a guidebook for people that do not know, they don't know LiDAR and they approach it for the first time. Therefore, the aim is to pinpoint to all the pitfalls that people that have been working for 30 years, not me, had encountered. Therefore, in that sense, I think it's more useful. It can still be useful. It's not like the guidelines do not offer coefficients, do not offer like specific things. It offers actually all these observations that we also always discussing. All those kind of things that after you work is 8 years in my case that I work with LiDAR, you start to see, you start to think about, and those are actually what was the aim in the guideline to offer mainly. That I think the observation on the processing and so on, it can be quite, I think, valid across a range of landscapes, of course. There is also actually at the end a series of chapters that are specific for specific landscapes. And they are like terrace landscape, karstic landscape, those are maybe, they're made by specific people that have been working on those specific landscapes. But, the general idea is more to provide a first introduction with a lot of things to think about when you actually start your own project. For in that sense, maybe, yeah.
Can I have a very quick comment on that? That's fantastic. But I believe that since it's been applied and reapplied a lot of times, and in Italy, now in the Balkans, I mean Croatia, because I'm working a lot, they started having a national data set now as well. Slovenia the same. Observations like the one that has been heard about our applications, that 5 echoes with a Rigel Mini 3, it's not enough to penetrate. So that's what when I was saying, I used like the standards and guidance is what the CIFA calls all these sort of nodes. But a node like that as a minimum, for example, a minimum hardware specs that you should have. And of course you can experiment, but from the people's experience, being out there, being accessible, so you stop wasting money on things that they not work at the end of the day, I think would be fantastic to have it in the near future, particularly now where we have big projects like the SCIP that they are doing this sort of testing.
I guess, I think, standards was maybe the wrong word, but maybe baseline would be a better word of sort of, minimum things that are going to be recorded by certain projects. And I think that part of that is not just, okay, we're identifying terraces and structures and, whatever features you guys have chosen to classify, but also coming up with sort of baseline ideas of how ground verification and accuracy metrics are going to be reported, because one of the things that we're running into as LiDAR has matured in my archaeology is different projects trying to do broader comparisons now, but they used totally different sensors to acquire their LiDAR data. And for us, it's all aerial. There's very little drone work that's been done, but you guys are dealing with such a wide range of sensors that in order to mitigate some of the problems with, inter-sensor data comparison, having standards for reporting error and doing analysis on the types of errors is also something that's going to be important as you try to, extrapolate and compare from the different types of LiDAR that have been used.
Thanks, everyone. We're running short on time, and I think it won't hurt if we conclude a couple of minutes early. I just want to say a couple things at the end here about a few kind of common themes and questions that have emerged from the papers today. And I'm going to keep this to basically just 6 bullet points that I think that we should keep in mind looking ahead. One are these questions of scale that we've just been talking about, right? We've seen papers that dealt extensively with LiDAR as a kind of documentation tool for features, sites, and landscapes, but we've seen less on this kind of truly regional scale that Tom was getting at. And I think part of that has to do with the nature of our data sets, but it's definitely something to think about going ahead. Second, we've been talking about lots of different types of data sets and data comparison, what appears differently in these different data sets. And I know much of what we've seen today is a work in progress, but I'd stress that it's really, really important to publish these comparisons, because this is how we move on to establishing best practices and people being able to pick up these toolkits and decide where and how to deploy them. On the topic of publication, we have struck a deal with the Journal of Greek Archaeology to publish a special issue there for these papers that have been presented today. And I'll be in touch with speakers about more information there down the road. Don't worry, there are no immediate deadlines or anything like that. Fourth, one thing that we have not discussed in much detail here are issues of data sharing and data publication and open access to data, for example, especially as these things relate to cultural heritage management. These are things that we'll have to think about going ahead as LiDAR becomes more widespread in Greece. On the one hand, open data offers access to more people, which in some cases might be a bad thing, and in some cases might be a good thing. That access can also be good in terms of site monitoring and possibilities for citizen science, as some people were talking about at lunch today, and interest and participation in archaeological work and remote sensing. One thing that came up again just now is one big question, whether public data is forthcoming in Greece. I don't know if anybody knows anything more about that than I do, but if you do, I think lots of people would like to hear about it. So we can make an exception to the end after this, and you can speak up. And then finally, we talked probably less than we should have about issues of temporality in these data sets that we're analyzing and working to make interpretations from. We've said many times that it's obvious that, or evident that LiDAR is recording a moment in time and it's everything together, right? Some of us have tried to deal with issues of chronology, phasing, and so on. And I would just encourage everyone to keep developing these sort of phased approaches to analyzing the data sets that we're looking at here. Bonna, do you have any concluding thoughts?
That was a very nice summary. I have slightly different kinds of comments, less maybe intellectually and more socially driven. I felt that there's a lot of great energy and collaboration in the room. Maybe a lot of island emphasis. Over half the papers were on islands, but that might be because half the papers were by Alex and Sylvian. But no, there was other islands there too. I was really struck by the way in which people mine different sources of data and are always really gifted strategists in the way in which they combine historical and archival data with legacy technologies and to put together the best possible vision of the Greek landscape. I also felt that it was really an interesting comparison between aerial and drone LiDAR and the challenges of the two. I learned a lot in that respect. I also learned really clearly that it's not an armchair activity, that LiDAR acquisition and analysis is the precursor to ground truthing as best as you can. Knowing that some places are really impossible to reach, and that's why this is actually also a really good technology. Many projects seem to be in their early stages, and I think that's also really good because it gives us a chance to begin to make collective choices, maybe. And again, this goes to the issue of maybe coming up with some basic parameters of how we want to think about the data, and as Tom said, not necessarily standards, but commonalities that will make it useful across projects. I'd like to, Konstantinos always provides us with the number of people who are watching online, because while this has been a wonderful group here in the room, you are joined by 1,668 others who were also listening in today. So it's really, I want to just congratulate the speakers for presenting to a very wide audience a very interesting work. And I'd also like to very much thank the staff of the American School, especially Niamh Michalopoulou and the housekeeping staff for the coffees, the lunch, and the soon-to-be reception. And also our digital media team with Konstantinos, Miguel, Dimitris, and Christos, without whom this would not have gone nearly as smoothly as it has. So thanks very much to that group, and on behalf of the American School, thank you. I think with that we can adjourn to the patio and the ground floor and share a glass of wine together. Thanks very much.